Welcome to Loops and Loops, your ultimate destination for all things deep learning. Whether you're a seasoned AI enthusiast or just dipping your toes into the world of neural networks, you're in for a treat. Join us as we unravel the mysteries of machine learning, dive into the latest research, and explore cutting-edge techniques in the realm of artificial intelligence. Get ready to expand your knowledge, sharpen your skills, and embark on a journey of endless possibilities with deep learning. So grab your headphones, settle in, and let's embark on this fascinating adventure together. Deep learning is a subset of machine learning that deals with algorithms inspired by the structure and function of the human brain, called artificial neural networks. Unlike traditional machine learning, which focuses on feature engineering and manual extraction of relevant information, deep learning aims to automatically learn hierarchical representations of data directly from raw input. Neural networks in deep learning are computational models inspired by the biological neural networks in the human brain. They consist of interconnected nodes or neurons organized in layers. Each neuron receives input signals, performs computations, and passes the output to the next layer of neurons, ultimately producing an output prediction. Deep learning models learn from data through a process called training. During training, the model is fed with input data along with corresponding labels or targets. The model adjusts its internal parameters iteratively through optimization algorithms such as gradient descent to minimize the difference between its predictions and the actual targets, thereby learning to make accurate predictions from new, unseen data. Common applications of deep learning include image and speech recognition, natural language processing, computer vision, autonomous driving, medical diagnosis, recommendation systems, and many others. Deep learning has demonstrated state-of-the-art performance in various domains, surpassing traditional machine learning techniques in tasks involving complex patterns and large-scale datasets. Advantages of deep learning include its ability to automatically learn hierarchical representations, handle large and unstructured datasets, and achieve superior performance in complex tasks. However, deep learning also has limitations such as the need for large amounts of labeled data, computational resources, and expertise in model design and optimization. A basic feed-forward neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is composed of interconnected neurons, and information flows forward from the input layer through the hidden layers to the output layer without feedback loops. Neural networks are trained using backpropagation, a technique that involves iteratively adjusting the model's internal parameters or weights based on the difference between predicted and actual outputs. Backpropagation computes the gradient of a loss function with respect to the model parameters and updates the weights to minimize the loss, thereby improving the model's predictive performance. Activation functions in neural networks introduce nonlinearity to the model, enabling it to learn complex patterns and relationships in the data. Common activation functions include sigmoid, tan rectified linear unit, and softmax, each serving different purposes such as introducing nonlinear transformations, handling vanishing gradients, or producing probability distributions. Different types of layers commonly used in neural networks include dense, fully connected layers, convolutional layers, pooling layers, recurrent layers, and normalization layers. Each layer type performs specific operations on the input data and contributes to the model's ability to extract features and make predictions. The number of layers and neurons in a neural network, known as its architecture, can significantly affect its performance. Increasing the number of layers and neurons can enhance the model's capacity to learn complex patterns, but may also lead to overfitting, where the model memorizes the training data and fails to generalize to new data. Finding the right balance in architecture design is crucial for achieving optimal performance. Convolutional layers in CNNs are designed to detect and extract spatial patterns and features from input images. Their purpose is to perform convolutions, which involve sliding small filter kernels across the input image, computing dot products at each position. This process enables the network to learn hierarchical representations of features, capturing local patterns such as edges, textures, and shapes. CNS handles spatial hierarchies of features by using multiple convolutional layers with increasing receptive fields. As the network progresses through layers, higher-level features are constructed by combining lower-level features, capturing more abstract and complex patterns at different spatial scales. This hierarchical approach allows CNNs to learn representations that are invariant to translation, rotation, and scaling. Pooling layers in CNNs are used to downsample the feature maps produced by convolutional layers, reducing their spatial dimensions while retaining important information. Pooling operations such as max pooling or average pooling aggregate information within local regions of the feature maps, helping to achieve spatial invariance, increase computational efficiency, and reduce overfitting by reducing the model's parameter space. Filter kernels in CNNs are small matrices of weights that are convolved with the input image. To produce feature maps, each filter kernel captures a specific pattern or feature, such as edges, corners, or textures, by learning the optimal combination of weights during training. By stacking multiple filter kernels in each convolutional layer, CNNs can learn to detect a diverse range of features across different channels. CNNs find applications in various computer vision tasks, including image classification, object detection, semantic segmentation, and image generation. They excel at recognizing patterns and structures in visual data, making them invaluable in areas such as autonomous driving, medical imaging, facial recognition, and surveillance systems. Recurrent neural networks are suitable for processing sequential data because of their ability to maintain temporal dependencies and capture long-range dependencies in sequences. Unlike feed-forward networks, which process input data independently, runners have recurrent connections that enable them to incorporate information from previous time steps, making them ideal for tasks involving sequences such as natural language processing, speech recognition, and time series analysis. Recurrent neural networks maintain memory of past inputs through hidden states, which are updated at each time step based on the current input and the previous hidden state. This recurrent nature allows RNs to capture temporal dynamics and dependencies in sequential data, enabling them to model sequences with variable lengths and learn patterns across multiple time steps. Training recurrent neural networks can be challenging due to issues such as the vanishing gradient problem, where gradients become extremely small as they propagate through many time steps, leading to slow convergence or unstable training. This problem arises because of the repeated application of the same weight matrix in recurrent connections, causing gradients to either vanish or explode during backpropagation. Long short-term memory networks are a type of recurrent neural network architecture designed to address the limitations of traditional recurrent neural networks, particularly the vanishing gradient problem and the difficulty of learning long-term dependencies. Long short-term memories introduce specialized memory cells with gating mechanisms that control the flow of information, allowing them to selectively remember or forget past inputs and gradients over multiple time steps, facilitating better gradient flow and more effective learning of long-range dependencies. Recurrent neural networks find applications in natural language processing tasks such as language modeling, machine translation, sentiment analysis, and text generation. They are also widely used in time series analysis for tasks such as forecasting, anomaly detection, and sequence prediction in domains such as finance, healthcare, and weather forecasting. Their ability to model sequential data makes them versatile and powerful tools for a wide range of applications requiring sequential processing. Optimization algorithms play a crucial role in training deep learning models by adjusting the model's parameters to minimize a predefined objective function, also known as the loss function. These algorithms iteratively update the model's parameters based on gradients computed from the loss function, aiming to find the optimal set of parameters that best fit the training data and generalize well to unseen data. Stochastic gradient descent is a widely used optimization algorithm in deep learning. It works by randomly selecting a subset of training samples called a mini-batch to compute the gradients of the loss function with respect to the model parameters. Stochastic gradient descent then updates the parameters in the direction that reduces the loss, typically multiplied by a learning rate. Variants of stochastic gradient descent, such as Momentum, AdaGrad, ERMS Probe, and ADAM introduce modifications to improve convergence speed, stability, and performance in different scenarios. The loss function in deep learning quantifies how well the model's predictions match the true labels or targets in the training data. Its purpose is to measure the discrepancy between predicted and actual outputs, providing a feedback signal that guides the optimization process during training. Common loss functions include mean squared error for regression tasks, categorical cross-entropy for multi-class classification, and binary cross-entropy for binary classification. Gradients are calculated using backpropagation, a technique that computes the gradients of the loss function with respect to the model parameters by recursively applying the chain rule of calculus. During forward propagation, input data is passed through the network to compute predictions, and during backward propagation, gradients are computed layer by layer, starting from the output layer and moving backward through the network, allowing efficient computation of parameter updates. To prevent overfitting in deep learning models, several techniques can be employed, including regularization, dropout, early stopping, data augmentation, and model architecture design. These techniques aim to reduce the model's capacity to memorize noise and irrelevant details from the training data, promoting better generalization performance on unseen data. Activation functions introduce nonlinear transformations to the output of neurons in neural networks, enabling them to learn complex patterns and relationships in the data. Popular activation functions include a rectified linear unit, sigmoid, and tan, each serving different purposes such as introducing sparsity, handling vanishing gradients, or controlling the range of output values. Dropout regularization is a technique used to prevent overfitting by randomly deactivating a fraction of neurons during training. It works by probabilistically dropping out neurons along with their connections, forcing the network to learn redundant representations and increasing robustness to noise in the training data. L2 regularization penalizes large weights in neural networks by adding a regularization term to the loss function proportional to the square of the L2 norm of the model's parameters. This penalty encourages smaller weights, preventing the model from fitting the training data too closely and improving generalization performance on unseen data. Batch normalization is a technique used to improve training stability and accelerate convergence by normalizing the activations of neurons within each mini-batch during training. It works by computing the mean and standard deviation of activations across the mini-batch and then scaling and shifting the activations to have zero mean and unit variance. Batch normalization helps address issues such as internal covariate shift and vanishing gradients, leading to faster and more stable training of deep neural networks. Generative adversarial networks are a type of deep learning architecture consisting of two neural networks, the generator and the discriminator, which are trained simultaneously through adversarial learning. The generator generates synthetic data samples, such as images or text, while the discriminator tries to distinguish between real and fake samples through competition and cooperation. Generative adversarial networks learn to generate high-quality, realistic samples that are indistinguishable from real data. Transfer learning is a technique in deep learning where a pre-trained model, trained on a large dataset for a specific task, is fine-tuned or adapted to a different but related task with a smaller dataset. By leveraging knowledge learned from the source task, transfer learning enables faster and more efficient training on the target task, especially when labeled data is limited or expensive to acquire. Reinforcement learning is a branch of machine learning. concerned with training agents to make sequential decisions in an environment to maximize cumulative rewards. It is related to deep learning in that deep neural networks are often used to approximate value functions or policies in reinforcement learning algorithms, enabling agents to learn complex strategies and behaviors in domains such as gaming, robotics, and autonomous driving. Attention mechanisms in deep learning models like transformers enable the model to focus on relevant parts of the input data while performing tasks such as machine translation or text summarization. By assigning different weights to different parts of the input sequence, attention mechanisms allow the model to selectively attend to important information, improving performance on tasks involving long sequences or complex relationships. Challenges and limitations of current deep learning approaches include issues such as interpretability, robustness to adversarial attacks, data efficiency, and generalization to out-of-distribution data. Deep learning models may also suffer from overfitting, scalability issues, and lack of transparency in decision-making, posing challenges for deployment in real-world applications. In computer vision tasks like object detection and image classification, deep learning models analyze visual data to identify and classify objects in images or videos. They achieve state-of-the-art performance by learning hierarchical representations of features directly from raw pixel data, enabling tasks such as object localization, segmentation, and recognition in diverse and complex scenes. In natural language processing tasks like sentiment analysis and machine translation, deep learning algorithms process and understand human language to perform tasks such as analyzing sentiment in text, translating text between languages, and generating coherent text responses. Deep learning models such as recurrent neural networks, transformers, and attention-based models have revolutionized NLP by capturing semantic relationships and contextual information in text data. Deep learning in medical imaging and diagnosis involves using deep neural networks to analyze medical images such as X-rays, MRIs, and CT scans for tasks like disease detection, diagnosis, and prognosis. Deep learning models can achieve high accuracy and efficiency in medical imaging tasks, aiding clinicians in diagnosing diseases such as cancer, cardiovascular disorders, and neurological conditions. In autonomous vehicles, deep learning models are applied for tasks like object detection, classification, and tracking to enable safe and efficient navigation in complex environments. Deep neural networks process sensor data from cameras, LiDAR, and radar to detect and recognize objects such as vehicles, pedestrians, and traffic signs, facilitating decision-making and control in autonomous driving systems. In finance, deep learning models are used for tasks such as fraud detection, stock prediction, algorithmic trading, and risk management. Deep neural networks analyze large-scale financial data, including market prices, trading volumes, and transaction histories, to identify patterns, trends, and anomalies, enabling applications such as fraud detection, market forecasting, and portfolio optimization in financial markets. Ethical considerations surrounding the use of deep learning in sensitive areas like surveillance and healthcare include concerns about privacy, fairness, accountability, and potential misuse of technology. In surveillance, for example, there are worries about mass surveillance infringing on individuals' rights to privacy and freedom. In healthcare, issues such as data security, patient confidentiality, and biased algorithms can impact patient outcomes and trust in the healthcare system. Biases in training data can affect the performance and fairness of deep learning models by perpetuating and amplifying existing biases present in the data. For example, biased training data may lead to biased predictions or decisions resulting in unfair treatment or discrimination against certain groups. To mitigate biases, it's crucial to ensure diverse and representative training data, perform bias audits, and employ techniques such as data augmentation, fairness-aware training, and bias mitigation algorithms. To ensure transparency and accountability, In deep learning algorithms, measures such as model interpretability, documentation, and validation are essential. Techniques like model explainability, sensitivity analysis, and uncertainty estimation can provide insights into how models make predictions and help stakeholders understand their behaviour. Additionally, documentation of model development, training procedures, and data sources can promote transparency and reproducibility, while rigorous validation and testing ensure model performance and safety. The potential risks of deploying deep learning systems without proper validation and testing include inaccurate predictions, biased decisions, privacy violations, and unintended consequences. Without thorough testing and validation, models may make erroneous predictions or decisions, leading to harm or adverse outcomes for individuals or society. It's crucial to conduct rigorous validation, testing, and ethical assessments before deploying deep learning systems in real-world applications to mitigate risks and ensure safety and fairness. Deep learning can be used to address societal challenges, such as climate change and poverty, by analysing large-scale data, identifying patterns, and generating insights to inform decision-making and policy interventions. For example, deep learning models can analyse satellite imagery to monitor deforestation, predict climate patterns, and assess environmental impacts. In poverty alleviation, deep learning can help analyse socioeconomic data, identify vulnerable populations, and inform targeted interventions and resource allocation strategies. Popular deep learning frameworks include TensorFlow, PyTorch, Keras, and MXNet, each with its unique features and strengths. TensorFlow and PyTorch are widely used open source frameworks for deep learning development, offering extensive support for building, training, and deploying deep neural networks. TensorFlow provides a comprehensive ecosystem with high-level APIs, distributed training, and production deployment capabilities, while PyTorch offers dynamic computation graphs, intuitive APIs, and a flexible imperative programming style. TensorFlow and PyTorch differ in terms of usability and performance, with TensorFlow known for its scalability, deployment, and production readiness, while PyTorch is favoured for its flexibility, ease of use, and developer-friendly interface. TensorFlow's static computation graphs offer advantages in performance optimization and deployment, whereas PyTorch's dynamic computation graphs enable intuitive model development and experimentation. High-level APIs like Keras provide simplified interfaces and abstractions for building and training deep learning models, allowing developers to focus on model design and experimentation without worrying about low-level implementation details. Keras serves as a user-friendly interface to TensorFlow and other back-end frameworks, offering a simple yet powerful API for rapid prototyping, experimentation, and model deployment. Resources and tutorials available for learning deep learning with Python include online courses, books, tutorials, and documentation from platforms such as Coursera, Udacity, Fast.ai, and official documentation from TensorFlow and PyTorch. These resources cover topics ranging from deep learning fundamentals and neural network architectures to advanced techniques, applications, and best practices in deep learning development. Recent advancements in deep learning research include innovations such as self-supervised learning and few-shot learning. Self-supervised learning leverages unlabeled data to pre-train models on auxiliary tasks, enabling them to learn meaningful representations without requiring annotated labels. Few-shot learning focuses on training models to generalize from a small number of examples by learning to adapt quickly to new tasks or classes with limited data. Researchers are exploring the integration of neuroscience principles into deep learning models to better understand biological intelligence and improve the performance of artificial intelligence systems. By incorporating concepts such as synaptic plasticity, attention mechanisms, and hierarchical processing, researchers aim to develop more efficient, flexible, and adaptive neural network architectures inspired by the brain's structure and function. Explainability plays a crucial role in improving the interpretability of deep learning models by providing insights into how models make predictions or decisions. Explainable AI techniques such as feature attribution methods, model visualization, and saliency maps help users understand the factors influencing model outputs, increasing trust, transparency, and accountability in AI systems. Neural architecture search is a technique for automatically discovering optimal neural network architectures tailored to specific tasks or constraints. Neural architecture search algorithms explore a search space of candidate architectures using techniques like reinforcement learning, evolutionary algorithms, or gradient-based optimization, aiming to find architectures that maximize performance while minimizing computational costs. Neural architecture search has implications for model design by automating the process of architecture engineering, enabling the creation of custom design networks optimized for various applications. Deep learning techniques are being applied to address challenges in areas like climate science and drug discovery by analyzing large-scale data, modeling complex relationships, and generating insights to inform decision-making and research. In climate science, deep learning models analyze satellite imagery, climate simulations, and environmental data to predict weather patterns, monitor climate change impacts, and enhance understanding of Earth systems. In drug discovery, deep learning accelerates drug design, virtual screening, and drug repurposing by predicting molecular properties, identifying potential drug candidates, and optimizing drug development pipelines. Common metrics used to evaluate the performance of deep learning models include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve. Accuracy measures the proportion of correctly classified instances, while precision measures the proportion of true positives among all predicted positives. Recall measures the proportion of true positives among all actual positives. And the F1 score combines precision and recall into a single metric. Receiver operating characteristic evaluates the trade-off between true positive rate and false positive rate across different classification thresholds, providing insights into the model's discriminative power and performance. Precision, recall, and F1 score differ in their emphasis on different aspects of classification performance. Precision focuses on minimizing false positives. Recall focuses on minimizing false negatives, and the F1 score balances precision and recall, making it suitable for imbalanced data sets, or when both false positives and false negatives are important. Cross-validation is a technique used to assess the performance of machine learning models. By splitting the data into multiple subsets, training the model on a subset of the data, and evaluating its performance on the remaining subset. Cross-validation helps estimate the model's generalization performance, detect overfitting, and optimize model hyperparameters by providing more reliable performance estimates than a single train test split. Confusion matrices are used to analyze the performance of classification models by summarizing the counts of true positive, true negative, false positive, and false negative predictions. Confusion matrices provide insights into the model's classification errors, such as misclassifications and confusion between different classes, helping diagnose model weaknesses and guide model improvement strategies. Considerations for deploying deep learning models in production environments include ensuring scalability, reliability, security, and efficiency. It's essential to optimize models for inference speed and memory footprint. Monitor model performance and drift over time, implement robust error handling and logging mechanisms, and adhere to privacy and regulatory requirements. Additionally, deploying models in production often involves integrating them with existing systems such as databases, APIs, or front-end applications, and establishing processes for model versioning, testing, and continuous integration and deployment. Model compression techniques like pruning and quantization improve the efficiency of deep learning models by reducing their size, computational complexity, and memory footprint. Pruning removes unimportant connections or neurons from the model, while quantization reduces the precision of model parameters, such as weights and activations, to lower bit width representations. These techniques enable faster inference, lower resource requirements, and deployment on resource-constrained devices like mobile phones or edge devices. Model serving is the process of deploying trained deep learning models to production environments and providing prediction or inference services to end users or applications. Model serving systems manage the deployment, scaling and monitoring of models, handle incoming requests, perform inference and return predictions or responses to clients. Model serving plays a critical role in deploying deep learning systems by ensuring models are available, scalable, and performant in production environments. Challenges associated with scaling deep learning. Model to large datasets or distributed environments include data preprocessing, augmentation, model parallelism, communication overhead, synchronization, and fault tolerance. Scaling deep learning models requires efficient data pipelines, distributed training frameworks, synchronization strategies, and hardware accelerators to handle the computational and memory requirements of training on large datasets across multiple nodes or GPUs. Containerization orchestration tools like Docker and Kubernetes are used to deploy deep learning applications by encapsulating models, dependencies, and runtime environments into portable containers and managing their deployment, scaling, and lifecycle across distributed clusters. Containers provide isolation, reproducibility, and consistency in deploying models, while orchestration tools automate deployment tasks, ensure availability, and optimize resource utilization in dynamic cloud-native environments. Common debugging techniques used during the development of deep learning models include visualizing model architectures, inspecting intermediate activations, gradients, and weights, monitoring training metrics, and analyzing prediction errors. Debugging tools such as integrated development environments, debuggers, and visualization libraries help developers diagnose issues, identify bugs, and optimize model performance during training and inference. Visualization tools like TensorBoard help diagnose issues in neural network training by providing interactive visualizations of training metrics, model architectures, and computational graphs. TensorBoard enables developers to monitor training progress, analyze model behavior, identify performance bottlenecks, and debug issues such as vanishing or exploding gradients, overfitting or underfitting. Strategies for identifying and addressing overfitting in deep learning models include collecting more data, using data augmentation techniques, applying regularization methods such as L1, L2 regularization, dropout, or batch normalization, reducing model complexity, and early stopping. Overfitting occurs when models learn to memorize training data instead of generalizing to unseen data, leading to poor performance on test or validation datasets. Gradient checking is used to verify the correctness of backpropagation implementations by comparing analytical gradients computed using backpropagation with numerical gradients computed using finite differences. Gradient checking helps ensure the correctness of the gradient computation process and identifies implementation errors or numerical instabilities that may affect model training. Strategies for diagnosing and mitigating issues related to vanishing or exploding gradients include gradient clipping, batch normalization, using appropriate activation functions, initializing model parameters properly, and using gradient normalization techniques such as gradient scaling or layer normalization. Vanishing gradients occur when gradients become too small during backpropagation, while exploding gradients occur when gradients become too large, leading to slow or unstable training. These strategies help stabilize training, improve convergence, and prevent numerical instabilities in deep learning models. Transfer learning is a technique in machine learning where a model trained on one task is leveraged to solve a different but related task. It involves using knowledge gained from solving one problem to help solve a different problem, typically by transferring learned features or representations from a pre-trained model to a new model. pre-trained language models like bidirectional encoder representations from Transformers and GP3, which is Generative Pre-trained Transformer 3, are large-scale neural network architectures trained on massive text corpora. They learn to understand and generate natural language by capturing semantic and syntactic patterns from the text data. Fine-tuning involves taking a pre-trained language model and adapting it to a specific natural language processing task, such as text classification or language generation, by updating the model parameters on a smaller task-specific dataset. Feature extraction in transfer learning refers to the process of extracting relevant features or representations from a pre-trained model for a new task. Fine-tuning, on the other hand, involves updating the parameters of the pre-trained model along with additional task-specific layers to adapt it to the new task. Feature extraction is commonly used when the new task is similar to the original task, while fine-tuning is preferred when the new task is sufficiently different or requires more adaptation. Common architectures used for transfer learning in computer vision tasks include convolutional neural networks such as very deep convolutional networks, ResNet and MobileNet. These architectures are pre-trained on large image datasets, like ImageNet, and learn to extract hierarchical features from images, which can be transferred and fine-tuned for various downstream tasks such as object detection and image classification. The choice of pre-trained model architecture can significantly affect the performance of fine-tuning. Different architectures may capture different levels of abstraction and semantic information from the data, leading to variations in performance depending on the specific characteristics of the task and dataset. Automated machine learning is a set of techniques and tools that automate various aspects of the machine learning pipeline, including data pre-processing, feature engineering, model selection, hyperparameter tuning, and model evaluation. AutoML streamlines the process of model development, reduces the need for manual intervention, and democratizes machine learning by making it accessible to users with varying levels of expertise. Automated machine learning techniques can be used to automate tasks such as feature engineering and model selection by automatically generating and evaluating a wide range of features and model architectures. This helps identify the most effective features and models for the given dataset and task, saving time and effort compared to manual experimentation. Hyperparameter optimization is the process of searching for the best set of hyperparameters for a machine learning algorithm to optimize its performance on a given dataset. Hyperparameters are parameters that are set before the learning process begins, such as learning rate, batch size, and network architecture. Hyperparameter optimization is important in deep learning because the choice of hyperparameters can significantly impact the performance and convergence of the model. Algorithms and approaches used for hyperparameter tuning include grid search, random search, Bayesian optimization, and evolutionary algorithms. These techniques systematically explore the hyperparameter space, evaluate the performance of different configurations, and iteratively refine the search to find the optimal set of hyperparameters. Interpretability is important in the context of deep learning models because it helps users understand how and why a model makes certain predictions or decisions. This is crucial for building trust, verifying model behavior, debugging errors, and identifying biases or unintended consequences in the model's outputs. Techniques for interpreting the predictions of black box models. Like deep neural networks include model-specific methods such as activation maximization, feature visualization, and layer-wise relevance propagation, as well as model-agnostic approaches like Shapley additive explanations values. Local interpretable model-agnostic explanations and permutation feature importance. Feature importance quantifies the contribution of each input feature to the model's predictions. For deep learning models, feature importance can be calculated using techniques such as gradient-based attribution methods, which measure how changes in input features affect model predictions by computing gradients with respect to the inputs. Techniques like saliency maps and gradient-based attribution visualize the sensitivity of model predictions to changes in input features by highlighting regions of the input space that have the greatest impact on the model's output. Saliency maps show the gradient of the model's output with respect to the input features, indicating which features are most influential for a given prediction. Challenges associated with achieving both high performance and interpretability in deep learning models include the complexity and nonlinearity of model architectures, the trade-off between model complexity and interpretability, and the potential for overfitting interpretability methods to specific datasets. Federated learning is a decentralized machine learning approach where model training is performed on distributed devices such as smartphones or IoT devices instead of a centralized server. Federated learning enables collaborative model training while keeping data localized on the devices, thereby addressing privacy concerns associated with centralized model training. Federated learning helps address privacy concerns by ensuring that sensitive data remains on users' devices and is not directly accessible by the central server. Only model updates, example gradients, are shared between the devices and the server, preserving the privacy of individual user data. Differential privacy is a framework for quantifying the privacy guarantees of data analysis algorithms. It ensures that the presence or absence of a single individual's data does not significantly affect the outcome of the analysis, thereby protecting individuals' privacy. In deep learning, differential privacy can be achieved through techniques such as adding noise to the training data or gradients during model training. Techniques for ensuring data privacy and confidentiality in federated learning settings include secure aggregation protocols, encryption techniques such as homomorphic encryption, and decentralized identity management systems. These techniques help protect the privacy of users' data and prevent unauthorized access to sensitive information during federated model training. Federated learning frameworks like TensorFlow Federated provide tools and libraries for implementing privacy-preserving machine learning models in federated settings. TensorFlow Federated abstracts away the complexities of federated learning, allowing developers to focus on building privacy-preserving models and deploying them in distributed environments. Model compression refers to techniques used to reduce the size and computational complexity of deep learning models, making them more efficient for deployment on resource-constrained devices such as smartphones, IoT devices, and embedded systems. It is important for deploying deep learning models in real-world applications, where memory processing power and energy consumption are limited. Techniques like pruning and quantization reduce the computational and memory requirements of deep learning models by removing redundant parameters and reducing the precision of model parameters, respectively. Pruning removes unimportant connections or neurons from the model, while quantization reduces the number of bits used to represent model parameters, leading to smaller memory footprints and faster inference speeds. Knowledge distillation is a process where a large, complex model, which is teacher model, transfers its knowledge to a smaller, simpler model, which is student model, by distilling the teacher model's predictions into a more compact representation. This helps compress the knowledge contained in the teacher model into a smaller model, reducing memory and computational requirements while maintaining performance. Challenges associated with compressing deep learning models while preserving their performance include balancing compression with performance trade-offs, avoiding significant drops in accuracy or generalization ability, ensuring compatibility with target deployment platforms, and managing the complexity of compression techniques and workflows. Frameworks like TensorFlow Lite and ONNX runtime support the deployment of compressed models on edge devices by providing optimized runtime environments and libraries for executing compressed models efficiently on various hardware platforms. They enable developers to deploy compressed models seamlessly on resource-constrained devices without sacrificing performance. Ethical considerations associated with the development and deployment of deep learning models include concerns about fairness, accountability, transparency, privacy, security, and bias. These considerations are important for ensuring that deep learning systems are developed and deployed responsibly and ethically, with consideration for their potential societal impacts and consequences. Biases in training data can lead to unfair or discriminatory outcomes in deep learning applications by perpetuating and amplifying biases present in the data. Biased training data can result in models that exhibit unfair or discriminatory behaviour, such as favouring certain demographic groups or perpetuating stereotypes. Algorithmic fairness is the principle of ensuring that machine learning models make decisions that are fair and unbiased across different demographic groups. It involves identifying and mitigating biases in training data, model design, and decision-making processes to ensure equitable outcomes for all individuals. Measures that can be taken to promote transparency. Accountability and fairness in deep learning systems include documenting data sources and pre-processing steps, evaluating models for bias and fairness, providing explanations for model predictions, and soliciting feedback from diverse stakeholders. Additionally, adopting transparent and ethical development practices, adhering to regulatory guidelines and standards, and fostering interdisciplinary collaboration can help promote responsible and ethical AI development. Frameworks like the Ethical AI Toolkit and Fairness indicators support the ethical development and evaluation of deep learning models by providing tools, guidelines, and resources for assessing and mitigating ethical risks and biases in AI systems. These frameworks help developers integrate ethical considerations into the AI development lifecycle and evaluate the fairness and transparency of AI models in real-world applications. Common challenges during training of deep learning models include overfitting, vanishing or exploding gradients, lack of labeled data, and computational resources. Techniques like regularization, dropout, batch normalization, and early stopping can help address overfitting. Gradient clipping, weight initialization strategies, and using different optimization algorithms can mitigate vanishing or exploding gradients. Data augmentation, transfer learning, and semi-supervised learning can alleviate the need for large labeled datasets. Utilizing cloud computing resources or distributed training frameworks can address computational limitation. Ensemble learning combines predictions from multiple individual models to improve overall performance. In deep learning, ensembles can be created by training multiple neural networks with different architectures, initializations, or training data. Combining diverse models helps capture complementary patterns in the data, reducing variance and improving generalization. Hyperparameters control the behavior and performance of the model during training. Unlike model parameters, which are learned from data example weights and biases, hyperparameters are set manually before training and include parameters like learning rate, batch size, and network architecture. Optimizing hyperparameters is crucial for achieving optimal model performance. Learning rate schedules adjust the learning rate during training to improve convergence and stability. Common schedules include step decay, exponential decay, and cyclic learning rates. Learning rate schedules help prevent the model from overshooting or getting stuck in local minima by adjusting the learning rate based on the training progress. Data augmentation involves applying transformations to the training data to increase its diversity and size, improving the model's ability to generalize to unseen examples. Common augmentations include rotation, translation, scaling, flipping, and adding noise. Data augmentation helps expose the model to different variations of the training data, making it more robust to variations in the test data. Transfer learning leverages knowledge from pre-trained models on large datasets to bootstrap the training of new models on smaller datasets or different tasks. By transferring learned features or representations, transfer learning accelerates training, reduces the need for large amounts of labeled data, and improves generalization. Imbalanced data sets pose challenges as models may become biased towards the majority class, leading to poor performance on minority classes. Techniques like class reweighting, data resampling example oversampling, undersampling, and generating synthetic samples can help address class imbalance, ensuring balanced representation during training. Multimodal deep learning models integrate information from different modalities, example, text, images, audio, to improve performance. Techniques like fusion layers, multitask learning, and attention mechanisms enable models to effectively process and combine information from diverse inputs, enhancing their understanding and performance across tasks. Adversarial examples are inputs deliberately crafted to cause misclassification or errors in deep learning models. They pose a challenge to model robustness and security. Defenses against adversarial attacks include adversarial training, robust optimization, and adversarial detection methods, which aim to make models more resilient to adversarial perturbations. Domain adaptation addresses the problem of domain shift, where the distribution of data in the training and test domains differs. By learning domain invariant features, domain adaptation enables models to generalize across domains, improving performance on unseen data. Techniques include adversarial domain adaptation, domain adversarial neural networks, and instance weighting methods. Autoencoders are unsupervised learning models that aim to learn efficient representations of input data by encoding it into a lower dimensional space and then reconstructing it from the encoded representation. They consist of an encoder network that compresses the input data into a latent space representation and a decoder network that reconstructs the input from this representation. Applications of autoencoders include data denoising, dimensionality reduction, anomaly detection, and generating new data samples. Attention mechanisms enable deep learning models to focus on relevant parts of the input data while performing tasks like machine translation, natural language processing, and image captioning. By dynamically weighting different parts of the input sequence, attention mechanisms improve the model's ability to capture long-range dependencies and context, leading to better performance in tasks requiring sequential or hierarchical processing. Graph neural networks extend traditional neural network architectures to handle graph-structured data, where nodes represent entities and edges represent relationships between them. Graph neural networks aggregate information from neighboring nodes and edges to generate node embeddings, capturing both local and global graph structure. They are used in tasks like social network analysis, recommendation systems, and molecular modeling. Self-supervised learning is a form of unsupervised learning where models learn to predict certain parts of the input data based on other parts of the same data. It leverages the inherent structure or redundancy in the data to create supervised learning signals without explicit labels. Self-supervised learning has advantages in training deep learning models with unlabeled data, as it enables models to learn useful representations without requiring manual annotation. Reinforcement learning is a type of machine learning where agents learn to make sequential decisions by interacting with an environment to maximize cumulative rewards. Unlike supervised learning, where models are trained on labeled data, and unsupervised learning, where models learn patterns in unlabeled data, reinforcement learning learns from feedback received as a result of actions taken in the environment. Deep Q-learning is a popular reinforcement learning algorithm that uses deep neural networks to approximate the action value function, enabling agents to learn complex decision-making policies. Ethical considerations surrounding the use of deep learning models for predictive policing and criminal justice systems include concerns about bias, fairness, accountability, transparency, and privacy. Deploying AI systems in law enforcement raises questions about the potential amplification of existing biases in the data, the fairness of algorithmic decisions, and the impact on individuals' rights and liberties. Deep learning techniques can be applied to address challenges in environmental monitoring And sustainability by analysing large-scale environmental data, modelling complex systems, optimising resource utilisation, and predicting environmental outcomes. Applications include climate modelling, natural disaster prediction, pollution monitoring, wildlife conservation, and sustainable agriculture. Interpretability in deep learning refers to the ability to understand and explain the decisions made by AI systems. It is important for building trust, transparency, and accountability in AI systems, especially in critical domains like healthcare, finance, and criminal justice. Interpretability techniques enable users to understand how models arrive at their predictions, diagnose model failures, detect biases, and ensure ethical and fair decision-making. Emerging trends in deep learning research include neurosymbolic AI, which integrates symbolic reasoning with neural network-based learning to enable more human-like reasoning and understanding, and meta-learning, which focuses on algorithms that can learn to learn by acquiring knowledge from previous tasks and experiences to adapt to new tasks more efficiently. These trends hold promise for advancing the capabilities and applications of deep learning in various domains. Limited memory-related artificial intelligence refers to AI systems designed to operate effectively with constrained memory resources. Unlike traditional AI models that may require large amounts of memory to store and process data, limited memory AI systems are optimized to work within specific memory constraints. These systems differ from traditional AI models, primarily in their approach to managing memory resources. While traditional models may prioritize accuracy and complexity, limited memory AI systems focus on efficiency and optimization to operate within memory limitations. The primary constraints faced by limited memory AI systems include restricted memory capacity, limited processing power, and the need to balance performance with resource usage. These constraints require careful optimization of algorithms, data structures, and model architectures. Optimization techniques commonly used to reduce memory usage in AI models include parameter sharing, model compression, data quantization, and efficient data storage and processing methods. These techniques help minimize memory footprint without significantly compromising performance. Designing limited memory AI systems involves trade-offs between memory usage, computational complexity, and performance. Developers must carefully balance these factors to create systems that meet application requirements while operating within memory constraints. Limited memory AI systems handle data storage and processing efficiently by employing algorithms and techniques optimized for resource-constrained environments. They may use specialized data structures, caching mechanisms, and streaming processing techniques to minimize memory usage and maximize performance. Common applications include edge computing, IoT devices, mobile applications, and embedded systems where memory resources are limited. These systems are often used in applications such as image and speech recognition, natural language processing, and predictive analytics. Model compression is a key concept in limited memory AI, involving techniques to reduce the size of AI models without significantly impacting performance. This may include pruning redundant parameters, quantizing model weights, or using compact architectures. Limited memory AI systems ensure acceptable performance despite memory constraints by optimizing algorithms and architectures for efficient resource usage. They may also employ dynamic memory management techniques to adapt to changing memory availability. Parameter sharing is a technique used to reduce memory usage by reusing parameters across different parts of the model. This helps minimize the number of parameters that need to be stored in memory, thus reducing memory footprint. Limited memory AI systems handle streaming data in real-time applications by processing data incrementally as it arrives, rather than storing and processing entire data sets at once. This allows them to operate efficiently in dynamic environments with continuous data streams. Deploying limited memory AI on resource-constrained devices presents challenges such as ensuring compatibility with hardware limitations, optimizing performance for specific platforms, and managing trade-offs between memory usage and functionality. Data quantization is a process used in limited memory AI to reduce memory usage by representing data using fewer bits. This allows for more efficient storage and processing of data while minimizing memory footprint. Techniques for optimizing memory usage. And deep learning models for edge computing include model distillation, weight pruning, and using lightweight architectures optimized for specific tasks and hardware platforms. Limited memory AI systems adapt to varying memory availability in dynamic environments by dynamically adjusting resource allocation, prioritizing critical tasks, and optimizing memory usage based on available resources and application requirements. Using shallow neural networks in limited memory applications offers several benefits. Shallow networks typically have fewer layers and parameters compared to deep networks, making them more memory efficient. They require less computational resources and can be trained faster, which is advantageous in resource-constrained environments. Additionally, shallow networks often generalize well to simple tasks and can achieve satisfactory performance with less memory, making them suitable for certain applications in limited memory AI systems. Dynamic model adaptation is a concept where models adjust their parameters and structures based on changing conditions or input data. In limited memory systems, dynamic adaptation allows models to adapt to varying memory availability, resource constraints, or evolving data distributions. This flexibility enables models to maintain performance and reliability in dynamic environments without exceeding memory limitations. In real-time processing, limited memory AI systems ensure data integrity and reliability by employing techniques such as error detection and correction, data validation, and redundancy. These systems also implement robust error handling mechanisms to mitigate data corruption or loss, ensuring accurate and reliable processing of data in real-time scenarios. Limited memory AI poses implications for privacy and data security, as sensitive information may be stored or processed within memory-constrained environments. To address these concerns, limited memory systems often employ encryption, access control mechanisms, and privacy-preserving techniques to safeguard sensitive data and protect user privacy. Handling scalability issues in large-scale deployments is a significant challenge for limited memory AI systems. These systems must efficiently scale to accommodate growing data sets, increasing computational demands, and expanding user bases while maintaining performance within memory constraints. Strategies such as distributed computing, parallel processing, and scalable architectures are used to address scalability challenges in large-scale deployments. Designing efficient data storage and retrieval mechanisms for limited memory AI involves optimizing data structures, compression techniques, and indexing methods to minimize memory usage and maximize retrieval efficiency. These mechanisms prioritize data access based on access patterns, data relevance, and memory availability to ensure efficient storage and retrieval operations. Data preprocessing plays a crucial role in reducing memory usage in models by transforming and optimizing input data before feeding it into the model. Techniques such as feature selection, dimensionality reduction, and data normalization help reduce the memory footprint of input data while preserving relevant information for model training and inference. Limited memory AI systems optimize memory allocation for different tasks or processes by dynamically managing memory resources based on task priorities, resource constraints, and performance requirements. These systems may employ memory pooling, caching, and memory recycling techniques to efficiently allocate and utilize memory resources across multiple tasks or processes. To mitigate performance degradation, In limited memory AI systems, strategies such as model optimization, algorithmic efficiency improvements, and resource utilization optimization are employed. These strategies focus on optimizing computational resources, minimizing memory usage, and maximizing performance within memory constraints to maintain acceptable system performance. Handling updates and modifications to model parameters. In limited memory AI systems involves techniques such as incremental learning, online learning, and transfer learning. These techniques allow models to adapt to changing data distributions, update model parameters efficiently, and incorporate new information without requiring extensive memory resources. Federated learning is a concept where models are trained across decentralized devices or servers without exchanging raw data. In limited memory, federated learning enables collaborative model training across distributed devices while preserving data privacy and minimizing memory usage. This approach is relevant to limited memory as it allows models to be trained on decentralized data sources without requiring centralized storage or processing. Prioritizing data storage and retrieval in limited memory AI systems involves techniques such as data caching, prefetching, and prioritization based on data relevance or access patterns. These techniques optimize data access and retrieval operations to minimize latency and maximize throughput, particularly in real-time or interactive applications. Ensuring compatibility with legacy systems and architectures is essential for limited memory AI systems to integrate seamlessly with existing infrastructure. These systems may employ interoperability standards, backward compatibility mechanisms, and middleware solutions to ensure compatibility with legacy systems while leveraging memory-constrained environments. Compression algorithms play a critical role in reducing memory usage in limited memory by compressing model parameters, intermediate representations, or input data. Techniques such as quantization pruning and Huffman coding help minimize memory footprint without significantly compromising model performance or accuracy. Limited memory has a significant impact on the development of edge computing solutions by enabling AI inference and processing on resource-constrained edge devices. These systems leverage limited memory resources efficiently to perform AI tasks locally, reducing latency, bandwidth requirements, and dependence on cloud-based processing, thus enabling edge computing applications in various domains. Limited memory AI systems manage asynchronous data streams in distributed environments by employing techniques such as event-driven processing, message queues, and distributed data processing frameworks. These systems process incoming data streams asynchronously, allowing them to handle varying data rates and arrival times across distributed nodes. Event-driven architectures enable limited memory AI systems to react to incoming data events dynamically, while message queues facilitate reliable data transfer and communication between distributed components. Additionally, distributed data processing frameworks like ApacheK or Apache Flink provide scalable and fault-tolerant mechanisms for processing asynchronous data streams in real time. Optimizing memory usage in natural language processing models involves several strategies tailored to the specific requirements of language processing tasks. Techniques such as word embedding compression, sparse matrix representations, and quantization of model parameters help reduce memory footprint while preserving model performance. Additionally, model distillation, where a smaller student model learns from a larger teacher model, can effectively transfer knowledge while reducing memory usage. Furthermore, pruning techniques, which remove redundant or less important parameters from NLP models, contribute to memory optimization without compromising task performance. Transfer learning is a machine learning technique where knowledge from a pre-trained model is transferred and adapted to a new task or domain. In limited memory, transfer learning is particularly relevant as it enables leveraging pre-trained models' knowledge to bootstrap learning in memory-constrained environments. By fine-tuning pre-trained models on target tasks with limited data, Limited memory AI systems can achieve better performance with less memory usage. Transfer learning facilitates efficient utilization of limited memory resources by reusing knowledge from pre-trained models, thereby reducing the need for extensive training data and computational resources. Limited memory AI systems ensure data consistency and accuracy in real-time processing through techniques such as data validation, error detection, and feedback mechanisms. These systems validate incoming data streams to identify and correct errors or inconsistencies, ensuring data quality before processing. Additionally, feedback mechanisms allow limited memory AI systems to refine model predictions or decisions based on real-time feedback, improving accuracy over time. By continuously monitoring and validating data streams, limited memory AI systems maintain data consistency and accuracy in dynamic real-time environments. The implications of limited memory AI for energy efficiency and sustainability are significant, as these systems prioritize resource efficiency and minimize energy consumption. By optimizing memory usage, limited memory systems reduce the computational resources required for processing, resulting in lower energy consumption and carbon footprint. Furthermore, the deployment of memory-efficient algorithms on resource-constrained edge devices enables localized processing, reducing the need for data transmission and central processing, thereby conserving energy and promoting sustainability. Fault tolerance and error recovery in real-time applications are essential considerations for limited memory systems to ensure reliability and robustness. These systems employ fault-tolerant architectures, redundant processing nodes, and error detection mechanisms to handle failures gracefully. Techniques such as checkpointing, replication, and automatic recovery enable limited memory systems to recover from faults or errors without compromising performance or data integrity. By implementing robust fault tolerance mechanism, limited memory AI systems maintain reliability and continuity in real-time applications. Model pruning is a technique used to reduce memory usage in AI systems by removing redundant or less important parameters from trained models. In limited memory, model pruning helps optimize memory usage without sacrificing model performance by identifying and pruning unnecessary connections or parameters. Limited memory systems can significantly reduce memory footprint while maintaining task performance. Pruning techniques include weight pruning, neuron pruning, and structured pruning, each targeting specific model components to achieve memory optimization. Reducing model complexity in limited memory AI systems involves techniques such as model simplification, feature engineering, and architecture optimization. These strategies aim to streamline model structures, reduce parameter counts, and simplify computations without compromising task performance. By simplifying model architectures and representations, limited memory AI systems can achieve better memory efficiency and faster inference speeds, making them suitable for resource-constrained environments. Limited memory AI systems handle data sparsity and imbalance in real-world datasets through techniques such as data augmentation, sampling strategies, and class balancing techniques. These systems address data sparsity by generating synthetic data samples, augmenting existing data, or applying oversampling and undersampling methods to balance class distributions. By pre-processing and augmenting data sets to address data sparsity and imbalance. Limited memory AI systems enhance model generalization and performance in real-world applications. Online learning is a machine learning paradigm where models are updated continuously as new data becomes available. In limited memory AI, online learning is relevant as it enables models to adapt dynamically to changing data distributions or incoming data streams. By updating model parameters incrementally and iteratively, limited memory AI systems can maintain model performance and adapt to evolving environments without requiring extensive memory resources. Online learning facilitates efficient utilization of limited memory by updating models in real time based on incoming data ensuring adaptability and responsiveness in dynamic scenarios. Streaming algorithms play a crucial role in optimizing memory usage in limited memory AI systems by processing data streams incrementally and efficiently. These algorithms enable real-time processing of data streams with limited memory resources by performing computations on the fly and discarding unnecessary data. By leveraging streaming algorithms such as reservoir sampling, count-min sketch, and sketching techniques, limited memory AI systems can process data streams in real time while minimizing memory usage and computational overhead. Streaming algorithms handle uncertainty and variability in streaming data by adapting dynamically to changing data distributions and incoming data patterns, ensuring efficient processing and accurate analysis in limited memory environments. Designing efficient memory management algorithms for limited memory involves addressing various challenges such as memory fragmentation, resource contention, and memory allocation overhead. These algorithms prioritize memory usage based on task requirements, memory availability, and system constraints to optimize memory allocation and utilization. Techniques such as memory pooling, garbage collection, and memory recycling are employed to manage memory efficiently and minimize overhead in limited memory environments. By implementing efficient memory management algorithms, limited memory systems maximize memory utilization while maintaining performance and reliability. Limited memory AI has a significant impact on the design of autonomous systems and robotics by enabling localized processing and decision-making on edge devices. These systems leverage limited memory resources efficiently to perform AI tasks locally, reducing latency, bandwidth requirements, and dependence on centralized processing. By deploying memory-efficient algorithms on edge devices, autonomous systems and robotics achieve faster response times, greater autonomy, and improved reliability, enabling applications in various domains such as autonomous vehicles, drones, and IoT devices. Privacy-preserving data sharing and collaboration in limited memory. AI systems involve techniques such as federated learning, secure multi-party computation, and differential privacy. These techniques enable collaborative model training across distributed nodes without compromising data privacy or confidentiality. By encrypting data, anonymizing user information, and implementing privacy-preserving algorithms, limited memory AI systems ensure secure and privacy-preserving data sharing and collaboration, facilitating collaborative learning and knowledge sharing while protecting sensitive information. Techniques for optimizing memory usage in computer vision models for edge devices include model compression, quantization, and sparsity regularization. Model compression techniques reduce the size of neural network models by removing redundant parameters or layers while preserving task performance. Quantization reduces the precision of model weights and activations, reducing memory requirements without significant loss in accuracy. Sparsity regularization encourages sparse representations in neural network models, reducing memory footprint by eliminating unnecessary activations or connections. Limited memory AI systems handle continuous learning and adaptation in dynamic environments by employing techniques such as incremental learning, transfer learning, and online learning. Incremental learning allows models to update gradually as new data becomes available, adapting to changing environments without retraining from scratch. Transfer learning leverages knowledge from pre-trained models to bootstrap learning in new tasks or domains, facilitating rapid adaptation with limited memory resources. Online learning updates model parameters iteratively based on incoming data, enabling real-time adaptation to dynamic environments while conserving memory resources. On-device processing refers to performing data processing and computation directly on edge devices, such as smartphones or IoT devices, without relying on centralized servers or cloud computing. On-device processing offers several advantages for limited memory, including reduced latency, increased privacy, and improved reliability. By processing data locally, limited memory AI systems minimize data transmission and storage requirements, enabling faster response times and reducing dependence on network connectivity. Additionally, on-device processing enhances data privacy and confidentiality by keeping sensitive information local, mitigating privacy risks associated with data transmission and storage. Lightweight algorithms play a crucial role in optimizing memory usage in limited memory AI systems by reducing computational complexity and memory requirements. These algorithms prioritize simplicity, efficiency, and resource efficiency, making them suitable for deployment in memory-constrained environments. Lightweight algorithms often employ techniques such as shallow networks, low-dimensional embeddings, and compact representations to minimize memory usage while maintaining task performance. By leveraging lightweight algorithms, limited memory systems achieve better memory efficiency and scalability, enabling deployment on resource-constrained edge devices. Limited memory AI systems handle data fusion and integration from multiple sources by employing techniques such as sensor fusion, feature fusion, and ensemble learning. Sensor fusion combines information from different sensors to generate more accurate and robust representations of the environment. Feature fusion integrates features extracted from multiple data sources to capture complementary information and enhance model performance. Ensemble learning aggregates predictions from multiple models to improve overall performance and reliability. By integrating data from multiple sources, limited memory AI systems enhance decision-making and adaptability in dynamic environments. Strategies for optimizing memory usage in reinforcement learning models include experience replay, parameter sharing, and model distillation. Experience replay stores past experiences in memory and replays them during training, enabling more efficient use of limited memory resources. Parameter sharing techniques reduce the number of learnable parameters by sharing weights across different parts of the model, reducing memory footprint without sacrificing task performance. Model distillation transfers knowledge from a larger, more complex model to a smaller, memory-efficient model, enabling efficient learning with limited memory resources. Limited memory has a significant impact on the development of smart cities and IoT ecosystems by enabling localized processing and decision-making on edge devices. These systems leverage limited memory resources efficiently to perform AI tasks locally, reducing latency, bandwidth requirements, and dependence on centralized processing. By deploying memory-efficient algorithms on edge devices, smart cities and IoT ecosystems achieve faster response times, greater autonomy, and improved reliability, enabling applications such as traffic management, environmental monitoring, and infrastructure optimization. Limited memory systems handle data pre-processing and feature extraction in real-time applications by employing lightweight algorithms and efficient data processing techniques. These systems prioritize real-time processing and low memory usage, often utilizing streaming algorithms, online learning, and incremental updates to pre-process and extract features from incoming data streams. By optimizing data pre-processing and feature extraction pipelines, limited memory AI systems enhance efficiency and responsiveness in real-time applications while conserving memory resources. Hardware accelerators play a crucial role in optimizing memory usage in limited memory systems by offloading computational tasks and accelerating model inference. These accelerators are optimized for parallel processing and matrix operations, enabling faster and more efficient execution of algorithms while reducing memory footprint. By leveraging hardware accelerators, limited memory systems achieve better performance and scalability, enabling deployment on resource-constrained edge devices and IoT platforms. Limited memory AI systems ensure data privacy and confidentiality in edge computing environments through techniques such as encryption, anonymization, and secure computation. These systems employ encryption algorithms to protect data during transmission and storage, ensuring confidentiality and integrity. Anonymization techniques anonymize user information and sensitive data to prevent identification, and tracking. Secure computation methods such as homomorphic encryption enable computation on encrypted data without revealing sensitive information, ensuring privacy-preserving data processing and collaboration in edge computing environments. Model distillation is a technique used to transfer knowledge from a larger, more complex model to a smaller, memory-efficient model. In limited memory AI, model distillation enables efficient learning and adaptation with constrained memory resources by compressing knowledge from pre-trained models into smaller, more lightweight models. By distilling knowledge from large models, limited memory systems can achieve comparable performance with reduced memory usage, enabling deployment on resource-constrained edge devices and IoT platforms. Techniques for optimizing memory usage in time series forecasting models include feature selection, dimensionality reduction, and model simplification. These techniques prioritize relevant features, reduce the dimensionality of input data, and simplify model structures to minimize memory requirements while maintaining forecasting accuracy. By selecting informative features, reducing data complexity, and streamlining model architectures, limited memory AI systems achieve better memory efficiency and scalability in time series forecasting applications. Limited memory AI systems handle model interpretation and explainability in real-time processing by employing techniques such as feature importance analysis, model visualization, and rule extraction. These systems prioritize transparency and interpretability by providing insights into model predictions and decision-making processes. Techniques such as feature importance analysis identify the most influential features on model predictions, while model visualization methods visualize model structures and decision boundaries. Rule extraction techniques extract human-readable rules from black box models, enhancing model interpretability and explainability in real-time applications. Reinforcement learning algorithms play a crucial role in optimizing memory usage in limited memory systems by enabling efficient exploration and learning in dynamic environments. These algorithms prioritize memory efficiency and scalability, often employing techniques such as value function approximation, policy gradient methods, and model-based reinforcement learning. By optimizing exploration-exploitation trade-offs and leveraging compact representations, limited memory AI systems achieve better memory efficiency and adaptation in reinforcement learning tasks. Limited memory systems handle data aggregation and summarization in distributed environments by employing techniques such as data fusion, summarization algorithms, and distributed computing. These systems aggregate and summarize information from multiple sources to generate concise representations of complex data streams. Summarization algorithms extract key insights and patterns from large data sets, reducing memory requirements while preserving essential information. Distributed computing frameworks such as MapReduce and Apache Spark enable parallel processing and distributed data processing, facilitating efficient data aggregation and summarization in limited memory systems. Limited memory AI significantly impacts the development of autonomous vehicles and drones by enabling onboard processing and decision-making with constrained memory resources. These systems prioritize memory efficiency to perform tasks such as navigation, obstacle avoidance, and object detection in real time. By optimizing memory usage, limited memory enhances the autonomy, responsiveness, and reliability of autonomous vehicles and drones, enabling safe and efficient operation in dynamic environments. Strategies for optimizing memory usage in anomaly detection models include feature selection, dimensionality reduction, and model simplification. These strategies prioritize relevant features, reduce data complexity, and streamline model structures to minimize memory requirements while maintaining detection accuracy. By selecting informative features and reducing model complexity, limited memory AI systems achieve better memory efficiency and scalability in anomaly detection tasks. Limited memory AI systems handle data quality assurance and validation in real-time processing by employing techniques such as data cleaning, outlier detection, and error correction. These systems prioritize data integrity and reliability by detecting and correcting errors, outliers, and inconsistencies in incoming data streams. By ensuring data quality and reliability, limited memory AI systems enhance the accuracy and robustness of real-time processing tasks. Automated machine learning techniques play a crucial role in optimizing memory usage in limited memory AI systems by automating the process of model selection, hyperparameter tuning, and architecture search. These techniques automatically explore and optimize model configurations to maximize performance while minimizing memory requirements. By leveraging automated machine learning, limited memory AI systems achieve better memory efficiency and scalability, enabling efficient deployment on resource-constrained edge devices and IoT platforms. Limited memory systems handle data redundancy and duplication in streaming environments by employing techniques such as data deduplication, compression, and filtering. These systems prioritize memory efficiency by removing redundant or duplicate data points, compressing data streams, and filtering out irrelevant information. By minimizing data redundancy and duplication, limited memory systems optimize memory usage and improve processing efficiency in streaming environments. Ensemble learning is a technique used to improve the performance and robustness of AI models by combining predictions from multiple base models. In limited memory AI, ensemble learning enhances model accuracy and reliability while minimizing memory usage by aggregating predictions from lightweight models. By leveraging ensemble learning, limited memory systems achieve better performance and scalability, enabling deployment on resource-constrained edge devices and IoT platforms. Techniques for optimizing memory usage in generative adversarial networks include model pruning, sparsity regularization, and parameter sharing. These techniques reduce model complexity and memory requirements while maintaining the ability to generate realistic and diverse samples. By optimizing memory usage, limited memory systems achieve better scalability and efficiency in generative tasks. Limited memory AI systems handle continuous monitoring and adaptation in dynamic systems by employing techniques such as adaptive learning, online updating, and incremental model refinement. These systems continuously update and adapt model parameters based on incoming data, enabling real-time adjustment to changing environments and conditions. By dynamically monitoring and adapting to changes, limited memory AI systems maintain performance and reliability in dynamic systems. Graph-based algorithms play a crucial role in optimizing memory usage in limited memory systems by representing data and relationships in compact graph structures. These algorithms prioritize memory efficiency by encoding data and connections in sparse matrices or graph representations, enabling efficient computation and storage. By leveraging graph-based algorithms, limited memory AI systems achieve better scalability and efficiency in tasks such as recommendation systems, social network analysis, and knowledge graphs. Limited memory AI significantly impacts the development of personalized healthcare solutions by enabling real-time analysis and decision-making with constrained memory resources. These systems prioritize memory efficiency to perform tasks such as patient monitoring, disease diagnosis, and treatment recommendation in personalized healthcare settings. By optimizing memory usage, limited memory enhances the accuracy, efficiency, and accessibility of personalized healthcare solutions, enabling better patient outcomes and healthcare delivery. Limited memory AI systems handle data storage and retrieval in resource-constrained environments by employing techniques such as data caching, indexing, and compression. These systems prioritize efficient data storage and retrieval by storing frequently accessed data in memory, indexing data for fast retrieval, and compressing data to minimize storage requirements. By optimizing data storage and retrieval, Limited memory AI systems enhance efficiency and responsiveness in resource-constrained environments. Strategies for optimizing memory usage in predictive maintenance models include feature engineering, model simplification, and data aggregation. These strategies prioritize relevant features, reduce model complexity, and aggregate data to minimize memory requirements while maintaining prediction accuracy. By optimizing memory usage, limited memory AI systems achieve better scalability and efficiency in predictive maintenance tasks. Limited memory AI systems handle data provenance and lineage tracking in distributed systems by recording metadata and lineage information for each data point or operation. These systems prioritize data integrity and traceability by tracking the origin, transformation, and usage of data throughout its lifecycle. By maintaining data provenance and lineage information, limited memory systems enhance transparency, reproducibility, and accountability in distributed data processing environments. Explainable AI techniques play a crucial role in optimizing memory usage in limited memory systems by providing insights into model predictions and decision-making processes. These techniques prioritize interpretability and transparency by explaining how these models arrive at their decisions and recommendations. By leveraging explainable AI, limited memory AI systems enhance trust, accountability, and usability, enabling better decision-making and deployment in real-world applications. Self-supervised learning is a technique used to train models using unlabeled data or auxiliary tasks. In limited memory, self-supervised learning enables efficient learning adaptation with constrained memory resources by leveraging unlabeled data to learn useful representations or features. By training on self-supervised tasks, limited memory AI systems can effectively utilize available data and optimize memory usage, enabling deployment on resource-constrained edge devices and IoT platforms. To optimize memory usage in recommendation systems, techniques like matrix factorization, hashing, and approximation methods can be employed. Matrix factorization reduces the dimensionality of user item matrices, while hashing techniques compress data representations. Approximation methods, such as low-rank approximations, enable efficient storage and computation without sacrificing recommendation accuracy. Limited memory AI systems ensure data synchronization and consistency in distributed environments through techniques like consensus algorithms and distributed locking mechanisms. Consensus algorithms ensure that distributed nodes agree on a consistent state, while distributed locking mechanisms prevent concurrent access to shared resources, maintaining data consistency across distributed systems. Meta-learning algorithms play a crucial role in optimizing memory usage in limited memory systems by learning to adapt model architectures and parameters based on past experiences. These algorithms enable efficient model adaptation and transfer learning, leveraging knowledge from previous tasks to optimize memory usage and improve performance in new tasks. Limited memory AI has a significant impact on the development of precision agriculture solutions by enabling real-time analysis and decision-making in resource-constrained environments. These systems prioritize memory efficiency to perform tasks such as crop monitoring, yield prediction, and irrigation management, enhancing productivity and sustainability in agriculture. Limited memory AI systems handle data imputation and missing value estimation in streaming data by employing techniques such as interpolation, extrapolation, and statistical modeling. These systems fill missing values in real-time data streams using historical information, statistical patterns, or predictive models, ensuring data completeness and reliability for downstream processing tasks. Strategies for optimizing memory usage in natural language understanding models include subword tokenization, pruning, and quantization. Subword tokenization reduces vocabulary size and memory requirements, while pruning techniques remove redundant or less informative model parameters. Quantization compresses model weights and activations, further reducing memory usage without significant loss in performance. Limited memory AI systems handle data pre-processing and feature engineering in real-time processing by employing techniques such as incremental learning, online feature extraction, and dimensionality reduction. These systems pre-process and extract features from streaming data on the fly, enabling efficient model inference and decision-making in dynamic environments. Knowledge distillation techniques play a crucial role in optimizing memory usage in limited memory systems by transferring knowledge from large, complex models to smaller, more memory-efficient models. These techniques distill knowledge from teacher models to student models through supervised learning, enabling compact representations and efficient memory usage while preserving model performance. Adversarial training is a technique used to improve the robustness and generalization of AI models by training them against adversarial examples. In limited memory AI, adversarial training enhances model resilience to memory-efficient attacks and perturbations, improving model reliability and performance in real-world scenarios. Techniques for optimizing memory usage in anomaly detection models include feature selection, dimensionality reduction, and model simplification. These techniques prioritize relevant features, reduce data complexity, and streamline model structures to minimize memory requirements while maintaining detection accuracy. Limited memory AI systems handle data fusion and integration from multiple sources by employing techniques such as data alignment, fusion rules, and consensus algorithms. These systems reconcile data from diverse sources, aligning timestamps and merging information to generate unified representations, ensuring comprehensive and accurate data integration for decision-making. Limited memory has a significant impact on the development of smart cities and IoT ecosystems by enabling real-time monitoring, analysis, and control of urban infrastructure and connected devices. These systems optimize memory usage to process vast amounts of sensor data, extract actionable insights, and facilitate data-driven decision-making for urban management and services. Limited memory AI systems handle data pre-processing and feature extraction in real-time applications by employing lightweight algorithms, streaming processing techniques, and online learning methods. These systems pre-process and extract features from streaming data on the fly, enabling efficient model inference and decision-making in dynamic environments. Hardware accelerators play a crucial role in optimizing memory usage in limited memory AI systems by offloading computation-intensive tasks to specialized hardware devices. These accelerators prioritize memory efficiency and performance, enabling faster and more energy-efficient execution of AI algorithms on edge devices and IoT platforms. Limited memory AI systems ensure data privacy and confidentiality in edge computing environments through techniques like data encryption, secure transmission protocols, and access control mechanisms. These systems encrypt sensitive data to prevent unauthorized access, use secure communication channels to transmit data securely between edge devices and central servers, and implement access control policies to restrict data access to authorized users or applications, safeguarding data privacy and confidentiality in edge computing environments. Model distillation is a process where knowledge is transferred from a complex, large model, which is teacher model, to a simpler, more memory-efficient model, which is student model. In limited memory, model distillation reduces the memory footprint of AI models by distilling knowledge from large, resource-intensive models to smaller, more memory-efficient ones while preserving performance and accuracy. This enables efficient deployment of AI models on resource-constrained devices and platforms, enhancing scalability and usability in real-world applications. Techniques for optimizing memory usage in time series forecasting models include feature selection, dimensionality reduction, and model simplification. Feature selection prioritizes relevant input features, reducing the dimensionality of the input space and memory requirements. Dimensionality reduction techniques like principal component analysis or autoencode compressed data, representations, further reducing memory usage. Model simplification streamlines model structures, reducing the number of parameters and memory overhead while maintaining forecasting accuracy. Limited memory AI systems handle model interpretation and explainability in real-time processing through techniques like feature importance analysis, attention mechanisms, and model visualization. These systems identify and highlight influential features, attention weights, or decision factors to explain model predictions and behaviours, enhancing transparency and trustworthiness in real-time AI applications. Reinforcement learning algorithms play a crucial role in optimizing memory usage in limited memory AI systems by learning efficient policies and strategies through trial and error interactions with the environment. These algorithms prioritize memory-efficient actions and state representations, enabling adaptive learning and decision-making in resource-constrained environments, such as edge devices or embedded systems. Limited memory AI has a significant impact on the development of autonomous vehicles and drones by enabling real-time perception, decision-making, and control in dynamic environments. These systems optimize memory usage to process sensor data, analyze surroundings, and plan optimal trajectories, enhancing safety, efficiency, and autonomy in transportation and surveillance applications. Limited memory AI systems handle data aggregation and summarization in distributed environments through techniques like data partitioning, aggregation functions, and sampling methods. These systems partition data into manageable chunks, aggregate information using functions like mean or median, and sample representative subsets to summarize distributed data efficiently, facilitating collaborative processing and analysis in distributed AI systems. Strategies for optimizing memory usage in anomaly detection models include feature selection, outlier removal, and model compression. Feature selection prioritizes relevant features for anomaly detection, reducing memory requirements. Outlier removal techniques identify and remove noisy or irrelevant data points, further reducing memory overhead. Model compression methods compress model parameters and representations, minimizing memory usage while maintaining detection accuracy. Limited memory AI systems handle data quality assurance and validation in real-time processing through techniques like data cleansing, validation checks, and anomaly detection. These systems pre-process data to remove errors or inconsistencies, perform validation checks to ensure data integrity, and employ anomaly detection algorithms to identify and correct data anomalies in real time, ensuring high data quality for downstream processing tasks. Automated machine learning techniques play a crucial role in optimizing memory usage in limited memory AI systems by automating model selection, hyperparameter tuning, and architecture search processes. These techniques leverage automated algorithms to search and optimize model configurations, enabling efficient memory usage and improving model performance without manual intervention, streamlining the development and deployment of AI systems in resource-constrained environments. Ensemble learning is a machine learning technique where multiple models are combined to improve predictive performance. In limited memory AI, ensemble learning enhances model robustness and generalization by aggregating predictions from diverse models, reducing overfitting, and improving memory efficiency. This enables more accurate and reliable predictions in resource-constrained environments, enhancing the effectiveness of AI systems in real-world applications. Techniques for optimizing memory usage in generative adversarial networks include model pruning, distillation, and quantization. Model pruning removes redundant or less informative components from generative adversarial network architectures, reducing memory overhead. Distillation techniques transfer knowledge from large generative adversarial networks to smaller, more memory-efficient models, preserving generative capabilities. Quantization compresses model weights and activations, further reducing memory usage while maintaining generative adversarial network performance. Limited memory AI systems handle continuous monitoring and adaptation in dynamic systems through techniques like incremental learning, online updating, and adaptive algorithms. These systems update models and adapt parameters in real time, incorporating new data, and environmental changes to maintain model performance and accuracy over time, ensuring responsiveness and adaptability in dynamic environments. Limited memory AI systems handle data storage and retrieval in resource-constrained environments by prioritizing essential data, implementing efficient data structures, and leveraging compression techniques. These systems store critical data while minimizing redundant or non-essential information, ensuring optimal memory utilization. They utilize lightweight data structures optimized for memory efficiency, such as hash tables or binary trees, enabling fast and efficient data retrieval. Additionally, they employ data compression methods like run-length encoding or dictionary compression to further reduce memory footprint while preserving data integrity. Strategies for optimizing memory usage in predictive maintenance models include feature selection, model simplification, and online learning. These models prioritize relevant features essential for predicting equipment failures while discarding redundant or less informative ones. Reducing memory requirements, model simplification techniques streamline model structures, reducing the number of parameters and memory overhead. Furthermore, online learning algorithms enable continuous model updating adaptation to evolving data patterns, ensuring efficient memory usage while maintaining predictive accuracy. Explainable AI techniques play a crucial role in optimizing memory usage in limited memory AI systems by providing insights into model behaviors and decisions. These techniques enable interpretable model representations, allowing users to understand and analyze memory usage patterns. They highlight influential features, attention mechanisms, or decision factors, enabling users to identify memory-intensive components and optimize model structures accordingly. Furthermore, explainable AI techniques facilitate model debugging and optimization, improving memory efficiency and overall performance in limited memory AI systems. Self-supervised learning is a machine learning paradigm where models learn from unlabeled data without explicit supervision. In limited memory AI, self-supervised learning reduces memory usage by leveraging data-driven learning objectives to train compact, memory-efficient models. These models learn meaningful representations from unlabeled data, enabling efficient memory utilization without relying on large labeled data sets. Self-supervised learning is particularly relevant in limited memory applications where labeled data is scarce or costly to obtain, allowing models to learn from abundant unlabeled data sources. Techniques for optimizing memory usage in recommendation systems include matrix factorization, hashing, and model distillation. These techniques reduce memory overhead by representing user item interactions as compact embeddings or hashes, enabling efficient storage and retrieval of recommendation data. Matrix factorization methods decompose user item interaction matrices into low-rank representations, reducing memory requirements while preserving recommendation accuracy. Hashing techniques map high-dimensional feature vectors to compact hash codes, further reducing memory footprint in recommendation systems. Additionally, model distillation transfers knowledge from complex recommendation models to smaller, more memory-efficient ones, enhancing scalability and usability in limited memory environments. Limited memory AI systems handle data synchronization and consistency in distributed environments through techniques like distributed consensus protocols, conflict resolution mechanisms, and version control systems. These systems ensure data consistency by coordinating data updates and propagating changes across distributed nodes using consensus algorithms like Paxos or Raft. They resolve conflicts arising from concurrent data modifications through conflict resolution mechanisms, such as timestamp-based ordering or conflict resolution policies. Furthermore, They utilize version control systems to track and manage data revisions, ensuring consistency and integrity in distributed data repositories. Limited memory AI systems handle data imputation and missing value estimation in streaming data through techniques like interpolation, extrapolation, and predictive modeling. These systems infer missing values by interpolating or extrapolating neighboring data points. In time series streams, preserving temporal patterns and trends. They also employ predictive modeling approaches, such as regression or classification algorithms, to estimate missing values based on available data features and contextual information, ensuring data completeness and reliability in real-time processing tasks. Strategies for optimizing memory usage in natural language understanding models include word embedding compression, subword tokenization, and model distillation. These strategies reduce memory overhead by compressing word embeddings or subword representations, enabling efficient storage and processing of textual data. They also distill knowledge from large language models to smaller, more memory-efficient ones, preserving semantic understanding and language comprehension capabilities. Additionally, they employ lightweight tokenization techniques to represent words or phrases with compact subword units, further reducing memory footprint in natural language processing tasks. Limited memory AI systems handle data pre-processing and feature engineering in real-time processing through techniques like incremental learning, feature selection, and online feature extraction. These systems incrementally update data pre-processing pipelines and feature extraction algorithms, enabling adaptive processing and model refinement in dynamic environments. They prioritize relevant features for real-time analysis using feature selection methods, reducing memory requirements and computational complexity. Furthermore, they employ online feature extraction techniques to generate informative features from streaming data, ensuring efficient memory usage and accurate real-time predictions. Knowledge distillation techniques play a crucial role in optimizing memory usage in limited memory AI systems by transferring knowledge from large, complex models to smaller, more memory-efficient ones. These techniques distill knowledge from teacher models to student models by minimizing the discrepancy between their predictions or representations, enabling compact model representations with reduced memory overhead. Knowledge distillation facilitates efficient deployment of AI models on resource-constrained devices and platforms, enhancing scalability and usability in real-world applications. Adversarial training is a machine learning technique where models are trained against adversarial examples to improve robustness and generalization. In limited memory AI, adversarial training enhances model resilience to memory-intensive attacks or perturbations by adversarial adversaries. These attacks aim to exploit vulnerabilities in AI models and consume excessive memory resources, compromising model performance and integrity. Adversarial training defends against such attacks by augmenting training data with adversarial examples, enabling models to learn robust representations and mitigate memory-related vulnerabilities. Techniques for optimizing memory usage in anomaly detection models include feature selection, model simplification, and adaptive learning. These techniques reduce memory overhead by prioritizing relevant features essential for detecting anomalies while discarding redundant or irrelevant ones. Model simplification methods streamline model architectures, reducing the number of parameters and memory requirements. Additionally, adaptive learning algorithms enable models to dynamically adjust to evolving data patterns, ensuring efficient memory usage and accurate anomaly detection in resource-constrained environments. Artificial general intelligence refers to a hypothetical form of artificial intelligence that possesses the ability to understand, learn, and apply knowledge across a wide range of tasks and domains, similar to human intelligence. Artificial general intelligence differs from narrow artificial intelligence in that narrow AI is designed to perform specific tasks or solve specific problems within a limited domain, whereas artificial general intelligence aims to exhibit general intelligence comparable to humans, capable of performing diverse tasks across different domains. The primary goals of artificial general intelligence research include creating machines that can reason, learn, plan, and perceive their environment in a manner that mirrors human-like intelligence. Researchers seek to develop AI systems that exhibit adaptability, flexibility, and autonomy across a broad spectrum of tasks. In the context of artificial general intelligence, human-level intelligence refers to the ability of AI systems to perform tasks and solve problems with a level of proficiency comparable to that of humans. This includes capabilities such as understanding natural language, recognizing patterns, making complex decisions, and exhibiting creativity. Key challenges in developing artificial general intelligence include understanding and replicating complex cognitive processes, integrating multiple forms of intelligence, ensuring ethical and responsible artificial intelligence development, and addressing concerns related to safety and control. Researchers approach the problem of replicating human intelligence in machines by studying cognitive science, psychology, neuroscience, and other disciplines to gain insights into the underlying principles of human cognition. They also develop artificial intelligence algorithms and architectures inspired by human cognitive processes. Ethical considerations surrounding the development of artificial general intelligence include concerns about artificial intelligence safety, privacy, bias, job displacement, and the potential for misuse or unintended consequences. It is essential to ensure that artificial general intelligence systems are developed and deployed responsibly to minimize harm and maximize societal benefits. Artificial general intelligence may impact the job market and employment landscape by automating repetitive tasks, creating new job opportunities in artificial intelligence development and related fields, and transforming industries through increased efficiency and productivity. Artificial general intelligence systems are not currently capable of experiencing consciousness or self-awareness as humans do. While they may exhibit advanced cognitive abilities, they lack subjective experience or awareness of their own existence. Neuroscience plays a role in understanding artificial general intelligence by providing insights into the structure and function of the human brain, which can inform the design and development of artificial intelligence algorithms and architectures that mimic biological intelligence. Artificial general intelligence systems learn and acquire new knowledge through techniques such as machine learning, deep learning, reinforcement learning, and symbolic reasoning. They analyze data, extract patterns, and adjust their behavior based on feedback and experience. Potential applications of artificial general intelligence span various industries, including healthcare, finance, education, transportation, and entertainment. Artificial general intelligence systems could revolutionize medical diagnosis, financial forecasting, personalized learning, autonomous vehicles, and content generation, among other areas. Artificial general intelligence systems handle uncertainty and ambiguity in tasks by probabilistic reasoning, uncertainty quantification, and adaptive decision-making strategies. They incorporate uncertainty into their models and algorithms to make informed decisions in uncertain or ambiguous situations. Safeguards to prevent artificial general intelligence from causing harm include robust artificial intelligence governance frameworks, transparency and accountability measures, artificial intelligence safety research, and the development of value-aligned artificial intelligence systems. These efforts aim to mitigate risks and ensure the responsible development and deployment of artificial general intelligence. While artificial general intelligence systems may exhibit creativity and innovation in problem solving and task performance, the extent to which they can genuinely emulate human-like creativity remains a subject of ongoing research and debate. Artificial general intelligence systems may generate novel ideas, solutions, or artifacts, but whether they can truly exhibit human-like creativity is still an open question. Artificial general intelligence systems perceive and interpret their environment through various sensors, such as cameras, microphones, or sensors that detect physical properties. They analyze incoming data using algorithms and models to understand their surroundings, recognize objects, and infer relationships between different elements in the environment. Limitations of current artificial general intelligence technologies include challenges in replicating complex human-like cognitive abilities, such as common sense reasoning, intuition, and creativity. Current artificial general intelligence systems also struggle with handling ambiguity, uncertainty, and context-dependent tasks that humans perform effortlessly. Artificial general intelligence systems handle ethical dilemmas and moral reasoning through ethical artificial intelligence frameworks and principles. They may be programmed with rules, guidelines, or ethical constraints to make decisions aligned with ethical principles and values, although implementing moral reasoning in artificial intelligence remains a complex challenge. Artificial general intelligence systems can understand and generate natural language through techniques like natural language processing, machine translation, and dialogue systems. Recent advancements in deep learning and language models have significantly improved the capabilities of artificial intelligence systems in understanding and generating human-like language. Recent advancements in artificial general intelligence research include breakthroughs in deep learning, reinforcement learning, and neural network architectures. Researchers are also exploring hybrid artificial intelligence approaches that combine symbolic reasoning with statistical learning, as well as techniques for lifelong learning and continual adaptation. Artificial general intelligence systems adapt to changing environments through techniques like reinforcement learning, which enables them to learn from feedback and adjust their behavior accordingly. They may also employ adaptive algorithms and self-learning mechanisms to continuously improve their performance over time. The implications of artificial general intelligence for privacy and data security include concerns about unauthorized access to sensitive information, data breaches, and surveillance. Safeguards such as data encryption, access control, and privacy-preserving techniques are essential to protect individuals' privacy and data security in the age of artificial general intelligence. Artificial general intelligence systems handle social interactions and relationships through techniques like effective computing, social signal processing, and human-robot interaction. They may be programmed with social norms, etiquette, and empathy to facilitate natural and meaningful interactions with humans. Ethical frameworks guiding the development and deployment of artificial general intelligence include principles like transparency, accountability, fairness, and human-centered design. These frameworks aim to ensure that artificial intelligence technologies are developed and used responsibly, with consideration for their societal impact and ethical implications. Artificial general intelligence systems do not experience emotions or empathy in the same way humans do, as they lack subjective consciousness and subjective experiences. However, they may simulate emotions or empathy through effective computing techniques or respond to emotional cues based on programmed rules or algorithms. Reinforcement learning plays a significant role in artificial general intelligence development by enabling agents to learn optimal behaviors through trial and error based on feedback from their environment. It allows artificial general intelligence systems to adapt to complex and dynamic environments, improving their performance over time. Artificial general intelligence systems integrate information from multiple sources through techniques like multimodal learning, fusion of heterogeneous data sources, and knowledge integration from various domains. They analyze and synthesize information from different modalities to make informed decisions and predictions. Risks associated with the proliferation of artificial general intelligence technology include concerns about job displacement, economic inequality, autonomous weapon systems, and loss of human control over intelligent systems. It is crucial to address these risks through robust governance, regulation, and ethical guidelines. Artificial general intelligence systems address the trade-off between exploration and exploitation in reinforcement learning by balancing between exploring new actions or strategies and exploiting known information to maximize rewards. They employ exploration strategies to discover new possibilities while leveraging existing knowledge to achieve goals efficiently. Artificial general intelligence systems can engage in meta-level reasoning and self-improvement through techniques like meta-learning, self-supervised learning, and model-based optimization. They may learn to learn, adapt their learning strategies, and improve their performance through iterative cycles of learning and optimization. Artificial general intelligence could potentially lead to job displacement as it becomes capable of performing a wide range of tasks currently done by humans. Workforce retraining programs will be crucial to help individuals transition to new roles and industries where human skills complement artificial general intelligence capabilities. Artificial general intelligence systems have the potential to autonomously acquire new skills and knowledge through techniques like reinforcement learning, self-supervised learning, and continual learning. They can learn from experience, adapt to new environments, and improve their performance over time without explicit human intervention. Artificial general intelligence systems handle uncertainty in decision-making by employing probabilistic reasoning, uncertainty quantification, and adaptive strategies. They incorporate uncertainty estimates into their models to make informed decisions and adjust their behavior based on feedback and changing circumstances. Neurosymbolic artificial intelligence integrates symbolic reasoning with neural network-based approaches, combining the strengths of both paradigms to advance artificial general intelligence research. It enables artificial intelligence systems to reason abstractly, understand complex relationships, and learn from structured and unstructured data simultaneously. Artificial general intelligence systems handle common sense reasoning and understanding through knowledge representation, reasoning algorithms, and learning from large-scale data. They may use knowledge graphs, ontologies, or semantic models to capture and reason about common sense knowledge. Measures to ensure alignment of artificial general intelligence systems with human values include value alignment research, ethical artificial intelligence frameworks, and human-in-the-loop artificial intelligence systems. These approaches aim to develop artificial intelligence technologies that prioritize human well-being, fairness, transparency, and accountability. Artificial general intelligence systems can collaborate effectively with humans and other artificial intelligence systems through techniques like multi-agent systems, coordination mechanisms, and human-artificial intelligence interaction interfaces. They can complement human expertise, share tasks, and achieve common goals in collaborative environment. Artificial general intelligence systems handle incomplete or ambiguous information by employing techniques like uncertainty modeling, inference algorithms, and context-aware reasoning. They use probabilistic reasoning and adaptive strategies to make decisions despite uncertainty or ambiguity. The implications of artificial general intelligence for global geopolitics and security include concerns about artificial intelligence arms race, autonomous weapons proliferation, and economic competitiveness. It is essential to address these implications through international cooperation, artificial intelligence governance frameworks, and responsible artificial intelligence development. Artificial general intelligence systems address the challenge of exploration and exploitation in reinforcement learning by balancing between exploring new strategies and exploiting known information to maximize rewards. They use exploration strategies to discover new possibilities while leveraging existing knowledge to achieve goals efficiently. Artificial general intelligence systems can engage in meta-level reasoning and strategic thinking by reasoning about their own reasoning processes, planning future actions, and optimizing their own performance. They can learn to adapt their strategies, anticipate outcomes, and make decisions at a high level of abstraction. Potential risks associated with the misuse of artificial general intelligence technology include autonomous weapons development, artificial intelligence-enabled surveillance, and societal disruption. It is crucial to mitigate these risks through artificial intelligence governance, regulation, and ethical guidelines to ensure safe and beneficial deployment of artificial general intelligence. Artificial general intelligence systems handle adversarial attacks and security threats through techniques like robust optimization, adversarial training, and anomaly detection. They can detect and mitigate attacks by learning robust representations, detecting anomalies, and adapting their behavior to adversarial environments. Artificial general intelligence systems can understand and interpret human emotions accurately through effective computing techniques, emotion recognition algorithms, and natural language processing. They analyze facial expressions, vocal cues, and textual content to infer emotional states and respond appropriately. Transfer learning plays a crucial role in artificial general intelligence systems by enabling knowledge transfer between different tasks, domains, or environments. It allows artificial intelligence systems to leverage knowledge learned from one context to improve performance in another, accelerating learning and adaptation processes. Artificial general intelligence systems handle feedback and learning from experience by analyzing incoming data, evaluating outcomes, and adjusting their behavior based on feedback signals. They use techniques like reinforcement learning, supervised learning, and unsupervised learning to learn from interactions with the environment and improve their performance over time. Measures to ensure the safety and reliability of artificial general intelligence systems include rigorous testing, validation procedures, and fail-safe mechanisms. Researchers also develop ethical guidelines, regulatory frameworks, and artificial intelligence safety protocols to minimize risks and ensure responsible deployment of artificial general intelligence technologies. Artificial general intelligence systems can exhibit common sense knowledge and reasoning by leveraging large-scale data, semantic models, and reasoning algorithms. They can understand everyday concepts, infer implicit knowledge, and apply common sense reasoning to solve problems in diverse domains. These systems address the challenge of lifelong learning by employing continual learning techniques, adaptive algorithms, and knowledge consolidation mechanisms. These systems address the challenge of lifelong learning by employing continual learning techniques, adaptive algorithms, and knowledge consolidation mechanisms. They can accumulate knowledge over time, update their models with new data, and adapt to changing environments without forgetting previous experiences. The implications of artificial general intelligence for human-machine collaboration and teamwork include opportunities for automation, task delegation, and complementary skills. Artificial general intelligence systems can augment human capabilities, share tasks, and achieve common goals in collaborative settings, leading to increased efficiency and productivity. Artificial general intelligence systems can exhibit meta-level reasoning and strategic planning by reasoning about their own reasoning processes, setting goals, and planning future actions. They can anticipate outcomes, consider alternative strategies, and make decisions at a higher level of abstraction. Artificial general intelligence systems address the challenge of model generalization to new domains by leveraging transfer learning, domain adaptation, and meta-learning techniques. They can transfer knowledge learned from one domain to another, adapt their models to new environments, and generalize their capabilities across diverse tasks. Artificial general intelligence systems can exhibit bounded rationality, like humans, by making decisions based on limited information, cognitive biases, and heuristics. They prioritize important information, simplify complex problems, and make decisions that are satisfactory rather than optimal. Artificial general intelligence systems handle ethical dilemmas with conflicting stakeholder interests by incorporating ethical principles, value alignment mechanisms, and stakeholder engagement processes into their decision-making frameworks. They aim to balance competing interests and minimize harm, while maximizing societal benefit. Social psychology plays a role in understanding human-artificial general intelligence interactions by studying human behaviour, cognition, and social dynamics in artificial intelligence-mediated environments. It informs the design of artificial intelligence interfaces, interaction protocols, and collaborative systems to promote effective communication and cooperation between humans and artificial general intelligence systems. Artificial general intelligence systems handle the challenge of real-time decision-making under uncertainty by employing adaptive algorithms, probabilistic reasoning, and decision-making heuristics. They analyze available information, estimate uncertainty, and make decisions that balance exploration and exploitation in dynamic environments. Artificial general intelligence systems can exhibit adaptive behaviour in response to changing environments by monitoring changes, updating their models, and adjusting their strategies accordingly. They can learn from experience, anticipate changes, and adapt their behaviour to achieve desired outcomes in evolving contexts. Measures to ensure the fairness and equity of artificial general intelligence systems in decision-making include fairness-aware algorithms, bias detection techniques, and diversity-aware training data. Researchers also advocate for transparency, accountability, and fairness principles in artificial intelligence development and deployment. Artificial general intelligence systems handle the challenge of interpretability and transparency in complex models by employing model explanation techniques, interpretability metrics, and transparency standards. They aim to provide users with insights into model behaviour, decision-making processes, and underlying reasoning to foster trust and understanding. Artificial general intelligence systems can exhibit self-regulation and self-control by incorporating self-monitoring mechanisms, goal-setting algorithms, and decision-making constraints into their architectures. They can regulate their behaviour, prioritise goals, and maintain consistency in achieving desired outcomes. Artificial general intelligence systems handle the challenge of transfer learning in dynamic environments by leveraging knowledge learned from one task or domain to improve performance in another. They adapt their models, update their representations, and transfer relevant knowledge across tasks or environments to facilitate learning adaptation. Symbolic reasoning plays a crucial role in artificial general intelligence systems by enabling abstract, rule-based reasoning and logical inference. It allows artificial intelligence systems to manipulate symbols, represent knowledge, and perform complex reasoning tasks similar to human cognition. Artificial general intelligence systems address the challenge of model scalability to handle large data sets by employing distributed computing frameworks, parallel processing techniques, and scalable algorithms. They partition data, distribute computations, and optimize algorithms to scale efficiently with increasing data volumes. Artificial general intelligence systems can exhibit adaptive behaviour in response to feedback and reinforcement by learning from experience, adjusting their strategies, and improving their performance over time. They use reinforcement learning, adaptive algorithms, and feedback mechanisms to adapt to changing environments and optimise outcomes. Measures to ensure the safety and security of artificial general intelligence systems from malicious attacks include robust cybersecurity protocols, secure development practices, and artificial intelligence safety research. Researchers also explore techniques like adversarial training, anomaly detection, and secure multi-party computation to mitigate risks and vulnerabilities. Artificial general intelligence systems handle the challenge of integrating diverse sources of knowledge through techniques like knowledge graphs, ontologies, and semantic models. They aggregate information from various sources, resolve inconsistencies, and synthesize knowledge to build comprehensive models of the world. Linguistics plays a role in understanding human-like language, understanding in artificial general intelligence by studying language structure, semantics, and pragmatics. It informs the design of natural language processing algorithms, dialogue systems, and language models that enable artificial intelligence systems to understand and generate human-like language. Artificial general intelligence systems can exhibit metacognitive abilities, like introspection and self-awareness by reasoning about their own cognitive processes, monitoring their performance, and adapting their strategies based on self-assessment. They can reflect on their own knowledge beliefs. And goals to improve decision-making and problem-solving. Artificial general intelligence systems address the challenge of robustness to adversarial examples by employing robust optimization techniques, adversarial training, and anomaly detection. They detect and mitigate adversarial attacks by learning robust representations, identifying anomalies, and adapting their behavior to adversarial environments. Philosophy plays a role in understanding the ethical implications of artificial general intelligence by exploring questions about morality, consciousness, and the nature of intelligence. It informs ethical frameworks, value alignment principles, and artificial intelligence governance policies to ensure responsible development and deployment of artificial general intelligence technologies. Artificial general intelligence systems handle the challenge of causal reasoning and understanding by modeling causal relationships, inferring causal effects, and predicting outcomes based on causal knowledge. They analyze causal structures, identify causal mechanisms, and make interventions to achieve desired outcomes. Artificial general intelligence systems can exhibit creativity and innovation in problem solving by generating novel ideas, exploring alternate solutions, and adapting strategies to achieve goals. They use techniques like generative modeling, reinforcement learning, and evolutionary algorithms to explore solution spaces and discover innovative solutions. Artificial general intelligence systems address the challenge of lifelong learning and continual adaptation by employing continual learning techniques, adaptive algorithms, and self-supervised learning mechanisms. They accumulate knowledge over time, update their models with new data, and adapt their behavior to changing environments without forgetting previous experiences. Artificial general intelligence systems handle the challenge of interpretability and transparency in complex models by employing model explanation techniques, interpretability metrics, and transparency standards. They aim to provide users with insights into model behavior, decision-making processes, and underlying reasoning to foster trust and understanding. Artificial general intelligence systems can exhibit meta-level reasoning and strategic planning by reasoning about their own thought processes, setting goals, and planning future actions. They can anticipate outcomes, consider alternative strategies, and make decisions at a higher level of abstraction. Artificial general intelligence systems address the challenge of uncertainty and ambiguity in decision-making by employing probabilistic reasoning, uncertainty quantification, and adaptive strategies. They analyze available information, estimate uncertainty, and make decisions that balance exploration and exploitation in dynamic environments. Artificial general intelligence systems can exhibit goal-directed behavior and planning similar to humans by setting objectives, formulating plans to achieve them, and executing actions to accomplish goals. They use techniques like reinforcement learning, planning algorithms, and hierarchical decision-making to pursue desired outcomes. Cognitive science plays a role in understanding human-like intelligence in artificial general intelligence by studying cognitive processes, mental representations, and problem-solving strategies. It informs the design of artificial intelligence algorithms, architectures, and models that mimic human cognition and behavior. Artificial general intelligence systems handle the challenge of integrating multiple modalities of information through techniques like multimodal learning, fusion of heterogeneous data sources, and cross-modal reasoning. They analyze and synthesize information from different sensory inputs to make informed decisions and predictions. Artificial general intelligence systems can exhibit metacognitive abilities like self-awareness and introspection by reasoning about their own cognitive processes, monitoring their performance, and adapting their strategies based on self-assessment. They can reflect on their own knowledge, beliefs, and goals to improve decision-making and problem-solving. Artificial general intelligence systems address the challenge of interpretability and transparency in decision-making by employing interpretable models, explanation mechanisms, and transparency tools. They aim to provide users with insights into decision-making processes, model behavior, and underlying reasoning to ensure accountability and trust. Neuroscience plays a role in understanding the computational principles of artificial general intelligence by investigating brain function, neural networks, and cognitive architectures. It provides insights into the mechanisms of learning, memory, and perception, which inform the development of artificial intelligence algorithms inspired by biological systems. Artificial general intelligence systems handle the challenge of generalization to new and unseen scenarios by leveraging transfer learning, domain adaptation, and meta-learning techniques. They can generalize knowledge learned from one domain to improve performance in new environments, tasks, or scenarios. Artificial general intelligence systems can exhibit common sense reasoning and understanding like humans by leveraging large-scale knowledge bases, semantic models, and reasoning algorithms. They can understand everyday concepts, infer implicit knowledge, and apply common sense reasoning to solve problems in diverse domains. Artificial general intelligence systems address the challenge of robustness to adversarial attacks and perturbations by employing robust optimization techniques, adversarial training, and anomaly detection. They detect and mitigate adversarial attacks by learning robust representations, identifying anomalies, and adapting their behavior to adversarial environments. Computational modeling plays a role in understanding human-like intelligence and artificial general intelligence by developing artificial intelligence algorithms, architectures, and models that simulate cognitive processes, learning mechanisms, and problem-solving strategies observed in humans. It provides a framework for testing hypotheses and validating theories about intelligence. Artificial general intelligence systems handle the challenge of integrating symbolic and subsymbolic reasoning through hybrid artificial intelligence approaches that combine symbolic reasoning with connectionist models. They use symbolic representations for abstract reasoning and subsymbolic techniques for pattern recognition and learning, leveraging the strengths of both paradigms. Artificial general intelligence systems can exhibit social intelligence and empathy in interactions with humans by recognizing emotions, understanding social cues, and responding appropriately to social situations. They can simulate empathy through effective computing techniques and engage in meaningful interactions with humans. Artificial general intelligence systems address the challenge of model interpretability and transparency by employing techniques such as model explanation methods, interpretability metrics, and transparency standards. These approaches aim to provide insights into the inner workings of artificial intelligence models, enabling users to understand how decisions are made and ensuring accountability and trust in artificial intelligence systems. Cognitive neuroscience plays a role in understanding the neural basis of artificial general intelligence by studying brain function, neural networks, and cognitive processes. Insights from cognitive neuroscience inform the development of artificial intelligence algorithms and architectures that mimic human intelligence, allowing researchers to build more biologically inspired artificial general intelligence systems. Artificial general intelligence systems handle the challenge of ethical decision-making in complex scenarios by incorporating ethical frameworks, value alignment mechanisms, and stakeholder engagement processes into their decision-making processes. These approaches aim to ensure that artificial general intelligence systems prioritize ethical principles, fairness, and societal well-being in their actions and decisions. Techniques for optimizing memory usage in artificial general intelligence systems include model compression, parameter sharing, and knowledge distillation. These methods reduce the memory footprint of artificial intelligence models while preserving their performance, allowing artificial general intelligence systems to operate efficiently in resource-constrained environments. Artificial general intelligence systems ensure data privacy and confidentiality in edge computing environments through techniques such as data encryption, access control mechanisms, and privacy-preserving algorithms. These approaches protect sensitive information and prevent unauthorized access to data in decentralized computing environments. Model distillation is a process where a complex artificial intelligence model, often referred to as the teacher model, transfers its knowledge to a simpler model known as the student model. This technique helps compress large models into smaller, more efficient versions without significant loss in performance, making them more suitable for deployment in resource-constrained environments. Strategies for optimizing memory usage in time series forecasting models include feature selection, dimensionality reduction, and memory-efficient algorithms. These techniques reduce the memory requirements of artificial intelligence models while maintaining their ability to accurately predict future trends in time series data. Artificial general intelligence systems handle model interpretation and explainability in real-time processing by generating explanations for their decisions, providing users with insights into the factors influencing artificial intelligence-driven outcomes. These explanations help users understand artificial intelligence predictions and build trust in artificial intelligence systems. Reinforcement learning algorithms can optimize memory usage in artificial general intelligence systems by learning efficient representations of data, prioritizing important information, and reducing redundancy in memory storage. These techniques help artificial general intelligence systems operate efficiently with limited memory resources while maximizing performance in reinforcement learning tasks. The impact of artificial general intelligence on the development of autonomous vehicles and drones is significant as it enables these systems to make intelligent decisions, navigate complex environments, and adapt to changing conditions autonomously. Artificial general intelligence-powered autonomous vehicles and drones have the potential to revolutionize transportation, logistics, and surveillance industries, offering safer, more efficient, and more capable solutions. Artificial general intelligence systems handle data aggregation and summarization in distributed environments by collecting and synthesizing information from multiple sources, summarizing key insights, and presenting aggregated results to users. These approaches help artificial general intelligence systems process large volumes of data efficiently and extract meaningful information from distributed data sources. Strategies for optimizing memory usage in anomaly detection models include anomaly pruning, feature selection, and model compression techniques. These methods reduce the memory footprint of artificial intelligence models while maintaining their ability to accurately detect anomalies in data streams. Artificial general intelligence systems handle data quality assurance and validation in real-time processing by employing data validation techniques, anomaly detection algorithms, and quality control mechanisms. These approaches ensure that artificial intelligence models receive accurate and reliable data inputs, leading to more robust and dependable artificial intelligence-driven decisions. AutoML techniques play a crucial role in optimizing memory usage in artificial general intelligence systems by automating the process of model selection, hyperparameter tuning, and architecture design. These techniques leverage algorithms to search through a wide range of models and configurations, identifying the most memory-efficient solutions for specific tasks or environments without the need for manual intervention. Ensemble learning is a concept where multiple machine learning models are combined to improve predictive performance. In the context of artificial general intelligence, ensemble learning can enhance model robustness, accuracy, and generalization by aggregating predictions from diverse models. It allows artificial general intelligence systems to leverage the strengths of different algorithms and mitigate the weaknesses of individual models, leading to more reliable and effective artificial intelligence solutions. Techniques for optimizing memory usage. In generative adversarial networks include model pruning, parameter sharing, and compression algorithms. These methods reduce the memory footprint of generative adversarial networks models while preserving their ability to generate high-quality synthetic data. By optimizing memory usage, artificial general intelligence systems can deploy generative adversarial networks in resource-constrained environments more efficiently. Artificial general intelligence systems handle continuous monitoring and adaptation in dynamic systems by employing online learning algorithms, adaptive control mechanisms, and real-time feedback loops. These approaches enable artificial general intelligence systems to adjust their behavior, update their models, and respond to changing conditions in dynamic environments, ensuring optimal performance over time. Graph-based algorithms play a role in optimizing memory usage in artificial general intelligence systems by representing data as graphs, leveraging graph structures for efficient storage and processing. These algorithms enable artificial general intelligence systems to analyze complex relationships, extract meaningful insights, and optimize memory usage in graph-based computations. The impact of artificial general intelligence on personalized healthcare solutions is significant, as it enables the development of artificial intelligence-driven tools and technologies that tailor medical treatments, interventions, and recommendations to individual patients' needs. Artificial general intelligence-powered healthcare solutions have the potential to improve patient outcomes, reduce healthcare costs, and enhance the quality of care by leveraging personalized data-driven insights and interventions. Artificial general intelligence systems handle data storage and retrieval in resource-constrained environments through techniques like data compression, indexing, and caching. These approaches optimize memory usage, minimize storage overhead, and enable efficient access to data in environments with limited resources. Strategies for optimizing memory usage in predictive maintenance models include feature selection, model compression, and anomaly detection techniques. These methods reduce the memory footprint of artificial intelligence models while maintaining their ability to accurately predict equipment failures and maintenance needs. Artificial general intelligence systems handle data provenance and lineage tracking in distributed systems by recording metadata, tracking data lineage, and ensuring data traceability across distributed nodes. These approaches enable artificial general intelligence systems to maintain data integrity, facilitate auditing, and ensure accountability in distributed data processing environments. Explainable artificial intelligence techniques play a role in optimizing memory usage in artificial general intelligence systems by providing insights into model behavior, decision-making processes, and underlying reasoning. These techniques help users understand artificial intelligence predictions, diagnose model performance issues, and identify opportunities for memory optimization. Self-supervised learning is a learning paradigm where artificial intelligence systems learn from unlabeled data without explicit supervision. In the context of artificial general intelligence, self-supervised learning enables artificial intelligence systems to acquire knowledge and learn representations from raw data, improving memory efficiency and generalization capabilities. Techniques for optimizing memory usage in recommendation systems include model compression, matrix factorization, and sparse representation methods. These approaches reduce the memory footprint of recommendation models while preserving their ability to generate accurate and personalized recommendations. Artificial general intelligence systems handle data synchronization and consistency in distributed environments through techniques like distributed consensus protocols, data replication, and conflict resolution mechanisms. These approaches ensure data consistency, coherence, and reliability across distributed nodes, enabling artificial general intelligence systems to operate seamlessly in distributed computing environments. Meta-learning algorithms play a role in optimizing memory usage in artificial general intelligence systems by learning to adapt to new tasks, environments, and datasets efficiently. These algorithms enable artificial general intelligence systems to leverage past experiences, generalize knowledge, and optimize memory usage for specific learning tasks or domains. The impact of artificial general intelligence on precision agriculture solutions is significant, as it enables the development of artificial intelligence-driven tools and technologies that optimize agricultural operations, improve crop yields, and minimize resource wastage. Artificial general intelligence-powered precision agriculture solutions leverage data analytics, sensor technologies, and machine learning algorithms to provide farmers with actionable insights and decision support for better agricultural management. Narrow artificial intelligence, often referred to as weak artificial intelligence, is designed to perform a specific task or set of tasks, exhibiting a narrow range of abilities within a limited context. Unlike general artificial intelligence, which aims to mimic human cognitive abilities across a wide range of tasks, narrow artificial intelligence is more specialized and focused. Picture it like a highly skilled worker in a factory excelling at one particular job, but not capable of performing tasks outside of its designated role. These systems are trained to excel at their specific tasks through a process called machine learning. During training, the artificial intelligence is exposed to vast amounts of data relevant to its function. This data serves as the foundation for the artificial intelligence to learn patterns, correlations, and rules that guide its decision-making process. Through iterative exposure to new data and feedback mechanisms, such as reinforcement learning or supervised learning, the artificial intelligence refines its algorithms to improve performance over time. Examples of narrow artificial intelligence applications are ubiquitous in our daily lives. From personalized recommendations on streaming platforms like Netflix or Spotify to virtual assistants such as Amazon's Alexa or Apple's Siri, narrow artificial intelligence enhances user experiences and streamlines tasks. Additionally, spam filters and email services, facial recognition technology in smartphones, and predictive text on keyboards are all examples of narrow artificial intelligence at work, demonstrating its versatility and practical utility. Characteristic features of narrow artificial intelligence systems include their specificity, dependence on large data sets, and lack of general intelligence. These systems excel at their designated tasks but lack the adaptability and creativity of human intelligence. Furthermore, narrow artificial intelligence relies heavily on data availability and quality. Without sufficient training data, the performance of these systems may suffer, highlighting the importance of robust data collection and pre-processing methods. Data processing and analysis are fundamental to the functioning of narrow artificial intelligence systems. These systems ingest vast amounts of data, process it through various algorithms to extract meaningful patterns or insights, and utilize these findings to make decisions or predictions. Techniques such as statistical analysis, pattern recognition, and machine learning algorithms form the backbone of data processing in narrow artificial intelligence, enabling the system to derive actionable intelligence from raw data inputs. Machine learning techniques play a pivotal role in the development and refinement of narrow artificial intelligence systems. By leveraging algorithms that allow the artificial intelligence to learn from experience and improve its performance over time, developers can create more sophisticated and effective artificial intelligence solutions. Supervised learning and unsupervised learning and reinforcement learning are common approaches used in narrow artificial intelligence development, each offering distinct advantages depending on the nature of the task at hand. Despite their efficacy in specific domains, narrow artificial intelligence systems have inherent limitations compared to general artificial intelligence. These limitations primarily stem from their narrow focus and lack of adaptability beyond predefined tasks. While narrow artificial intelligence excels at tasks it's been trained for, It struggles with tasks outside its expertise, lacking the ability to generalize knowledge or learn new skills autonomously. Narrow artificial intelligence systems can learn and adapt within the scope of their designated tasks through continuous exposure to new data and feedback mechanisms. These systems can refine their algorithms and improve performance over time. However, their adaptability is limited to the specific task or tasks they've been trained for, lacking the versatility and cognitive flexibility of human intelligence. Various algorithms are employed in narrow artificial intelligence systems to facilitate decision-making and prediction. Neural networks, decision trees, support vector machines, and Bayesian networks are among the commonly used algorithms, each suited to different types of tasks and data characteristics. These algorithms process input data, identify patterns or relationships, and generate output predictions or decisions based on learned parameters and rules. Industries across diverse sectors benefit from the application of narrow artificial intelligence technologies. From healthcare and finance to retail and manufacturing, narrow artificial intelligence solutions enhance efficiency, productivity, and decision-making processes. For instance, in healthcare, artificial intelligence-powered diagnostic systems assist medical professionals in interpreting medical images and identifying potential health risks. While in finance, artificial intelligence algorithms analyze market data to inform investment strategies and detect fraudulent activities. Interpreting and understanding data inputs are central to the functioning of narrow artificial intelligence systems. These systems employ various techniques, including natural language processing, computer vision, and sensor data analysis, to extract relevant information from diverse data sources. By processing and interpreting data inputs effectively, narrow artificial intelligence systems can generate actionable insights and facilitate informed decision-making across a wide range of applications. Ethical considerations abound in the development and deployment of narrow artificial intelligence systems. Concerns related to privacy, fairness, accountability, and bias must be addressed to ensure that artificial intelligence technologies benefit society without causing harm or perpetuating inequalities. Developers must implement measures to mitigate biases in training data, ensure transparency and explainability in artificial intelligence decision-making processes, and adhere to ethical guidelines and regulatory frameworks to uphold the responsible and ethical use of artificial intelligence technologies. Handling uncertainty and variability in data poses significant challenges for narrow artificial intelligence systems. Real-world data often exhibit noise, incompleteness, and ambiguity, which can undermine the reliability and accuracy of artificial intelligence predictions or decisions. Techniques such as uncertainty quantification, probabilistic modeling, and ensemble methods are employed to address these challenges, enabling artificial intelligence systems to account for uncertainty and variability in data and make more robust and reliable predictions. Developers face a myriad of challenges when creating narrow artificial intelligence solutions. These challenges include sourcing and pre-processing large and diverse data sets, selecting appropriate algorithms and techniques for specific tasks, optimizing model performance and scalability, addressing ethical and regulatory considerations, and ensuring the robustness and reliability of artificial intelligence systems in real-world environments. Collaboration across multidisciplinary teams, ongoing research and development efforts, and adherence to best practices and standards are essential for overcoming these challenges and advancing the field of narrow artificial intelligence. Narrow artificial intelligence systems process natural language inputs using techniques like natural language processing. These systems break down sentences into smaller parts, analyze the meaning of words, and understand context to generate appropriate responses. The key components of a narrow artificial intelligence system architecture include data input modules, processing algorithms, decision-making modules, and output interfaces. These components work together to process data, make decisions, and produce desired outputs. Narrow artificial intelligence systems can interact with humans in natural language. Virtual assistants like Siri, Alexa, and chatbots are examples of narrow artificial intelligence systems capable of understanding and responding to human language inputs. Narrow artificial intelligence systems handle image recognition tasks by analyzing pixel data from images and comparing patterns to pre-existing templates or training data. Techniques like convolutional neural networks are commonly used for this purpose. Using narrow artificial intelligence in data analysis raises privacy concerns as it involves analysing potentially sensitive information. Proper data anonymization, encryption, and compliance with privacy regulations are crucial to mitigate these risks. Narrow artificial intelligence systems perform pattern recognition tasks by identifying recurring patterns or trends in data. Machine learning algorithms such as support vector machines or decision trees are often employed for pattern recognition tasks. Data labeling is essential in training narrow artificial intelligence models as it provides ground truth annotations for supervised learning. It involves manually categorizing or tagging data to teach the artificial intelligence what to look for in future instances. Narrow artificial intelligence systems handle feedback and corrections by incorporating them into their learning algorithms. This helps them improve their performance over time based on user interactions and feedback. Real-world examples of narrow artificial intelligence improving efficiency and productivity include personalized recommendation systems in e-commerce, fraud detection algorithms in banking, and predictive maintenance systems in manufacturing. Narrow artificial intelligence systems handle large-scale data processing tasks by utilizing distributed computing frameworks. These frameworks enable parallel processing of data across multiple nodes to expedite computation. Techniques used to evaluate the performance of narrow artificial intelligence algorithms include metrics such as accuracy, precision, recall, and F1 score. Cross-validation and confusion matrices are also commonly employed for performance assessment. Narrow artificial intelligence systems can generate new insights from data analysis by uncovering hidden patterns, correlations, or trends that may not be apparent to human analysts. Narrow artificial intelligence systems handle unstructured data by employing techniques like text mining, sentiment analysis, or topic modeling to extract meaningful information from text, images, or other unstructured formats. Bias in narrow artificial intelligence algorithms can lead to unfair or discriminatory outcomes. Risks associated with bias include perpetuating existing inequalities, undermining trust in artificial intelligence systems, and causing harm to affected individuals or groups. Narrow artificial intelligence systems handle feature selection and extraction by identifying relevant features from raw data inputs and transforming them into a format suitable for analysis. Techniques like principal component analysis or feature engineering are commonly used for this purpose. Challenges in scaling narrow artificial intelligence solution. To handle big data include managing computational resources, optimizing algorithms for efficiency, and ensuring scalability without sacrificing performance or accuracy. Narrow artificial intelligence systems handle noisy or incomplete data inputs by employing techniques like data cleaning, imputation, or filtering to pre-process the data and remove or mitigate the effects of noise or missing values. Domain expertise is crucial in developing narrow artificial intelligence solutions as it provides insights into the specific requirements, nuances, and constraints of the application domain. Domain experts contribute to defining relevant features, selecting appropriate algorithms, and interpreting results effectively. Narrow artificial intelligence systems handle real-time data processing requirements by employing efficient algorithms, parallel processing techniques, and stream processing frameworks to analyze and respond to data inputs in near real time. Considerations when deploying narrow artificial intelligence in safety-critical applications include rigorous testing and validation, adherence to regulatory standards and safety protocols, and implementing fail-safe mechanisms or redundancy measures to mitigate risks of system failure or malfunction. Narrow artificial intelligence systems handle data security and protection by implementing encryption, access control, and data anonymization techniques to safeguard sensitive information and prevent unauthorized access or data breaches. Techniques for improving the interpretability of narrow artificial intelligence models include feature importance analysis, model visualization, and generating human-readable explanations or justifications for model predictions or decisions. Narrow artificial intelligence systems handle time series. Data analysis by employing specialized algorithms like recurrent neural networks or autoregressive models to capture temporal dependencies and patterns in sequential data. Data augmentation plays a role in improving the performance of narrow artificial intelligence models by increasing the diversity and quantity of training data. Techniques such as data synthesis, transformation, or perturbation help expose the model to a wider range of scenarios and improve generalization. Narrow artificial intelligence systems handle anomaly detection tasks by identifying deviations or outliers from expected patterns in data. Techniques such as statistical modeling, clustering, or machine learning algorithms are used to detect and classify anomalies. Narrow artificial intelligence systems can detect and mitigate adversarial attacks by incorporating robustness techniques such as adversarial training, input perturbation, or defensive distillation to improve resilience against malicious input manipulations. Handling imbalanced data sets is a challenge for narrow artificial intelligence systems, as it can lead to biased model predictions or inaccurate performance evaluation. Techniques such as resampling, cost-sensitive learning, or ensemble methods are employed to address class imbalance and improve model fairness and effectiveness. Deploying narrow artificial intelligence solutions in resource-constrained environments presents challenges such as limited computational power, memory, or bandwidth. Optimization techniques, model compression, and edge computing strategies are utilized to overcome these constraints and enable efficient deployment of artificial intelligence solutions. Narrow artificial intelligence systems handle data streaming and real-time analytics by leveraging stream processing frameworks like Apache Kafka or ApacheLink to ingest, process, and analyze data continuously as it flows through the system. Transfer learning plays a role in improving the performance of narrow artificial intelligence models by transferring knowledge learned from one task or domain to another. Pre-trained models or feature representations are fine-tuned or adapted to new tasks with limited labeled data, accelerating model training and improving generalization performance. Narrow artificial intelligence systems handle data pre-processing and normalization by cleaning, transforming, and standardizing raw data inputs to make them suitable for analysis. This includes tasks like removing outliers, scaling features to a common range, and handling missing values to ensure data quality and consistency. Techniques to reduce the computational complexity of narrow artificial intelligence algorithms include algorithmic optimizations, model simplification, and dimensionality reduction methods such as principal component analysis or feature selection techniques. These approaches help streamline computations and improve efficiency without sacrificing model performance. Handling temporal and spatial data correlations involves analyzing the relationships between data points across time or space. Narrow artificial intelligence systems employ specialized algorithms like recurrent neural networks for temporal data and spatial modeling techniques for spatial data to capture these correlations and make accurate predictions or decisions. Narrow artificial intelligence systems can integrate with existing software and infrastructure through APIs, libraries, or software development kits that allow seamless communication and interoperability with other systems. This enables organizations to leverage artificial intelligence capabilities within their existing workflows and applications. Explainability plays a crucial role in building trust in narrow artificial intelligence systems by providing insights into how the artificial intelligence makes decisions or predictions. Techniques such as model interpretation, feature importance analysis, and generating human-readable explanations help users understand and trust artificial intelligence-driven decisions. Narrow artificial intelligence systems handle regression tasks by predicting continuous numerical values and classification tasks by categorizing data into predefined classes or labels. Techniques like linear regression, logistic regression, and support vector machines are commonly used for these tasks. Optimizing hyperparameters in narrow artificial intelligence models involves tuning model parameters and settings to maximize performance metrics such as accuracy or efficiency. Techniques like grid search, random search, or Bayesian optimization are used to search for optimal hyperparameter configurations. Feature engineering and selection are critical in narrow artificial intelligence model development to identify relevant features that contribute to predictive performance. Techniques such as feature scaling, dimensionality reduction, or creating new features from existing ones help improve model accuracy and efficiency. Narrow artificial intelligence systems can adapt to changes in data distribution over time through techniques like online learning or concept drift detection. These approaches enable the artificial intelligence to continuously update its model based on incoming data streams and adjust to evolving patterns or trends. Handling missing data in narrow artificial intelligence. Models involves imputation methods such as mean imputation, median imputation, or predictive modeling to estimate missing values based on available data. These techniques help prevent bias and ensure robust model performance. Narrow artificial intelligence systems handle model training and inference on distributed systems by parallelizing computations across multiple nodes or processors. Distributed frameworks like TensorFlow or PyTorch enable scalable and efficient training and deployment of artificial intelligence models on distributed architectures. Uncertainty quantification in narrow artificial intelligence applications involves estimating the uncertainty associated with model predictions or decisions. Techniques like probabilistic modeling, Bayesian inference, or Monte Carlo sampling help quantify and account for uncertainty in artificial intelligence-driven outcomes. Narrow artificial intelligence systems handle sequential decision-making tasks by employing reinforcement learning techniques such as Markov decision processes or deep Q learning. These approaches enable the artificial intelligence to learn optimal action sequences in dynamic environments to achieve desired goals. Techniques to reduce overfitting in narrow artificial intelligence models include regularization methods like L1 or L2 regularization, dropout, or early stopping. These techniques help prevent the model from memorizing noise in the training data and improve its generalization performance. Narrow artificial intelligence systems handle multimodal data inputs by integrating information from multiple sources or modalities such as text, images, or sensor data. Techniques like fusion methods, multitask learning, or attention mechanisms are used to combine and process diverse data inputs effectively. Narrow artificial intelligence systems can learn from unlabeled data through techniques like unsupervised learning. Instead of relying on labeled examples, these systems identify patterns, clusters, or relationships within the data to uncover underlying structures and insights autonomously. Reinforcement learning plays a crucial role in training narrow artificial intelligence agents by enabling them to learn optimal behaviours through trial and error. Agents receive feedback in the form of rewards or penalties based on their actions, allowing them to learn from experience and improve their decision-making over time. Narrow artificial intelligence systems handle temporal dependencies in data sequences by employing specialized algorithms like recurrent neural networks or long short-term memory networks. These architectures are designed to capture sequential information and learn patterns across time steps in data sequences. Techniques for improving the scalability of narrow artificial intelligence solutions include distributed computing frameworks, parallel processing techniques, and model optimization strategies. These approaches enable efficient utilization of computational resources and facilitate the deployment of artificial intelligence solutions at scale. Narrow artificial intelligence systems address data drift and concept drift by continuously monitoring incoming data streams and adapting their models accordingly. Techniques like online learning, adaptive algorithms, and change detection methods help detect and mitigate shifts in data distribution or underlying concepts over time. Narrow artificial intelligence systems can perform feature extraction automatically through techniques like deep learning. Deep neural networks can learn hierarchical representations of raw data, automatically extracting relevant features for subsequent analysis or decision-making tasks. Model ensembling plays a role in improving the robustness of narrow artificial intelligence solutions by combining predictions from multiple individual models to make more accurate and reliable decisions. Techniques like bagging boosting or stacking are commonly used to create ensembles of diverse models that complement each other's strengths and weaknesses. Narrow artificial intelligence systems handle data transformation and normalization by pre-processing raw data, inputs to standardize or scale them to a common range. This helps ensure consistency and comparability across different features and improves the performance of artificial intelligence models. Techniques to address the cold start problem in narrow artificial intelligence applications include hybrid approaches, transfer learning, or leveraging auxiliary information to bootstrap the learning process. These techniques help overcome the lack of initial data or knowledge and accelerate model training. Narrow artificial intelligence systems handle batch processing and streaming data by employing specialized frameworks and algorithms for each scenario. Batch processing involves analyzing fixed batches of data offline, while streaming data processing involves analyzing data in real time as it arrives. Narrow artificial intelligence systems can perform unsupervised learning tasks to uncover patterns, clusters, or associations within data without labeled examples. Techniques like clustering, dimensionality reduction, or association rule mining are used for unsupervised learning tasks. Domain adaptation plays a role in transferring knowledge between domains in narrow artificial intelligence by adapting models trained on source domain data to perform well on target domain data. Techniques like domain alignment, adversarial training, or transfer learning are used to bridge the gap between different domains. Narrow artificial intelligence systems handle noise and outliers in data by employing techniques like robust statistics, outlier detection methods, or data pre-processing steps such as filtering or smoothing. These techniques help improve the quality and reliability of artificial intelligence-driven decisions or predictions. Techniques for improving the efficiency of narrow artificial intelligence algorithms include algorithmic optimizations, model pruning, or hardware acceleration. These approaches help reduce computational overhead and speed up the training or inference process. Narrow artificial intelligence systems handle privacy-preserving data analysis by implementing techniques like differential privacy, federated learning, or homomorphic encryption to protect sensitive information while still deriving useful insights from. These techniques help balance the trade-off between data privacy and utility in artificial intelligence-driven applications. Model compression plays a crucial role in reducing the memory footprint of narrow artificial intelligence models by optimizing model parameters, reducing redundancy, or using specialized compression techniques. This enables efficient deployment of artificial intelligence models on resource-constrained devices or environments without sacrificing performance. Narrow artificial intelligence systems handle data augmentation and synthesis by generating additional training examples through techniques like image rotation, flipping, or adding noise to text data. These approaches help increase the diversity and quantity of training data, improving the generalization and robustness of artificial intelligence models. Narrow artificial intelligence systems can detect and handle concept drift in data streams by continuously monitoring data distributions and adapting their models accordingly. Techniques like change detection algorithms or drift detection methods help detect shifts in data patterns and trigger model updates or retraining as needed. Techniques for improving the robustness of narrowed artificial intelligence models to adversarial attacks include adversarial training, input perturbation, or robust optimization methods. These approaches help defend against malicious input manipulations and improve model resilience to adversarial perturbations. Narrow artificial intelligence systems handle data exploration and visualization by employing techniques like descriptive statistics, scatter plots, or heat maps to analyze and visualize data distributions, correlations, or trends. This helps users gain insights into the underlying characteristics of the data and inform subsequent modeling or decision-making processes. Active learning plays a role in optimizing the data labeling process for narrow artificial intelligence models by selecting the most informative or uncertain data points for annotation. This reduces the labeling effort while maximizing the effectiveness of the training data, leading to more efficient model training and improved performance. Narrow artificial intelligence systems handle multitask learning scenarios by jointly training a single model to perform multiple related tasks simultaneously. This enables shared learning of task-specific features and relationships, leading to improved generalization and efficiency across tasks. Narrow artificial intelligence systems can adapt to changes in the environment or task requirements through techniques like transfer learning, continual learning, or online adaptation. These approaches enable the artificial intelligence to update its knowledge or adapt its behavior based on new data or evolving circumstances. Techniques for quantifying and mitigating bias in narrow artificial intelligence models include fairness-aware algorithms, bias detection methods, or fairness constraints during model training. These approaches help identify and mitigate biases in artificial intelligence-driven decisions or predictions, promoting fairness and equity in artificial intelligence applications. Narrow artificial intelligence systems handle hierarchical and relational data structures by employing techniques like graph neural networks, relational learning algorithms, or hierarchical clustering methods. These approaches enable effective modeling and analysis of complex data structures with interconnected or nested relationships. Uncertainty estimation plays a crucial role in decision-making with narrow artificial intelligence models by quantifying the confidence or uncertainty associated with model predictions. Techniques like probabilistic modeling, uncertainty quantification, or Bayesian inference help users make informed decisions or take appropriate actions based on artificial intelligence-driven predictions. Narrow artificial intelligence systems handle distributed training across multiple devices or nodes by partitioning data and computations, synchronizing model updates, or employing decentralized optimization algorithms. These approaches enable efficient parallelization of model training and scaling to large datasets or computational resources. Narrow artificial intelligence systems can perform automated feature selection and dimensionality reduction through techniques like feature importance analysis, principal component analysis, or autoencoders. These approaches help identify relevant features and reduce the dimensionality of input data, improving model efficiency and generalization performance. Techniques for improving the interpretability of narrow artificial intelligence. Models include feature importance analysis, model visualization, or generating human-readable explanations for model predictions. These approaches help users understand and trust artificial intelligence-driven decisions, promoting transparency and accountability in artificial intelligence applications. Narrow artificial intelligence systems handle model evaluation and validation by assessing performance metrics like accuracy, precision, recall, or F1 score using techniques like cross-validation, holdout validation, or bootstrapping. These approaches help ensure the reliability and effectiveness of artificial intelligence models in real-world applications. Hyperparameter tuning plays a crucial role in optimizing the performance of narrow artificial intelligence models by adjusting parameters that control the learning process, such as learning rates or regularization strengths. This helps fine-tune the model to achieve better accuracy, generalization, and efficiency. Narrow artificial intelligence systems handle data labeling and annotation tasks by utilizing human annotators or crowdsourcing platforms to label data examples with relevant tags or categories. This labeled data is then used to train artificial intelligence models through supervised learning. Narrow artificial intelligence systems can handle semi-supervised and self-supervised learning tasks where only a subset of the data is labelled or no labels are provided at all. Techniques like self-training, pseudo-labeling, or generative models enable artificial intelligence systems to leverage unlabeled data to improve performance. Techniques for improving the efficiency of narrow artificial intelligence inference include model quantization, pruning, or compression to reduce the computational resources required for model execution. These approaches help deploy artificial intelligence models on resource-constrained devices or environments without sacrificing performance. Narrow artificial intelligence systems handle explainable and interpretable decision-making by generating human-readable explanations or justifications for model predictions or decisions. Techniques like feature importance analysis, model visualization, or rule-based explanations help users understand and trust artificial intelligence-driven outcomes. Probabilistic reasoning plays a role in narrow artificial intelligence applications by quantifying uncertainty and reasoning under uncertainty using probabilistic models or inference algorithms. This enables artificial intelligence systems to make more informed decisions or predictions in uncertain or ambiguous situations. These systems handle temporal and spatial data correlations by employing specialized algorithms like recurrent neural networks or convolutional neural networks. These architectures are designed to capture sequential and spatial dependencies in data, enabling accurate predictions or classifications. Narrow artificial intelligence systems can perform online and incremental learning by updating model parameters continuously as new data becomes available. This enables artificial intelligence systems to adapt to changes in the environment or task requirements without retraining the entire model from scratch. Techniques for optimizing the memory usage of narrow artificial intelligence models include model compression, parameter sharing, or sparse representations to reduce the memory footprint of model parameters or activations. This enables efficient deployment of artificial intelligence models on memory-constrained devices or platforms. Narrow artificial intelligence systems handle uncertainty and variability in data by employing techniques like uncertainty quantification, robust statistics, or ensemble methods to account for and mitigate uncertainty in artificial intelligence-driven decisions or predictions. Interpretability plays a crucial role in ensuring the trustworthiness of narrow artificial intelligence models by providing insights into how the model operates and why it makes certain predictions or decisions. Transparent and interpretable models help users understand and trust artificial intelligence-driven outcomes, promoting accountability and fairness. Narrow artificial intelligence systems handle class imbalance and rare events in data by employing techniques like oversampling, undersampling, or cost-sensitive learning to balance class distributions and improve model performance on minority classes. Narrow artificial intelligence systems can handle multimodal and heterogeneous data inputs by integrating information from multiple sources or modalities such as text, images, or sensor data. Techniques like fusion methods, multitask learning, or attention mechanisms enable effective processing and analysis of diverse data inputs. Techniques for improving the robustness of narrow artificial intelligence models to adversarial attacks include adversarial training, input sanitization, or robust optimization methods. These approaches help defend against malicious input manipulations and improve model resilience to adversarial perturbations. Narrow artificial intelligence systems handle data privacy and security concerns by implementing techniques like data anonymization, encryption, or access control to protect sensitive information and prevent unauthorized access or data breaches. These measures help ensure the confidentiality and integrity of data in artificial intelligence-driven applications. Data preprocessing and feature engineering play essential roles in narrow artificial intelligence model development by preparing raw data inputs for analysis and extracting relevant features that capture important information. Preprocessing involves tasks like cleaning, scaling, and encoding data to ensure consistency and compatibility, while feature engineering involves creating new features or transforming existing ones to improve model performance and accuracy. Narrow artificial intelligence systems handle concept drift and data evolution over time by continuously monitoring data streams and adapting their models accordingly. Techniques like online learning, adaptive algorithms, or change detection methods help detect shifts in data patterns and trigger model updates or retraining as needed. Narrow artificial intelligence systems can perform anomaly detection and outlier identification tasks by analyzing data patterns and identifying instances that deviate significantly from expected behavior. Techniques like statistical modeling, clustering, or machine learning algorithms are used for anomaly detection in various domains. Techniques for improving the interpretability of narrow artificial intelligence models include model visualization, feature importance analysis, or generating human-readable explanations for model predictions. Narrow artificial intelligence systems handle uncertainty and variability in data inputs by employing techniques like uncertainty quantification, robust statistics, or ensemble methods to account for and mitigate uncertainty in artificial intelligence-driven decisions or predictions. Narrow artificial intelligence systems handle data storage and retrieval in resource-constrained environments by using efficient data structures, compression techniques, or streaming data processing frameworks to minimize memory usage and optimize performance. Model distillation is a process where a large, complex model, which is teacher model, transfers its knowledge to a smaller, simpler model, which is student model, through supervised learning. This helps compress the knowledge of the teacher model into a more lightweight student model, making it suitable for deployment in resource-constrained environments typical of narrow artificial intelligence applications. Strategies for optimizing memory usage in time series forecasting models include using sparse representations, model compression techniques, or incremental learning approaches to reduce memory footprint while preserving model accuracy and performance. A neural network is a computational model inspired by the structure and function of the human brain. It consists of interconnected nodes called neurons organized into layers, through which data flows, allowing the network to perform complex tasks like pattern recognition, classification, and regression. Neural networks mimic the human brain by using interconnected neurons to process and transmit information. Like the brain, they can learn from experience, adapt to new inputs, and improve performance over time. The basic components of a neural network include neurons, weights, biases, activation functions, and layers. Neurons receive input signals, apply weights and biases, and pass the result through an activation function to produce an output. These outputs are then passed to other neurons in the network, allowing information to flow through the network. Neurons in a neural network are connected through weighted connections, which determine the strength of the connection between neurons. These weights are adjusted during the learning process to optimize the network's performance. The input layer of a neural network receives input data and passes it to the subsequent layers for processing. It contains one neuron for each feature or input variable. The output layer of a neural network produces the final output, or prediction based on the processed input data. It contains one neuron for each possible output or class in a classification task. Information flows through a neural network in a forward pass, starting from the input layer, passing through the hidden layers, and culminating in the output layer, where the final prediction or output is generated. The activation function in a neural network determines the output of a neuron based on its input. It introduces nonlinearity into the network, enabling it to learn complex patterns and relationships in the data. Neural networks learn from data through a process called training, where they adjust their weights and biases to minimize the difference between predicted and actual outputs. This is typically done using optimization algorithms like gradient descent. Backpropagation is an algorithm used to train neural networks by computing the gradient of the loss function with respect to the network's parameters. It involves propagating the error backward through the network and adjusting the weights and biases accordingly to minimize the error. Supervised learning in neural networks involves training the network on labeled data, where each input is associated with a corresponding target output. The network learns to map inputs to outputs by minimizing the difference between predicted and actual outputs. Unsupervised learning in neural networks involves training the network on unlabeled data, where the network learns to extract meaningful patterns or features from the data without explicit supervision. Reinforcement learning in neural networks involves training the network to make sequential decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. The network learns to maximize cumulative rewards over time by exploring different actions and learning from the consequences. The loss function in a neural network is a mathematical measure that quantifies the difference between the predicted output of the network and the actual output or ground truth. It represents how well the network is performing on a given task, such as classification or regression. The loss function is used in training a neural network to guide the optimization process. During training, the network adjusts its parameters, such as weights and biases, to minimize the value of the loss function. This is achieved through an optimization algorithm like gradient descent. Gradient descent is an optimization algorithm used to minimize the loss function and train neural networks. It works by iteratively adjusting the parameters of the network in the direction of the steepest descent of the loss function with respect to those parameters. This process continues until the algorithm converges to a minimum of the loss function. Training neural networks comes with several challenges, including vanishing gradients, exploding gradients, overfitting, underfitting, and computational complexity. These challenges can affect the network's ability to learn and generalize from the training data. Overfitting occurs when a neural network learns to perform well on the training data, but fails to generalize to new unseen data. It can be prevented by techniques such as regularization, dropout, and early stopping, which aim to reduce the complexity of the model and improve its ability to generalize. Underfitting, on the other hand, occurs when a neural network is too simple to capture the underlying patterns in the data. It can be addressed by increasing the complexity of the model, adding more layers or neurons, or using more sophisticated architectures. Common types of neural networks include feed-forward neural networks, recurrent neural networks, convolutional neural networks, generative adversarial networks, long short-term memory networks, and gated recurrent unit networks. Each type has its unique architecture and is suited for different tasks. A feed-forward neural network is the simplest type of neural network where information flows in one direction, from input to output, without any loops or cycles. It's commonly used for tasks like classification and regression. A recurrent neural network is designed to handle sequential data by introducing connections between neurons that form loops, allowing information to persist over time. RNNs are commonly used for tasks like time series prediction and natural language processing. A convolutional neural network is specialized for processing grid-like data, such as images, by applying convolutional operations to extract hierarchical features. Convolutional neural networks are widely used in image recognition and computer vision tasks. A generative adversarial network consists of two neural networks, a generator and a discriminator, that are trained together in a competitive manner. Generative adversarial networks are used for generating new data samples, such as images or text, that resemble the training data. Long short-term memory networks are a type of recurrent neural network designed to capture long-term dependencies in sequential data by introducing memory cells with gating mechanisms. Long short-term memories are commonly used for tasks like speech recognition and language translation. Gated recurrent unit networks are another type of recurrent neural network that simplifies the architecture of long short-term memory networks while retaining similar capabilities. GRUs are often used in scenarios where computational resources are limited or simpler models are preferred. Neural networks are used in image recognition by processing pixel data through layers of neurons to extract features and make predictions about the content of images. They can identify objects, classify images, and even generate new images. In natural language processing, neural networks are used to process and understand human language by converting text data into numerical representations that can be processed by the network. They are used for tasks such as language translation, sentiment analysis, and text generation. Neural networks are employed in speech recognition by processing audio data to identify and interpret spoken words. They analyze patterns in sound waves and convert them into text, allowing devices like smartphones and virtual assistants to understand and respond to human speech. In autonomous vehicles, neural networks play a crucial role in interpreting sensor data from cameras, LiDAR, and radar systems to perceive the vehicle's surroundings. They help in tasks such as object detection, lane detection, and pedestrian recognition, enabling the vehicle to make decisions and navigate safely. In medical diagnosis, neural networks analyze patient data such as medical images, genetic information, and clinical records to assist healthcare professionals in diagnosing diseases and conditions. They can detect abnormalities in medical images, predict disease risk factors, and provide personalized treatment recommendations. In financial forecasting, neural networks analyze historical market data and economic indicators to predict future trends in stock prices, exchange rates, and other financial instruments. They help investors and financial institutions make informed decisions about investments and risk management. Recommender systems utilize neural networks to analyze user preferences and behavior to recommend personalized products, services, or content. They power recommendation engines on e-commerce platforms, streaming services, and social media platforms, enhancing user experience and engagement. Neural networks are integrated into robotics to enable tasks such as object recognition, motion planning, and control in robotic systems. They allow robots to perceive their environment, make decisions, and adapt to changes autonomously, enhancing their capabilities in various applications. In drug discovery, neural networks analyze chemical and biological data to predict the properties and activities of molecules, aiding in the development of new drugs and therapies. They accelerate the drug discovery process by screening potential candidates and optimizing drug design. Anomaly detection systems utilize neural networks to identify unusual patterns or deviations from normal behavior in data, such as network traffic, manufacturing processes, or financial transactions. They help detect and prevent fraudulent activities, equipment failures, or security breaches. Virtual assistants like Siri, Alexa, and Google Assistant employ neural networks to understand and respond to user queries and commands. They process natural language input, extract relevant information, and generate appropriate responses, providing users with personalized assistance and information. Sentiment analysis involves using neural networks to analyze text data, such as social media posts or customer reviews, to determine the sentiment or emotions expressed. It helps businesses understand public opinion, customer feedback, and trends, enabling them to make informed decisions and improve products or services. Neural networks are utilised in fraud detection systems to identify fraudulent transactions or activities by analysing patterns and anomalies in financial data. They help financial institutions detect and prevent fraudulent behaviour, protecting customers and mitigating financial losses. In game playing, neural networks are employed to develop intelligent agents that can play games such as chess, Go, or video games. They learn to make strategic decisions and adapt to different game scenarios, competing against human players or other AI opponents. Weather forecasting models leverage neural networks to analyse meteorological data, such as temperature, humidity, and wind patterns, to predict weather conditions and patterns. They help meteorologists make forecasts about future weather events and phenomena, aiding in disaster preparedness and planning. In genomics, neural networks analyse genetic sequences and biological data to study gene expression, protein interactions, and disease mechanisms. They help researchers understand complex biological systems, identify genetic markers, and develop personalised medicine and treatments. Customer segmentation involves using neural networks to group customers based on similarities in behaviour, demographics, or preferences. They help businesses tailor marketing strategies, product recommendations, and customer experiences to specific customer segments, improving customer satisfaction and retention. Neural networks play a crucial role in personalised medicine by analysing individual patient data, such as genetic information, medical history, and lifestyle factors, to tailor treatment plans and interventions. They help healthcare professionals predict disease risk, recommend personalised therapies, and optimise treatment outcomes based on patient-specific characteristics. In social network analysis, neural networks analyse social media data and online interactions to identify patterns, communities, and influential users. They help researchers understand social dynamics, detect trends, and predict user behaviour, aiding in targeted marketing, content moderation, and social network optimization. Text generation involves using neural networks to generate human-like text based on input prompts or existing text data. They are employed in applications such as chatbots, virtual assistants, and content generation tools, producing natural and coherent text responses or content. Autonomous drones utilise neural networks to process sensor data and make decisions in real time, enabling tasks such as navigation, obstacle avoidance, and object tracking. They help drones operate autonomously in various environments, including surveillance, agriculture, and delivery. Content recommendation systems use neural networks to analyse user preferences and behaviour to recommend personalised content, such as articles, videos, or products. They enhance user engagement and satisfaction by providing relevant and timely recommendations tailored to individual interests. Emotion recognition involves using neural networks to analyse facial expressions, voice patterns, or text data to identify and interpret human emotions. They are employed in applications such as customer service, healthcare, and entertainment, enabling systems to understand and respond to user emotions. Object detection systems utilise neural networks to identify and localise objects within images or videos. They are employed in various applications, including surveillance, autonomous vehicles, and medical imaging, enabling systems to recognise and track objects of interest. Machine translation involves using neural networks to translate text or speech from one language to another. They analyze linguistic patterns and semantic meaning to produce accurate and fluent translations, facilitating communication and information exchange across languages. Face recognition systems use neural networks to analyze facial features and patterns to identify individuals from images or video footage. They are employed in security, law enforcement, and access control systems, enabling biometric authentication and identity verification. Autonomous navigation systems utilize neural networks to process sensor data and make decisions for navigating vehicles or robots in dynamic environments. They help systems plan routes, avoid obstacles, and adapt to changing conditions, enabling safe and efficient navigation. In cybersecurity, neural networks analyze network traffic, system logs, and user behavior to detect and prevent cyber threats such as malware, phishing, and unauthorized access. They help identify anomalies, predict potential attacks, and strengthen defense mechanisms to protect digital assets and data. Customer churn prediction involves using neural networks to analyze customer data and predict the likelihood of customers leaving a service or subscription. They help businesses identify at-risk customers, implement targeted retention strategies, and improve customer loyalty and satisfaction. Energy forecasting systems utilize neural networks to analyze historical energy consumption data and predict future demand or generation patterns. They help energy companies optimize resource allocation, plan infrastructure investments, and improve energy efficiency and sustainability. Wildlife conservation efforts utilize neural networks to analyze ecological data, such as satellite imagery, camera trap photos, and acoustic recordings to monitor and protect endangered species and habitats. They help researchers track animal populations, detect illegal activities, and inform conservation strategies and policies. Neural networks are utilised in agriculture to optimise crop yield, predict crop diseases, and monitor soil conditions. By analysing data from sensors, satellites, and drones, neural networks can provide farmers with valuable insights into crop health, water usage, and pest management, allowing for more efficient and sustainable farming practices. In supply chain optimization, neural networks are employed to forecast demand, optimize inventory levels, and improve logistics efficiency. By analyzing historical sales data and market trends, neural networks can help businesses streamline their supply chain operations, reduce costs, and enhance customer satisfaction through timely deliveries and optimized inventory management. Traffic management systems utilize neural networks to analyze traffic patterns, predict congestion, and optimize traffic flow. By processing data from sensors, cameras, and GPS devices, neural networks can provide real-time insights to traffic controllers, enabling them to adjust traffic signals, reroute vehicles, and alleviate congestion in busy urban areas. In music generation, neural networks are used to compose, arrange, and produce music autonomously. By analysing patterns in existing music compositions, neural networks can generate new melodies, harmonies, and rhythms, offering musicians and composers new creative possibilities and inspiration. Real-time bidding platforms use neural networks to analyse user behaviour and predict ad performance in milliseconds. By processing vast amounts of data about user preferences and browsing history, neural networks can help advertisers bid on ad placements more effectively, maximising their return on investment and reaching their target audience more efficiently. Virtual reality applications utilise neural networks to create immersive experiences and realistic simulations. By processing sensory data from virtual environments and user interactions, neural networks can enhance the realism and interactivity of virtual reality experiences, enabling users to engage with digital content in more immersive ways. Augmented reality systems use neural networks to overlay digital information onto the physical world in real time. By analysing the user's surroundings and context, neural networks can enhance the accuracy and relevance of augmented reality content, offering users valuable information and interactive experiences in their everyday environment. Drug response prediction involves using neural networks to analyze genetic data and predict how individuals will respond to different medications. By identifying genetic markers associated with drug efficacy and adverse reactions, neural networks can help healthcare providers personalize treatment plans and improve patient outcomes. Network intrusion detection systems utilize neural networks to identify and mitigate cyber threats in computer networks by analyzing network traffic patterns and detecting anomalous behavior. Neural networks can detect and respond to potential security breaches, protecting sensitive data and preventing cyber attacks. Sentiment analysis involves using neural networks to analyze text data and extract sentiment or emotions expressed by users. By processing social media posts, customer reviews, and other text data, neural networks can identify positive, negative, or neutral sentiments, enabling businesses to understand customer feedback and sentiment trends. Customer service automation systems use neural networks to automate repetitive tasks and streamline customer interactions. By analyzing customer inquiries and dialogues, neural networks can provide automated responses, route inquiries to the appropriate department, and improve the efficiency of customer service operations. Content moderation platforms utilize neural networks to detect and remove inappropriate or harmful content from online platforms. By analyzing images, videos, and text data, neural networks can identify content that violates community guidelines or poses risks to users, helping to maintain a safe and positive online environment. Image captioning involves using neural networks to generate descriptive captions for images automatically. By analyzing the content and context of images, neural networks can generate natural language descriptions that accurately describe the visual content, enabling accessibility and enhancing user experience in applications such as social media and image search. Content creation tools use neural networks to assist users in generating various types of content, such as articles, artwork, or music. By analyzing user input and existing content, neural networks can provide suggestions, generate drafts, and assist users in the creative process, offering inspiration and support in content creation endeavors. Supply chain management systems leverage neural networks to optimize inventory levels, forecast demand, and improve operational efficiency. By analyzing data from suppliers, manufacturers, and distributors, neural networks can help businesses reduce costs, minimize stockouts, and streamline supply chain operations, enhancing overall performance and competitiveness. Neural networks are applied in social media analytics to analyze user behavior, sentiment, and trends across various platforms. Processing vast amounts of social media data, neural networks can identify patterns, detect emerging topics, and predict user engagement, helping businesses understand and leverage social media for marketing, customer engagement, and brand management purposes. In wildlife monitoring, neural networks are used to analyze camera trap images, satellite data, and acoustic recordings to track and identify animal species, monitor habitat changes, and assess biodiversity. By automatically classifying and recognizing wildlife patterns, neural networks enable researchers and conservationists to collect data more efficiently and make informed decisions about wildlife conservation efforts. Urban planning utilizes neural networks to analyze urban infrastructure, traffic patterns, and demographic data to optimize city design and development. By processing data from sensors, GPS devices, and urban databases, neural networks can help urban planners identify areas for improvement, predict future population growth, and plan for sustainable urban development. Manufacturing optimization employs neural networks to optimize production processes, improve product quality, and reduce costs in manufacturing industries. By analyzing sensor data, production logs, and quality control metrics, Neural networks can identify inefficiencies, predict equipment failures, and optimize manufacturing workflows, enhancing productivity and profitability. Language modeling involves using neural networks to generate human-like text or speech in natural language processing tasks. By analyzing large corpora of text data, neural networks can learn the syntactic and semantic patterns of human language, enabling applications such as machine translation, text generation, and speech recognition. Product recommendation systems leverage neural networks to analyze user preferences, purchase history, and browsing behavior to recommend relevant products or services. By processing user interactions and feedback, neural networks can personalize recommendations, improve user experience, and increase sales for e-commerce platforms and online retailers. Fault detection systems use neural networks to monitor industrial equipment, detect anomalies, and predict equipment failures in real time by analyzing sensor data and historical performance. Neural networks can identify deviations from normal operating conditions, enabling proactive maintenance and minimizing downtime in industrial settings. Data compression techniques employ neural networks to compress large data sets into smaller representations while preserving essential information. By learning efficient representations of data, neural networks can reduce storage space, accelerate data transmission, and optimize memory usage in various applications, including image and video compression. Medical imaging utilizes neural networks to analyze and interpret medical images, such as X-rays, MRIs, and CT scans for diagnostic purposes, by extracting features and patterns from image data. Neural networks can assist radiologists in detecting abnormalities, diagnosing diseases, and guiding treatment decisions, improving patient care and outcomes. Autonomous vehicles employ neural networks to perceive the surrounding environment, detect obstacles, and make driving decisions in real time. By processing sensor data from cameras, LiDAR, and radar systems, neural networks can recognize objects, predict their movements, and navigate safely in complex traffic scenarios, enabling autonomous driving technology. Facial recognition systems utilize neural networks to identify and verify individuals based on facial features captured in images or video footage. By analyzing facial landmarks and patterns, neural networks can match faces against a database of known identities, enabling applications such as biometric authentication, surveillance, and access control. Weather prediction employs neural networks to analyze meteorological data, satellite images, and atmospheric models to forecast weather patterns and phenomena. By learning complex relationships between weather variables, neural networks can predict future weather conditions, provide early warnings for severe weather events, and support decision-making in meteorology and climate science. Gaming utilizes neural networks for various purposes, including character animation, game design, and player behavior prediction. By simulating virtual environments, learning player preferences, and generating realistic game elements, neural networks enhance the immersion and realism of video games, offering engaging and interactive gaming experiences. Speech synthesis involves using neural networks to generate human-like speech from text input. By learning the prosody, intonation, and pronunciation rules of spoken language, neural networks can synthesize natural-sounding speech for applications such as virtual assistants, voice assistants, and automated customer service systems. Chatbots utilize neural networks to understand and generate natural language responses in conversational interactions with users. By analyzing text input, learning from previous conversations, and generating contextually relevant responses, neural networks enable chatbots to provide personalized assistance, answer questions, and engage users in natural language conversations. Neural networks are employed in autonomous drones to navigate, identify obstacles, and make decisions independently. By processing data from onboard sensors like cameras and LiDAR, neural networks can recognize objects, plan flight paths, and avoid collisions, enabling drones to operate safely and efficiently in various environments, such as surveillance, agriculture, and package delivery. Credit scoring utilizes neural networks to assess creditworthiness and predict the likelihood of loan defaults based on borrower profiles and financial histories. By analyzing vast amounts of credit-related data, neural networks can identify patterns, assess risk levels, and automate the credit evaluation process, helping lenders make informed decisions and manage credit risk effectively. Customer segmentation employs neural networks to group customers based on shared characteristics, preferences, and behaviours. By analysing customer data such as demographics, purchase history, and online interactions, neural networks can identify distinct customer segments, tailor marketing strategies, and personalised product recommendations, enhancing customer engagement and satisfaction. Predictive maintenance utilizes neural networks to forecast equipment failures and schedule maintenance activities proactively. By analyzing sensor to-date equipment performance metrics and maintenance records, neural networks can detect anomalies, predict potential failures, and optimize maintenance schedules, minimizing downtime and reducing maintenance costs in industrial settings. Document analysis involves using neural networks to extract, classify, and analyze information from documents such as invoices, contracts, and forms. By processing text, images, and structured data, neural networks can automate document processing tasks, extract relevant information, and improve document management efficiency in various industries, including finance, legal, and healthcare. Stock trading employs neural networks to analyze market data, identify trading patterns, and make investment decisions. By processing historical stock prices, news articles, and market indicators, neural networks can predict price movements, identify trading opportunities, and optimize trading strategies, enabling traders to make informed investment decisions and maximize returns. Fraud detection utilizes neural networks to identify fraudulent activities and prevent financial losses in banking, e-commerce, and other industries. By analyzing transaction data, user behavior, and historical fraud patterns, neural networks can detect anomalies, flag suspicious transactions, and mitigate fraud risks, protecting businesses and customers from fraudulent activities. Network security employs neural networks to detect and mitigate cybersecurity threats such as malware, phishing attacks, and network intrusions. By analyzing network traffic, log files, and security events, neural networks can identify abnormal behavior, detect potential threats, and enhance threat detection capabilities, strengthening network defenses and protecting sensitive data. Personalized medicine utilizes neural networks to analyze genetic data, patient medical records, and clinical outcomes to tailor treatment plans and predict disease risks. By processing large-scale genomic data and healthcare records, neural networks can identify genetic markers, predict treatment responses, and optimize personalized healthcare interventions, improving patient outcomes and healthcare efficiency. Music recommendation systems use neural networks to analyze user preferences, listening habits, and music features to generate personalized playlists and recommendations. By processing music metadata, user interactions, and audio features, neural networks can recommend relevant songs, discover new artists, and enhance user engagement in music streaming platforms and applications. Investment analysis employs neural networks to analyze financial data, economic indicators, and market trends to evaluate investment opportunities and risks. By processing historical market data, company financials, and macroeconomic indicators, neural networks can predict asset prices, identify trading strategies, and support investment decision-making in finance and investment management. Advertising employs neural networks to analyze user demographics, interests, and online behavior to target ads and optimize campaigns. Processing and impressions, click-through rates, and conversion data, neural networks can identify target audiences, personalize ad content, and improve ad performance, maximizing advertising effectiveness and return on investment. Customer retention strategies utilize neural networks to analyze customer behavior, preferences, and feedback to identify at-risk customers and implement targeted retention campaigns. By processing customer data, purchase history, and interaction patterns, neural networks can predict customer churn, segment customer groups, and personalize retention efforts, improving customer loyalty and retention rates for businesses. Neural networks are harnessed in text summarization to condense large volumes of text into concise summaries. By analyzing the content and structure of documents, neural networks can identify key information, extract important sentences, and generate summaries that capture the essence of the original text, facilitating efficient information retrieval and comprehension. Knowledge discovery utilizes neural networks to uncover valuable insights and patterns from large datasets. By processing diverse data sources and extracting hidden relationships, neural networks can identify trends, discover hidden patterns, and generate actionable insights, empowering decision-making and innovation in various fields such as healthcare, finance, and research. Sentiment classification employs neural networks to analyze text data and classify sentiment polarity, such as positive, negative, or neutral. By processing textual features, linguistic patterns, and contextual clues, neural networks can accurately categorize text sentiments, enabling businesses to gauge customer opinions, sentiment trends, and brand perception, informing marketing strategies and customer engagement efforts. Content filtering utilizes neural networks to personalize content recommendations and filter out irrelevant or inappropriate content. By analyzing user preferences, browsing behavior, and content features, neural networks can recommend relevant content, detect spam or offensive material, and improve content curation and moderation in online platforms and applications. Speech recognition employs neural networks to convert spoken language into text. By processing audio signals, phonetic features, and language patterns, neural networks can transcribe speech accurately, enabling voice-controlled interfaces, virtual assistants, and automated transcription services, enhancing accessibility and user experience in various applications. Event detection utilizes neural networks to identify and classify events or anomalies in data streams. By analyzing sensor data, network traffic, or social media feeds, neural networks can detect unusual patterns, identify significant events, and trigger alerts or responses in real time, supporting applications such as surveillance, cybersecurity, and predictive maintenance. Traffic prediction employs neural networks to forecast traffic conditions, congestion levels, and travel times. By analyzing historical traffic data, weather conditions, and transportation patterns, neural networks can predict future traffic trends, optimize route planning, and improve traffic management and urban mobility. Market analysis utilizes neural networks to analyze financial data, market trends, and investor sentiment to predict asset prices and market movements. By processing historical market data, news articles, and economic indicators, neural networks can identify trading opportunities, forecast market trends, and support investment decision-making in finance and trading. Recommendation systems utilize neural networks to analyze user preferences, browsing behavior, and content features to deliver personalized recommendations and suggestions. By processing user interactions and content metadata, neural networks can recommend relevant products, articles, or media content, enhancing user engagement and satisfaction in e-commerce, media, and content platforms. Demand forecasting employs neural networks to predict future demand for products or services based on historical sales data, market trends, and external factors. By analyzing sales patterns, economic indicators, and consumer behavior, neural networks can forecast demand accurately, optimize inventory management, and improve supply chain efficiency in retail and manufacturing. Email classification utilizes neural networks to categorize incoming emails into different folders or labels based on their content or purpose. By analyzing email content, sender information, and metadata, neural networks can classify emails into categories such as primary, social, promotions, or spam, improving email organization and productivity for users. Sales prediction employs neural networks to forecast future sales volumes or revenues based on historical sales data, market trends, and promotional activities. By analyzing sales patterns, customer demographics, and marketing campaigns, neural networks can predict sales outcomes, optimize pricing strategies, and support sales planning and forecasting in retail and sales management. Risk assessment utilizes neural networks to evaluate and quantify risks associated with various activities, investments, or decisions. By processing relevant data sources and identifying risk factors, neural networks can assess risks accurately, prioritize risk mitigation measures, and inform decision-making processes in finance, insurance, and project management. Quality control employs neural networks to detect defects, anomalies, or deviations from desired standards in manufacturing processes or product quality. By analyzing sensor data, images, or inspection results, neural networks can identify quality issues, classify defects, and automate quality control inspections, ensuring product consistency and compliance with quality standards. Process optimization utilizes neural networks to improve efficiency, productivity, and performance in industrial processes or business operations. By analyzing process data, workflow patterns, and performance metrics, neural networks can identify bottlenecks, optimize resource allocation, and automate decision-making processes, enhancing productivity and competitiveness in various industries. Neuro-linguistic programming utilizes strategies for goal-setting achievement by helping individuals clarify their goals, develop action plans, and overcome obstacles. Techniques such as visualization and anchoring are used to reinforce positive outcomes and motivation. Perceptual positions in neuro-linguistic programming refer to the ability to adopt different perspectives or viewpoints. By viewing a situation from multiple perspectives, individuals can gain insight into their own behavior and the behavior of others, leading to improved communication and problem solving. Ecology in neuro-linguistic programming refers to the consideration of the wider consequences and implications of actions and decisions. It ensures that changes made through neuro-linguistic programming techniques are aligned with a person's values, beliefs, and overall well-being. Congruence and alignment in neuro-linguistic programming refer to the consistency between a person's thoughts, feelings, and actions. By achieving congruence and alignment, individuals can enhance their authenticity and effectiveness in communication and behavior. Techniques used in neuro-linguistic programming for resolving conflicts and improving relationships include reframing, negotiation, and rapport-building exercises. These techniques help individuals navigate challenging situations and foster positive interactions with others. Outcome specification in neuro-linguistic programming involves defining clear and achievable goals, including specific criteria for success. By specifying outcomes, individuals can focus their efforts and measure progress toward their desired results. Mirroring and matching are techniques used in neuro-linguistic programming to build rapport and establish connections with others. By subtly mimicking the body language, speech patterns, and gestures of another person, individuals can create a sense of familiarity and trust. Presuppositions in neuro-linguistic programming are underlying beliefs or assumptions that shape our perceptions and behaviours. By adopting empowering presuppositions, individuals can change their mindset and approach to challenges, leading to greater resilience and resourcefulness. Submodalities in neuro-linguistic programming refer to finer distinctions within our sensory experiences, such as visual images, sounds, and feelings. By exploring and manipulating these submodalities, individuals can change their perceptions and responses to stimuli. Pacing and leading in neuro-linguistic programming involve matching the current state or behavior of another person, which is pacing, and then gradually guiding them toward desired outcome, which is leading. This technique is used to build rapport and influence others effectively in communication. In neuro-linguistic programming, techniques for managing stress and anxiety include relaxation techniques such as deep breathing and visualization to promote a sense of calmness and relaxation. Neuro-linguistic programming also utilizes techniques like anchoring, where individuals associate a specific gesture or action with a positive state, allowing them to access that state whenever they need to manage stress or anxiety. The strategy model in neuro-linguistic programming refers to the step-by-step process individuals use to achieve a specific outcome or behavior. It involves identifying the sequence of mental and behavioral steps involved in performing a task or achieving a goal. By understanding the strategy model, individuals can optimize their approach and increase their chances of success. Neuro-linguistic programming utilizes techniques like reframing to change limiting beliefs by altering the way individuals perceive and interpret their experiences. Reframing involves viewing a situation from a different perspective or finding alternative meanings that empower individuals to overcome obstacles and achieve their goals. Sensory acuity and calibration. In neuro-linguistic programming, interventions involve developing heightened awareness of sensory cues, such as body language, tone of voice, and facial expressions. By calibrating to these cues, individuals can better understand others' perspectives and tailor their communication and behaviour accordingly. The neuro-linguistic programming meta-model is a set of linguistic patterns and techniques used to challenge limiting beliefs and clarify communication. It involves questioning and challenging vague language, generalizations and distortions to uncover underlying assumptions and beliefs that may be holding individuals back. Outcome specification in neuro-linguistic programming involves clearly defining desired outcomes and establishing specific criteria for success. By specifying outcomes, individuals can set clear goals and create actionable plans to achieve them, increasing their motivation and focus. In therapeutic settings such as counselling and psychotherapy, neuro-linguistic programming can be applied to help individuals overcome limiting beliefs, manage emotions, and improve communication skills. Neuro-linguistic programming techniques like reframing, anchoring, and parts integration are used to facilitate personal growth and positive change. Future pacing in neuro-linguistic programming involves mentally rehearsing future scenarios where individuals have achieved their goals, allowing them to experience the desired outcomes and reinforce their motivation and commitment to achieving them. Parts integration in neuro-linguistic programming is a technique used to resolve internal conflicts by integrating conflicting parts of the psyche into a harmonious whole. By acknowledging and honouring the positive intentions of each part, individuals can resolve inner conflicts and achieve greater alignment and congruence. Sensory acuity in neuro-linguistic programming is important for observing non-verbal cues such as body language, facial expressions, and tonality during communication. By developing sensory acuity, individuals can enhance their ability to understand others' perspectives and respond effectively in social interactions. The swish pattern in neuro-linguistic programming is a technique used to break undesirable habits or behaviours and replace them with more positive alternatives. It involves mentally visualising a desired outcome and associating it with a triggering stimulus, allowing individuals to reprogram their automatic responses and behaviours. Metaprograms in neuro-linguistic programming are mental filters or patterns that influence how individuals perceive and respond to the world around them. By understanding metaprograms, individuals can gain insight into their own behaviour and the behaviour of others, enabling them to communicate more effectively and build rapport. Techniques used in neuro-linguistic programming for reframing negative experiences involve changing the meaning or interpretation of past events to create more empowering perspectives. By reframing negative experiences, individuals can release limiting beliefs and emotions and move forward with greater confidence and resilience. Ecology in neurolinguistic programming refers to considering the wider consequences and implications of actions and decisions. It involves ensuring that changes made through neurolinguistic programming techniques are aligned with a person's values, beliefs, and overall well-being, promoting positive and sustainable outcomes. Perceptual positions in neurolinguistic programming refer to the ability to adopt different perspectives or viewpoints. By viewing a situation from multiple perceptual positions, individuals can gain insight into their own behaviour and the behaviour of others, leading to improved communication and problem solving. In outcome orientation in neurolinguistic programming is crucial for defining clear goals and objectives. By focusing on desired outcomes, individuals can establish specific criteria for success and create actionable plans to achieve them. This helps to maintain clarity and direction, guiding individuals toward their desired results. Deep learning algorithms are crucial in natural language processing tasks because they can automatically learn intricate patterns and representations from vast amounts of text data. These algorithms, often based on neural networks, enable neurolinguistic programming systems to understand and generate human-like language. For instance, in text classification tasks, deep learning models can learn to classify documents into different categories by analysing their content and context. Semantic analysis algorithms in neurolinguistic programming are designed to understand the meaning of text by extracting and interpreting the underlying semantics. These algorithms can identify relationships between words, phrases, or sentences, enabling neurolinguistic programming systems to comprehend the context and intent of the text. Examples include word embeddings, which represent words as dense vectors in a semantic space, and semantic role labeling, which identifies the roles of words in a sentence. Information retrieval algorithms play a crucial role in neurolinguistic programming systems by retrieving relevant documents or passages from large text corpora in response to user queries. These algorithms use techniques such as term frequency, inverse document frequency, and cosine similarity to rank documents based on their relevance to the query. By retrieving relevant information, neurolinguistic programming systems can provide more accurate and useful responses to user queries or tasks. Named entity recognition algorithms are used in neurolinguistic programming to identify and classify named entities, such as names of people, organizations, locations, and dates in text data. By recognizing named entities, neurolinguistic programming systems can extract valuable information and perform tasks such as information extraction, entity linking, and question answering more accurately and efficiently. Sentiment analysis algorithms in neurolinguistic programming are designed to analyze text data and determine the sentiment or emotional tone expressed within it. These algorithms can classify text as positive, negative, or neutral sentiment based on the language used and the context. Sentiment analysis is widely used in applications such as social media monitoring, customer feedback analysis, and brand sentiment analysis. Topic modeling algorithms are used in neurolinguistic programming to identify latent topics or themes within a collection of documents or text data. These algorithms, such as latent dirichlet allocation, cluster words into topics based on their co-occurrence patterns in documents. Topic modeling enables neurolinguistic programming systems to automatically discover the underlying themes or subjects present in large text corpora, facilitating tasks such as document summarization, content recommendation, and information retrieval. Neural network algorithms are at the forefront of advancing neurolinguistic programming technology due to their ability to learn complex patterns and representations from text data. These algorithms, including recurrent neural networks, convolutional neural networks, and transformer models, are used in various neurolinguistic programming tasks such as text classification, machine translation, named entity recognition, and sentiment analysis. Neural network algorithms enable neuro-linguistic programming systems to achieve state-of-the-art performance across a wide range of tasks. Sequence-to-sequence algorithms are used in neuro-linguistic programming for tasks that involve generating output sequences based on input sequences, such as machine translation, text summarization, and dialogue generation. These algorithms, often based on recurrent neural networks or transformer models, learn to map input sequences to output sequences by capturing the underlying relationships and dependencies between them. Sequence-to-sequence algorithms have significantly improved the performance of neuro-linguistic programming systems in tasks requiring sequence generation. Word embedding algorithms are used in neuro-linguistic programming to represent words as dense vectors in a continuous semantic space. These algorithms, such as Word2, Vec, and Glove, learn distributed representations of words based on their contextual usage in text data. Word embeddings capture semantic similarities between words and enable neuro-linguistic programming systems to better understand the meaning of text and perform tasks such as word analogy, text classification, and information retrieval. The clustering algorithms are used in neuro-linguistic programming to organize and summarize text data by grouping similar documents or passages together. These algorithms, such as k-means clustering and hierarchical clustering, partition text data into clusters based on their similarity or dissimilarity in terms of content or features. The clustering algorithms enable neuro-linguistic programming systems to automatically organize large text corpora, discover hidden patterns, and summarize information for further analysis or exploration. Tokenization is the process of breaking down text data into smaller units, such as words or subwords, called tokens. Tokenization is an essential pre-processing step in neuro-linguistic programming algorithms because it enables the analysis and manipulation of text at the token level. By tokenizing text data, neuro-linguistic programming systems can perform tasks such as text parsing, part-of-speech tagging, and named entity recognition more effectively. Graph-based algorithms are used in neuro-linguistic programming for text data analysis by representing text data as graphs and leveraging graph-based techniques for various tasks. These algorithms, such as graph-based ranking algorithms and graph neural networks, model relationships between words, sentences, or documents as nodes and edges in a graph structure. Graph-based algorithms enable neuro-linguistic programming systems to capture semantic relationships, perform link analysis, and extract valuable insights from text data. Attention mechanisms are used in neuro-linguistic programming to enhance the performance of neural network models by focusing on relevant parts of the input sequence during processing. These mechanisms, such as self-attention and multi-head attention, enable neural network models to weigh the importance of different input elements dynamically. Attention mechanisms have significantly improved the performance of neuro-linguistic programming algorithms in tasks such as machine translation, text summarization, and question answering. Developing effective neuro-linguistic programming algorithms for low-resource languages poses several challenges, including limited annotated data, linguistic diversity, and lack of resources for model training and evaluation. These challenges hinder the development and deployment of neuro-linguistic programming technologies for languages with fewer resources and support. Addressing these challenges requires innovative approaches, such as data augmentation, transfer learning, and cross-lingual modeling to adapt existing neuro-linguistic programming algorithms to low-resource language settings and improve their performance. Reinforcement learning algorithms are used in neuro-linguistic programming to improve conversational agents and dialogue systems by learning optimal strategies for interacting with users. These algorithms enable conversational agents to engage in natural and coherent conversations with users by learning from interaction experiences and feedback. Reinforcement learning algorithms have been applied to various neuro-linguistic programming tasks such as dialogue generation, response generation, and conversational recommendation, leading to more robust and engaging conversational agents. Syntax parsing algorithms are used in neuro-linguistic programming to analyze the grammatical structure of sentences and parse them into syntactic components such as phrases, clauses, and dependencies. These algorithms, such as constituency parsing and dependency parsing, enable neuro-linguistic programming systems to understand the syntactic relationships between words in a sentence and extract meaningful syntactic information. Syntax parsing algorithms are essential for tasks such as grammar checking, sentence generation, and syntactic analysis. Ensemble learning algorithms are used in neuro-linguistic programming to improve the robustness and accuracy of neuro-linguistic programming models by combining multiple base models or classifiers to make predictions. These algorithms, such as bagging, boosting, and stacking, leverage the diversity of individual models to reduce overfitting, increase generalization, and improve overall performance. Ensemble learning techniques are widely used in neuro-linguistic programming for tasks such as text classification, sentiment analysis, and named entity recognition to achieve state-of-the-art results. Light-of-mouth patterns in neuro-linguistic programming are linguistic techniques used to influence and persuade others. These patterns involve skillfully reframing objections, challenging limiting beliefs, and offering alternative perspectives to encourage behavioral change or acceptance of new ideas. Neuro-linguistic programming emphasizes the importance of ecology, which involves considering the broader consequences and ethical implications of interventions. This ensures that changes made through neuro-linguistic programming techniques are aligned with a person's values, beliefs, and overall well-being, promoting positive and sustainable outcomes. Techniques used in neuro-linguistic programming for building rapport and trust include mirroring and matching, where individuals subtly mimic the non-verbal behaviours of others to create a sense of connection and rapport. Active listening and empathy also play key roles in building trust and rapport in interpersonal interactions. Re-imprinting in neuro-linguistic programming refers to the process of revisiting and revising past memories or experiences to create more empowering beliefs and emotions. This therapeutic technique helps individuals release negative emotions and limiting beliefs associated with past experiences, leading to emotional healing and personal growth. Neuro-linguistic programming utilizes techniques like the Disney strategy for creative problem solving by adopting different perceptual positions, such as dreamer, realist, and critic. This helps individuals explore multiple perspectives and generate innovative solutions to challenges or obstacles they may encounter. Nested loops in neuro-linguistic programming refer to the process of embedding multiple stories or narratives within each other to facilitate therapeutic interventions. By using nested loops, therapists can create engaging and transformative experiences that lead to profound insights and personal change. Neuro-linguistic programming addresses the concept of perceptual positions, which involves adopting different perspectives or viewpoints to gain insight into one's own behaviour and the behaviour of others. By understanding perceptual positions, individuals can enhance their empathy, communication skills, and conflict resolution abilities. Techniques used in neuro-linguistic programming. For resolving internal conflicts and incongruence include parts integration, where conflicting aspects of the psyche are harmonized to promote inner alignment and emotional well-being. This helps individuals overcome internal resistance and achieve greater congruence between their thoughts, feelings, and actions. The SCORE model in neuro-linguistic programming is a framework for understanding human behavior based on the concepts of stimulus, response, outcome, and evaluation. By analysing these elements, individuals can gain insight into the factors influencing behaviour and identify opportunities for change and improvement. The pacing and leading in neuro-linguistic programming involve establishing rapport with others by matching their communication style and then subtly guiding them toward a desired outcome or behaviour. This technique helps build trust and influence others in a positive and persuasive manner. The Milton model in neuro-linguistic programming is a set of language patterns and techniques derived from the therapeutic work of Milton H. Erickson. These patterns are used to induce trance-like states, elicit unconscious responses, and facilitate persuasive communication without directly challenging resistance or objections. Neuro-linguistic programming addresses the concept of well-formed outcomes by helping individuals define clear, specific, and achievable goals that are congruent with their values and beliefs. By establishing well-formed outcomes, individuals can increase their motivation, focus, and likelihood of success in achieving their desired results. In neuro-linguistic programming, techniques for eliciting and changing criteria for decision-making involve identifying the unconscious factors that influence an individual's choices and preferences. By uncovering and understanding these criteria, individuals can adjust them to make more informed and effective decisions aligned with their goals and values. Meta-modeling in neuro-linguistic programming refers to the process of questioning and challenging the structure of language to uncover unconscious patterns of thinking and communication. By deconstructing vague or limiting language patterns, individuals can gain clarity and insight into their underlying beliefs and behaviours. The fast phobia cure in neuro-linguistic programming is a technique used to overcome fears and phobias by dissociating from the negative emotions associated with them. By systematically desensitizing oneself to the feared stimulus while maintaining a state of relaxation, individuals can reframe their perception and response to the phobia. Reframing in neuro-linguistic programming involves changing the context or meaning of a situation to shift perspectives and beliefs. By reframing negative or limiting interpretations, individuals can adopt more empowering and resourceful ways of thinking and behaving. The swish pattern in neuro-linguistic programming is a technique used for behaviour change by associating an undesirable behaviour or response with a more desirable one. By visualising a trigger image associated with the undesired behaviour and then swiftly replacing it with a preferred image, individuals can reprogram their automatic responses. Submodalities in neuro-linguistic programming refer to the finer distinctions within sensory experiences, such as visual images, sounds, and feelings. By understanding how these submodalities influence perception, individuals can modify their internal representations to change their emotional responses and behaviours. Re-imprinting in neuro-linguistic programming involves revisiting and revising past memories or experiences to create more empowering beliefs and emotions. This therapeutic technique helps individuals release negative emotions and limiting beliefs associated with past experiences, leading to emotional healing and personal growth. Nested loops in neuro-linguistic programming involve embedding multiple stories or narratives within each other to facilitate therapeutic interventions. By using nested loops, therapists can create engaging and transformative experiences that lead to profound insights and personal change. Perceptual positions in neuro-linguistic programming involve adopting different viewpoints or perspectives to gain insight into one's own behaviour and the behaviour of others. By understanding perceptual positions, individuals can enhance their empathy, communication skills, and conflict resolution abilities. Techniques for resolving internal conflicts and incongruence in neuro-linguistic programming include parts integration, where conflicting aspects of the psyche are harmonized to promote inner alignment and emotional well-being. This helps individuals overcome internal resistance and achieve greater congruence between their thoughts, feelings, and actions. The SCORE model in neuro-linguistic programming is a framework for understanding human behaviour based on the concepts of stimulus, response, outcome, and evaluation. By analysing these elements, individuals can gain insight into the factors influencing behaviour and identify opportunities for change and improvement. The reframe pattern in neuro-linguistic programming involves changing the meaning or interpretation of a situation to create more empowering beliefs and perspectives. By reframing limiting beliefs or negative experiences, individuals can release emotional blocks and adopt more resourceful ways of thinking and behaving. The Milton model in neuro-linguistic programming is a set of language patterns named after the renowned therapist Milton Erickson. These patterns are designed to induce a trance-like state in the listener, making them more receptive to suggestions and influencing their behavior. By using vague language, metaphors, and presuppositions, practitioners can communicate in a way that bypasses the critical conscious mind, allowing for deeper persuasion and persuasion. Well-formed outcomes in neurolinguistic programming refer to goals that are clearly defined, achievable, and aligned with a person's values and beliefs. By setting well-formed outcomes, individuals can increase their motivation and focus towards achieving their desired objectives, leading to greater success and fulfillment. Techniques for eliciting and changing criteria for decision-making in neurolinguistic programming involve understanding the unconscious factors that influence a person's choices and preferences. By identifying and modifying these criteria, individuals can make more effective decisions aligned with their goals and values, leading to better outcomes and results. The fast phobia cure in neurolinguistic programming is a technique used to overcome fears and phobias by dissociating from the negative emotions associated with them. By systematically desensitizing oneself to the feared stimulus while maintaining a state of relaxation, individuals can reframe their perception and response to the phobia, leading to lasting change and emotional freedom. The swish pattern in neurolinguistic programming is a technique used for behavior change by associating an undesirable behavior or response with a more desirable one. By visualizing a trigger image associated with the undesired behavior and then swiftly replacing it with a preferred image, individuals can reprogram their automatic responses, leading to positive behavior change and personal growth. Calibration in neurolinguistic programming involves developing heightened sensory awareness to detect subtle changes in behavior and physiology during interpersonal interactions. This allows individuals to accurately read and interpret non-verbal cues, facilitating effective communication and rapport building, leading to stronger connections and understanding. Perceptual positions in neurolinguistic programming involve adopting different viewpoints or perspectives to gain insight into one's own behavior and the behavior of others. By understanding perceptual positions, individuals can enhance their empathy, communication skills, and conflict resolution abilities, leading to better relationships and personal development. In neurolinguistic programming, resolving internal conflicts and incongruence involves techniques like parts integration and timeline therapy. Parts integration helps individuals reconcile conflicting aspects of themselves by understanding the positive intentions behind each part and integrating them into a harmonious whole. Timeline therapy allows individuals to revisit past experiences, reframe them, and align them with their present goals, resolving inner conflicts and incongruence. Neurolinguistic programming utilizes the reframe pattern to change limiting beliefs by shifting perspectives and interpretations, by reframing negative or disempowering beliefs into more positive and empowering ones. Individuals can overcome self-imposed limitations and achieve greater success and fulfillment in life. Metamodeling in neurolinguistic programming is a process of questioning and challenging the structure of language to uncover unconscious patterns of thinking and communication. By examining and reframing vague or limiting language patterns, individuals can gain clarity and insight into their underlying beliefs and behaviours, leading to personal growth and transformation. The fast phobia cure in neurolinguistic programming is a technique used to overcome fears and phobias by dissociating from the negative emotions associated with them. By systematically desensitizing oneself to the feared stimulus while maintaining a state of relaxation, individuals can reframe their perception and response to the phobia, leading to lasting change and emotional freedom. Techniques for building rapport and trust in neurolinguistic programming include mirroring and matching, where individuals subtly synchronize their behaviors with those of others to create a sense of connection and rapport. Active listening and empathy also play key roles in building trust and rapport in interpersonal interactions, leading to stronger relationships and better communication. Calibration in neurolinguistic programming involves finely tuning one's sensory acuity to detect subtle changes in another person's behaviour and physiology. It's like being able to read between the lines of non-verbal communication cues, such as changes in posture, breathing patterns, or micro-expressions on someone's face. By calibrating to these signals, practitioners can gain deeper insights into a person's state of mind, emotions, and intentions, allowing for more effective communication and rapport building. Nested loops in neurolinguistic programming are a therapeutic technique used to address complex issues or conflicts by exploring multiple layers of meaning and understanding. It's like unraveling a series of interrelated stories or experiences, each nested within the other. By navigating through these nested loops, practitioners can help clients uncover hidden patterns, beliefs, or emotions that may be contributing to their challenges, leading to deeper insights and resolution. Perceptual positions in neurolinguistic programming refer to different perspectives from which individuals can view a situation or experience. These positions include first person seeing things from one's own perspective, second person seeing things from another person's perspective, and third person seeing things from an observer's perspective. By shifting between these positions, individuals can gain a more comprehensive understanding of a situation and its impact on themselves and others, leading to greater empathy and communication effectiveness. Techniques for resolving internal conflicts and incongruence in neurolinguistic programming include parts integration, timeline therapy, and visual squash. These techniques help individuals reconcile conflicting beliefs, values, or emotions by aligning them with their deeper desires and goals. By resolving internal conflicts and achieving congruence, individuals can experience greater inner harmony and personal fulfillment. The SCORE model in neurolinguistic programming is a framework for understanding behaviour by examining the stimulus, cause, organism, response, and effect. It helps practitioners identify the factors that influence behaviour and its outcomes, allowing for a deeper understanding of human psychology and motivation. Reframing in neurolinguistic programming involves changing the context or meaning of a situation to shift perspectives and beliefs. By reframing negative or limiting interpretations, individuals can adopt more empowering and resourceful ways of thinking and behaving, leading to greater confidence and resilience. Pacing and leading in neurolinguistic programming involves establishing rapport with someone by matching their behaviours, such as their tone of voice or body language, and then gradually guiding them towards a desired outcome or behaviour. By initially mirroring the other person's behaviour, you create a sense of connection and trust, making it easier to influence them positively towards the intended goal. Neurolinguistic programming addresses the concept of well-formed outcomes by guiding individuals in setting clear, achievable, and ecologically sound goals. Well-formed outcomes consider various factors such as specificity, measurability, achievability, relevance, and ecological compatibility, ensuring that goals are aligned with personal values and have a positive impact on all areas of life. Techniques for eliciting and changing criteria for decision-making in neurolinguistic programming involve identifying and modifying the unconscious factors that influence a person's choices and preferences. By eliciting and reshaping these criteria, individuals can make more effective decisions aligned with their goals and values, leading to better outcomes and results. Metamodeling in neurolinguistic programming is a process of questioning and challenging the structure of language to uncover unconscious patterns of thinking and communication. By examining and reframing vague or limiting language patterns, individuals can gain clarity and insight into their underlying beliefs and behaviours, leading to personal growth and transformation. The fast phobia cure in neurolinguistic programming is a technique used to overcome fears and phobias by dissociating from the negative emotions associated with them. By systematically desensitizing oneself to the feared stimulus while maintaining a state of relaxation, individuals can reframe their perception and response to the phobia, leading to lasting change and emotional freedom. Reframing in neurolinguistic programming involves changing the context or meaning of a situation to shift perspectives and beliefs. By reframing negative or limiting interpretations, individuals can adopt more empowering and resourceful ways of thinking and behaving, leading to greater confidence and resilience. The swish pattern in neuro-linguistic programming is a technique used for behaviour change by associating an undesirable behaviour or response with a more desirable one. By visualising a trigger image associated with the undesired behaviour and then swiftly replacing it with a preferred image, individuals can reprogram their automatic responses, leading to positive behaviour change and personal growth. Submodalities in neuro-linguistic programming refer to the finer distinctions within sensory experiences, such as visual images, sounds, and feelings. By understanding how these submodalities influence perception, individuals can modify their internal representations to change their emotional responses and behaviours, leading to personal transformation and empowerment. In neuro-linguistic programming, techniques for building rapport and trust involve mirroring and matching the other person's body language, tone of voice, and speech patterns. By subtly synchronizing with the other person's communication style, practitioners can create a sense of connection and understanding, fostering trust and rapport in the interaction. Re-imprinting in neuro-linguistic programming is a therapeutic technique used to revisit and reframe past experiences that have had a significant impact on a person's beliefs or behaviours. By revisiting these memories from a new perspective and incorporating positive resources and learnings, individuals can rewrite their internal narrative, leading to emotional healing and personal growth. The Disney strategy in neuro-linguistic programming is a creative problem-solving technique inspired by Walt Disney's creative process. It involves adopting 3 different perceptual positions: the dreamer, the realist, and the critic. By shifting between these positions, individuals can explore a challenge from multiple perspectives, sparking creativity and generating innovative solutions. Calibration in neuro-linguistic programming refers to the ability to detect subtle changes in another person's behaviour and physiology. By finely tuning one's sensory acuity and observing micro-expressions, body language, and voice tone, practitioners can gain deeper insights into the other person's state of mind and emotional responses, enhancing communication and understanding. Nested loops in neuro-linguistic programming are a therapeutic technique used to address complex issues or conflicts by exploring multiple layers of meaning and understanding. By navigating through nested loops of conversation, individuals can uncover hidden patterns, beliefs, or emotions that may be contributing to their challenges, leading to deeper insights and resolution. Perceptual positions in neuro-linguistic programming refer to different perspectives from which individuals can view a situation or experience. By shifting between these positions, first person, second person, and third person, individuals can gain a more comprehensive understanding of a situation and its impact on themselves and others, leading to greater empathy and communication effectiveness. Techniques for resolving internal conflicts and incongruent neuro-linguistic programming include parts integration, timeline therapy, and visual squash. These techniques help individuals reconcile conflicting beliefs, values, or emotions by aligning them with their deeper desires and goals, leading to greater inner harmony and personal fulfillment. The SCORE model in neuro-linguistic programming is a framework for understanding behaviour by examining the stimulus, because organism, response, and effect. It helps practitioners identify the factors that influence behaviour and its outcomes, allowing for a deeper understanding of human psychology and motivation. Neuro-linguistic programming addresses the concept of well-formed outcomes by guiding individuals in setting clear, achievable, and ecologically sound goals. Well-formed outcomes consider various factors such as specificity, measurability, achievability, relevance, and ecological compatibility, ensuring that goals are aligned with personal values and have a positive impact on all areas of life. Techniques for eliciting and changing criteria. The decision-making in neuro-linguistic programming involve identifying and modifying the unconscious factors that influence a person's choices and preferences. By eliciting and reshaping these criteria, individuals can make more effective decisions aligned with their goals and values, leading to better outcomes and results. In the context of artificial intelligence, the theory of mind refers to the ability of AI systems to understand and attribute mental states to themselves and others, similar to how humans perceive and interpret the thoughts, intentions, beliefs, desires, and emotions of themselves and those around them. This capability enables AI systems to engage in more sophisticated social interactions, predict the behaviour of other agents, and demonstrate empathy in certain contexts. AI systems with theory of mind capabilities can understand mental states not only in others but also in themselves. This self-awareness aspect allows them to recognize their own beliefs, intentions, and emotions, which can influence their decision-making processes and interactions with other agents. The attribution of mental states is crucial for AI's ability to predict behavior because it provides insight into the underlying motivations, intentions, and desires driving the actions of other agents. By inferring the mental states of others, AI systems can anticipate how individuals are likely to behave in different situations and adjust their own actions accordingly. AI systems infer the mental states of other agents through various means, including analysing observable behaviours, interpreting verbal and non-verbal cues, and applying probabilistic reasoning or machine learning algorithms to predict the most likely mental states given the available evidence. While AI systems with theory of mind capabilities may demonstrate empathy in certain contexts, it's important to note that this empathy is typically simulated rather than genuine. These systems can recognize and respond to emotions expressed by humans, but their understanding is based on predefined rules or learned patterns rather than genuine emotional understanding. Examples of mental states that AI systems with theory of mind can recognize include beliefs, which is what an agent thinks is true or false, intentions, which is what an agent intends to do, desires, which is what an agent wants or prefers, and emotions, which is how an agent feels. The challenges in developing AI systems with theory of mind capabilities include the complexity of human cognition, the ambiguity and variability of human behaviour, the need for robust and interpretable algorithms, and the ethical considerations surrounding privacy, consent, and manipulation. AI systems with theory of mind capabilities can contribute to collaborative tasks by understanding the intentions, goals, and preferences of other agents and coordinating their actions accordingly. This can lead to more effective teamwork and cooperation in settings where multiple agents need to work together towards a common goal. Ethical considerations when developing AI systems with theory of mind capabilities include ensuring privacy and consent in data collection and analysis, preventing manipulation or exploitation of vulnerable individuals, promoting transparency and accountability in decision-making processes, and addressing potential biases or discrimination in predictions and recommendations. AI systems with theory of mind capabilities can benefit human-robot interaction by enhancing the robot's ability to understand and respond to human intentions, emotions, and preferences. This can lead to more natural and intuitive interactions, improved collaboration between humans and robots, and increased acceptance and trust in robotic systems. AI systems can interpret non-verbal cues such as facial expressions, body language, tone of voice, and gestures to infer the mental states of other agents. By analysing these cues in combination with contextual information, AI systems can make more accurate predictions about the intentions, emotions, and beliefs of other agents. Advancing theory of mind in AI involves research areas such as cognitive psychology, neuroscience, machine learning, natural language processing, effective computing, and human-robot interaction. Researchers are exploring new algorithms, models, and data sets to improve AI's understanding of human cognition and behaviour. AI systems with theory of mind capabilities adapt to changes in an agent's mental states by continuously monitoring and updating their beliefs, intentions, and predictions based on new evidence or feedback from the environment. This adaptability allows them to maintain accurate mental state models and make appropriate adjustments to their behaviour and dynamic social context. AI systems with theory of mind capabilities can indeed understand and respond to emotions by analysing various cues such as facial expressions, tone of voice, and body language. These systems can infer the emotional states of other agents and adjust their responses accordingly. For example, a virtual assistant equipped with theory of mind capabilities might recognise when a user is feeling frustrated and respond with empathy and assistance. The implications of theory of mind for personalised recommendation systems are significant. By understanding the preferences, interests, and goals of individual users, AI systems can tailor recommendations more effectively. For instance, a streaming service with theory of mind capabilities might recommend movies or TV shows based not only on past viewing history, but also on the user's current mood or emotional state. AI systems with theory of mind capabilities may encounter situations where different agents hold conflicting mental states. In such cases, these systems must reconcile these conflicts and make decisions accordingly. For example, in a collaborative task involving multiple agents, a robot with theory of mind capabilities might need to navigate conflicting preferences or goals to achieve a mutually beneficial outcome. Predicting the intentions of other agents accurately is a crucial aspect of theory of mind in AI systems. By analysing contextual information, historical data, and observable behaviours, these systems can make educated guesses about what other agents are likely to do next. This ability is essential for effective communication, collaboration, and coordination between different agents in various contexts. There are potential risks associated with AI systems misunderstanding or misinterpreting mental states. For example, if a virtual assistant misinterprets a user's emotional state and responds inappropriately, it could lead to frustration or mistrust. Additionally, misattributing mental states could result in biased or discriminatory decisions, especially in sensitive domains such as hiring or healthcare. AI systems with theory of mind capabilities learn to attribute mental states to different agents through a combination of supervised learning, reinforcement learning, and unsupervised learning techniques. They analyse data from interactions with other agents, including feedback and outcomes, to refine their models of mental states and improve their predictive accuracy over time. Recognising and responding to deception is a challenging task for AI systems with theory of mind capabilities. These systems must analyse subtle cues and patterns in behaviour to detect signs of deception accurately. For example, a chatbot with theory of mind capabilities might detect inconsistencies in a user's responses and adjust its conversational strategy accordingly. Natural language processing plays a vital role in developing theory of mind in AI by enabling systems to understand and generate human-like language. Through techniques such as sentiment analysis, named entity recognition, and semantic parsing, AI systems can extract valuable information about mental states from textual data and use it to inform their decision-making processes. AI systems distinguish between different types of mental states, such as beliefs and desires, through careful analysis of contextual cues and behavioural patterns. For example, a self-driving car with theory of mind capabilities might infer a pedestrian's belief that it is safe to cross the street based on their posture and gaze direction. Theory of mind has significant implications for AI systems' ability to understand cultural differences. By recognising and respecting diverse cultural norms, values, and communication styles, these systems can adapt their behaviour more effectively in multicultural environments. For example, a language translation system with theory of mind capabilities might adjust its output based on the cultural context of the target audience. AI systems with theory of mind capabilities can adapt their behaviour based on feedback from humans by incorporating this feedback into their learning algorithms. For example, a virtual assistant might learn to provide more helpful responses to user queries by analysing feedback ratings and adjusting its response generation strategy accordingly. Handling uncertainty and inferring mental states is a fundamental challenge for AI systems with theory of mind capabilities. These systems must account for ambiguity, noise, and incomplete information in their models of other agents' mental states and make decisions robustly in the face of uncertainty. Cognitive modeling approaches, such as Bayesian inference neural networks and probabilistic graphical models, are used to develop theory of mind in AI. These approaches enable AI systems to represent and reason about mental states in a flexible and adaptive manner, incorporating uncertainty and learning from experience. AI systems with theory of mind capabilities can anticipate the future actions of other agents by simulating different scenarios and predicting the most likely outcomes based on their models of mental states and behaviour. This ability is essential for proactive decision-making and planning in dynamic environments. Some limitations of current AI systems' theory of mind capabilities include their reliance on simplified models of human cognition, their difficulty in handling complex social dynamics and interactions, and their susceptibility to biases and errors in mental state attribution. Additionally, these systems may struggle with generalizing to new or unseen situations outside their training data. AI systems with theory of mind interpret ambiguous social cues by analyzing contextual information, previous interactions, and behavioral patterns. They use probabilistic reasoning and machine learning techniques to infer the most likely mental states based on available evidence. For example, a virtual assistant might interpret a user's vague request by considering their past preferences, recent activities, and the current context to provide a relevant response. Artificial intelligence systems with theory of mind can adapt their behaviour based on changes in social context by continuously updating their models of other agents' mental states. They monitor feedback and adjust their strategies accordingly to maintain effective communication and collaboration. For instance, a collaborative robot might modify its task allocation strategy in response to changes in team dynamics or environmental conditions to achieve better outcomes. Machine learning plays a crucial role in developing theory of mind in AI by enabling systems to learn from data and experience. Supervised learning, reinforcement learning, and unsupervised learning techniques are used to train models that can infer mental states, predict behaviour, and adapt to changing social dynamics. By analysing large data sets of social interactions, AI systems can learn to recognise patterns and generalise to new situations. These systems with theory of mind handle conflicting goals between different agents by balancing competing objectives and negotiating mutually beneficial solutions. They consider the preferences, priorities, and constraints of all involved parties to reach consensus or compromise. For example, a negotiation agent might adjust its bargaining strategy based on the perceived importance of conflicting goals and the potential for cooperation. These systems with theory of mind recognise and respond to social norms by incorporating cultural norms, conventions, and expectations into their decision-making processes. They analyse contextual cues and historical data to infer the implicit rules governing social interactions and adjust their behaviour accordingly. For instance, a conversational agent might avoid sensitive topics or use polite language to adhere to social norms and avoid causing offence. The implications of theory of mind for AI systems' understanding of intentionality are significant. By recognising that other agents have beliefs, desires, and intentions that guide their actions, these systems can make more accurate predictions about behaviour and engage in more effective communication and collaboration. For example, a collaborative robot might anticipate a human partner's goals and proactively offer assistance to support their intentions. AI systems with theory of mind handle situations where mental states are concealed by inferring underlying motivations and intentions from observable behaviour and contextual cues. They use probabilistic reasoning and predictive modelling to generate hypotheses about concealed mental states and update their beliefs based on new evidence. For example, a sentiment analysis system might infer a user's emotional state from their writing style and linguistic cues. AI systems with theory of mind capabilities can distinguish between different levels of trustworthiness in other agents by analysing past interactions, reputation signals, and social cues. They assess factors such as reliability, consistency, and honesty to determine the credibility of information and the reliability of other agents. For instance, a recommendation system might give more weight to reviews from trusted sources or users with a history of accurate feedback. Strategies AI systems can use to mitigate biases in attributing mental states include incorporating diverse perspectives, considering multiple sources of evidence, and actively monitoring and correcting for cognitive biases. They can also employ techniques such as counterfactual reasoning and sensitivity analysis to evaluate the robustness of their predictions and identify potential sources of bias. AI systems' theory of mind interpret indirect communication and implied meanings by analysing contextual cues, linguistic patterns, and social conventions. They infer underlying intentions and beliefs from subtle hints and indirect references, taking into account the speaker's perspective and the context of the conversation. For example, a language processing system might recognise sarcasm or irony by detecting incongruities between literal meaning and implied intent. AI systems with theory of mind accurately interpret sarcasm and humour by analysing contextual cues, linguistic patterns, and social dynamics. They recognise incongruities between literal meaning and intended meaning and infer the speaker's underlying attitudes and emotions. For example, a sentiment analysis system might detect humour by identifying positive emotions and playful language cues in text. Effective computing plays a crucial role in developing theory of mind in AI by enabling systems to recognise, interpret, and respond to human emotions. By analysing physiological signals, facial expressions, vocal intonations, and other affective cues, AI systems can infer emotional states and adjust their behaviour accordingly. For example, a virtual assistant might use effective computing techniques to detect user frustration and respond with empathy and support. AI systems with theory of mind handle situations where agents have conflicting beliefs by reconciling divergent viewpoints and finding common ground. They engage in dialogue, negotiation, and persuasion to resolve disagreements and reach consensus. For example, a decision support system might facilitate collaborative decision-making by presenting conflicting evidence and encouraging discussion among stakeholders. Practical applications of theory of mind in AI outside of human-robot interaction include personalised recommendation systems, customer service chatbots, collaborative decision-making tools, and virtual assistants for mental health support. These systems leverage theory of mind capabilities to understand user preferences, anticipate needs, and tailor interactions to individual characteristics and goals. These systems with theory of mind handle situations where agents have hidden agendas by inferring underlying motivations and goals from observable behaviour and contextual cues. They use probabilistic reasoning and predictive modelling to generate hypotheses about hidden intentions and update their beliefs based on new evidence. For example, a negotiation agent might anticipate hidden agendas by analysing past negotiation tactics and detecting patterns of deceptive behaviour. AI systems with theory of mind recognise and respond to changes in an agent's priorities by monitoring behavioural cues, contextual information, and explicit communication. They adapt their strategies and responses based on perceived shifts in priorities to maintain effective collaboration and achieve shared goals. For instance, a collaborative planning system might adjust its task allocation strategy in response to changes in team members' stated preferences or objectives. Reinforcement learning plays a significant role in developing theory of mind in AI by enabling systems to learn from interactions with other agents and the environment. AI systems use reinforcement learning techniques to model the intentions, beliefs, and preferences of other agents and predict their future behaviour. By optimizing their decision-making strategies based on feedback and rewards, These systems can improve their ability to infer mental states and anticipate the actions of other agents. They interpret the intentions behind an agent's actions by analysing contextual cues, behavioural patterns, and explicit communication. They infer underlying goals, desires, and beliefs from observable behaviour and use predictive modelling to anticipate future actions. For example, a collaborative robot might interpret human partners' gestures as signalling an intention to pass an object and adjust its own actions accordingly. These systems with theory of mind recognise and respond to social cues in different cultural contexts by incorporating cultural norms, conventions, and expectations into their decision-making processes. They analyse contextual cues and historical data to infer the implicit rules governing social interactions and adjust their behaviour accordingly. For instance, a conversational agent might adapt its communication style and topics of conversation to align with cultural norms and avoid causing offence. Strategies AI systems can use to improve their accuracy in inferring mental states include incorporating diverse perspectives, considering multiple sources of evidence, and actively monitoring and correcting for cognitive biases. They can also employ techniques such as counterfactual reasoning and sensitivity analysis to evaluate the robustness of their predictions and identify potential sources of bias. These AI systems with theory of mind handle situations where agents have incomplete or contradictory information by reconciling divergent viewpoints and finding common ground. They engage in dialogue, negotiation, and persuasion to resolve disagreements and reach consensus. For example, a decision support system might facilitate collaborative decision-making by presenting conflicting evidence and encouraging discussion among stakeholders. AI systems with theory of mind can adapt their behaviour based on changes in an agent's beliefs by monitoring feedback, updating their mental models of other agents, and adjusting their strategies accordingly. They assess factors such as credibility, reliability, and consistency to determine the impact of belief changes on decision-making and interaction. For instance, a collaborative planning system might revise its predictions and plans in response to new information or updates from other agents. The implications of theory of mind for AI systems' understanding of moral reasoning are significant. By recognizing that other agents have beliefs, desires, and intentions that guide their actions, these systems can make more ethical decisions and engage in more morally responsible behavior. For example, an autonomous vehicle might prioritize the safety and well-being of pedestrians and other road users by anticipating their intentions and adjusting its driving behavior accordingly. AI systems with theory of mind handle situations where agents have conflicting desires by balancing competing objectives and negotiating mutually acceptable solutions. They consider the preferences, priorities, and constraints of all involved parties to reach consensus or compromise. For example, a negotiation agent might mediate between conflicting parties by identifying common interests and proposing trade-offs that satisfy everyone's desires to some extent. AI systems with theory of mind recognize and respond to changes in an agent's emotional expression by analyzing facial expressions, vocal intonations, and other affective cues. They adapt their communication style, tone, and responses based on the perceived emotional state of other agents to maintain effective interaction and support. For instance, a virtual assistant might offer comforting responses or empathetic gestures in response to user expressions of distress or sadness. Challenges in evaluating the performance of AI systems with theory of mind capabilities include assessing the accuracy of mental state inferences, measuring the effectiveness of adaptive behaviour, and evaluating the impact on collaborative outcomes. Evaluating theory of mind requires considering factors such as predictive accuracy, computational efficiency, and real-world applicability. For instance, a simulated social interaction environment might be used to assess the ability of AI systems to infer mental states and engage in effective collaboration with human users. AI systems with theory of mind interpret the social dynamics of group interactions by analysing the behaviour, communication patterns, and relationships among different agents. They consider factors such as social roles, power dynamics, and group norms to understand the underlying dynamics and interactions. For example, in a collaborative work environment, an AI system might observe patterns of leadership, cooperation, and conflict resolution to adapt its own behaviour and contribute effectively to group tasks. AI systems with theory of mind can adapt their behaviour based on changes in an agent's personality by recognising shifts in behavioural cues, communication style, and preferences. They use predictive modelling and probabilistic reasoning to infer changes in personality traits and adjust their interactions accordingly. For instance, in a virtual assistant context, if a user's communication style becomes more formal or casual over time, the AI system might adjust its responses to match the user's evolving preferences. The theory of mind has significant implications for AI systems' understanding of deception and manipulation. By recognising that other agents may have hidden intentions or agendas, these systems can anticipate potential deception and take appropriate precautions. They analyse behavioural cues, inconsistencies in communication, and contextual information to detect signs of manipulation or dishonesty. For example, in a cybersecurity context, an AI system might identify suspicious patterns of behaviour that indicate attempted fraud or malicious activity. AI systems with theory of mind handle situations where agents have conflicting emotions by recognising and reconciling divergent feelings and motivations. They analyse facial expressions, vocal intonations, and other effective cues to infer changes in emotional states and adjust their responses accordingly. For instance, in a mental health support context, an AI system might detect signs of ambivalence or mixed emotions in a user's speech and offer empathetic responses to address their conflicting feelings. AI systems with theory of mind recognise and respond to changes in an agent's level of trust by monitoring behavioural cues, communication patterns, and past interactions. They adapt their behaviour based on perceived shifts in trustworthiness to maintain effective collaboration and communication. For example, in a human-robot teamwork scenario, if a human teammate expresses skepticism or distrust towards the robot's capabilities, the AI system might prioritise building rapport and demonstrating reliability to regain trust. Strategies AI systems can use to learn from interactions with humans and other agents include active listening, observation, feedback analysis, and iterative refinement. They engage in dialogue, collaboration, and knowledge exchange to gather information, refine their mental models, and improve their predictive accuracy. For instance, in a conversational agent context, an AI system might track user feedback and adjust its responses to better meet user needs and preferences over time. AI systems with theory of mind handle situations where agents have hidden motives by inferring underlying intentions and goals from observable behaviour and contextual cues. They use probabilistic reasoning and predictive modelling to generate hypotheses about hidden motives and update their beliefs based on new evidence. For example, in a negotiation scenario, an AI system might identify hidden motives such as financial incentives or strategic alliances and adjust its negotiation strategy accordingly. AI systems with theory of mind recognise and respond to changes in an agent's cultural background by incorporating cultural norms, conventions, and expectations into their decision-making processes. They analyse contextual cues and historical data to infer the implicit rules governing social interactions and adjust their behaviour accordingly. For instance, in a customer service context, an AI system might adapt its communication style and service offerings to align with cultural preferences and avoid causing offence. Cognitive neuroscience plays a crucial role in informing the development of theory of mind in AI by providing insights into the underlying mechanisms of human cognition, social perception, and interpersonal communication. Researchers draw on theories and findings from cognitive neuroscience to design computational models and algorithms that simulate human-like reasoning, inference, and social interaction. For example, neuroimaging studies might identify brain regions associated with theory of mind tasks, guiding the development of AI systems that mimic similar cognitive processes. AI systems with theory of mind interpret the social hierarchies present in human societies by analysing patterns of authority, influence, and status within social groups. They recognise roles such as leaders, followers, and subordinates and infer the dynamics of power and prestige based on observed behaviour and communication. For instance, in a team collaboration setting, an AI system might identify informal leaders or opinion leaders within the group and adapt its interaction strategies accordingly to facilitate effective communication and decision-making. AI systems with theory of mind can adapt their behaviour based on changes in an agent's level of cooperation by monitoring cooperative cues, communication patterns, and past interactions. They adjust their strategies and responses based on perceived shifts in cooperativeness to maintain effective collaboration and achieve shared goals. For example, in a multi-agent game scenario, if a teammate becomes less cooperative or competitive, the AI system might adjust its own behaviour to maintain balance and avoid conflict. The theory of mind has profound implications for AI systems' understanding of empathy and compassion. By recognising and empathising with the emotions, perspectives, and needs of other agents, these systems can engage in more compassionate and supportive interactions. They analyse effective cues, verbal expressions, and situational context to infer emotions and respond with empathy. For example, in a virtual therapy context, an AI system might offer empathetic responses and validation to support users experiencing distress or emotional challenges. AI systems with theory of mind handle situations where agents have conflicting priorities by identifying shared goals, negotiating trade-offs, and finding mutually acceptable solutions. They consider factors such as preferences, constraints, and resource availability to balance competing objectives and resolve conflicts. For example, in a resource allocation scenario, an AI system might prioritise tasks based on their importance, urgency, and impact, taking into account conflicting priorities among different stakeholders. AI systems with theory of mind recognise and respond to changes in an agent's level of engagement by monitoring behavioural cues, communication patterns, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in engagement to maintain effective collaboration and communication. For example, in an online learning context, an AI tutor might adjust its pacing, content, and feedback based on the student's level of attention and participation to maximise learning outcomes. Strategies AI systems can use to handle situations where agents have conflicting values include facilitating dialogue, negotiation, and compromise to find common ground and reconcile divergent perspectives. They engage in value-sensitive decision-making, ethical reasoning, and moral deliberation to navigate complex ethical dilemmas and trade-offs. For example, in a healthcare decision support context, an AI system might consider patients' values, preferences, and cultural beliefs when recommending treatment options, balancing medical efficacy with patient autonomy and well-being. AI systems with theory of mind interpret the social norms and conventions of different cultures by analysing patterns of behaviour, communication styles, and contextual cues within specific cultural contexts. They recognise cultural norms, values, and expectations and adapt their behaviour accordingly to facilitate effective communication and collaboration. For example, in a cross-cultural communication scenario, an AI system might adjust its language, gestures, and interaction style to align with the cultural preferences and sensitivities of different communities. AI systems with theory of mind can adapt their behaviour based on changes in an agent's emotional state by recognising effective cues, verbal expressions, and non-verbal signals associated with different emotions. They use predictive modelling and probabilistic reasoning to infer shifts in emotional states and adjust their responses accordingly to provide appropriate support and assistance. For instance, in a mental health support context, an AI system might offer empathetic responses and coping strategies tailored to address fluctuations in emotional well-being. Theory of mind has significant implications for AI systems' understanding of cooperation and collaboration by enabling them to recognize, anticipate, and respond to the intentions, goals, and preferences of other agents. They analyze social cues, communication patterns, and past interactions to infer the underlying dynamics of cooperation and adjust their behavior to promote effective collaboration and achieve shared goals. For example, in a team project context, an AI system might coordinate tasks, allocate resources, and facilitate communication to foster cooperation and productivity among team members. AI systems with theory of mind handle situations where agents have hidden emotions by recognizing subtle cues, inconsistencies in behavior, and contextual information that suggest underlying emotional states. They use probabilistic reasoning and predictive modeling to infer hidden emotions and adjust their responses accordingly to provide empathetic support and understanding. For example, in a customer service context, an AI system might detect signs of emotional distress or frustration in a user's speech and offer empathetic responses and problem-solving assistance. AI systems with theory of mind recognize and respond to changes in an agent's level of satisfaction by monitoring behavioral cues, communication patterns, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in satisfaction to maintain effective engagement and address user needs and preferences. For example, in a customer feedback scenario, an AI system might track changes in satisfaction ratings and adjust its service offerings or communication style to enhance user experience and satisfaction. AI systems with theory of mind interpret the intentions behind an agent's social interactions by analyzing behavioral cues, communication patterns, and contextual information. They infer underlying goals, motivations, and beliefs from observable behavior and adjust their responses accordingly to facilitate effective communication and interaction. For example, in a negotiation scenario, an AI system might recognize cues indicating a desire for cooperation, competition, or compromise and adjust its negotiation strategy accordingly to achieve desired outcomes. AI systems with theory of mind adapt their behavior based on changes in an agent's level of trustworthiness by monitoring behavioral cues, communication patterns, and past interactions. They adjust their strategies and responses based on perceived shifts in trustworthiness to maintain effective collaboration and communication. For example, in a collaborative work environment, an AI system might build trust by demonstrating reliability, competence, and integrity in its interactions with other agents. AI systems with theory of mind handle situations where agents have hidden intentions by inferring underlying goals, motives, and beliefs from observable behavior and contextual cues. They use probabilistic reasoning and predictive modeling to generate hypotheses about hidden intentions and update their belief based on new evidence. For example, in a negotiation scenario, an AI system might identify hidden motives such as financial incentives or strategic alliances and adjust its negotiation strategy accordingly to achieve desired outcomes. AI systems with theory of mind recognize and respond to changes in an agent's level of commitment by monitoring behavioral cues, communication patterns, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in commitment to maintain effective engagement and cooperation. For example, in a collaborative project setting, an AI system might recognize signs of increased commitment, such as greater effort or enthusiasm, and respond with encouragement and support to maintain motivation and productivity. Social psychology plays a crucial role in informing the development of theory of mind in AI by providing insights into the underlying mechanisms of social perception, interpersonal relationships, and group dynamics. Researchers draw on theories and findings from social psychology to design computational models and algorithms that simulate theory of mind capabilities, such as empathy, perspective taking, and social influence. For example, social psychological experiments might identify factors influencing social influence and persuasion, guiding the design of AI systems that mimic similar social dynamics and behaviours. AI systems with theory of mind handle situations where agents have hidden beliefs by analysing behavioural cues, communication patterns, and contextual information to infer underlying beliefs. They use probabilistic reasoning and predictive modelling to generate hypotheses about hidden beliefs and adjust their responses accordingly to facilitate effective communication and interaction. For example, in a collaborative project setting, an AI system might recognise signs of conflicting beliefs among team members and mediate discussions to reconcile differences and achieve consensus. AI systems with theory of mind can recognise and respond to changes in an agent's level of assertiveness by monitoring behavioural cues, communication styles, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in assertiveness to maintain effective communication and collaboration. For example, in a negotiation scenario, an AI system might adjust its negotiation tactics in response to changes in the assertiveness of the negotiating parties to achieve mutually beneficial outcomes. Anthropology plays a role in informing the development of theory of mind in AI by providing insights into human social behaviours, cultural practices, and belief systems. Researchers draw on anthropological theories and findings to design computational models and algorithms that simulate theory of mind capabilities, such as cultural understanding, social cognition, and group dynamics. For example, anthropological studies might identify cross-cultural variations in social norms and values, guiding the design of AI systems that can adapt their behaviour to diverse cultural contexts. AI systems with theory of mind interpret the social identities and affiliations of different groups by analysing patterns of behaviour, communication styles, and group dynamics. They recognise social cues such as language, attire, and group interactions to infer individuals' social identities and group affiliations. For example, in a social networking context, an AI system might analyse users' interactions and shared interests to identify social groups and recommend relevant content or connections. Theory of mind has implications for AI systems' understanding of social power dynamics by enabling them to recognise, anticipate, and respond to hierarchical structures, authority relationships, and influence tactics within social groups. They analyse social cues, communication patterns, and interaction dynamics to infer power dynamics and adjust their behaviour accordingly to navigate social hierarchies and promote positive social relationships. For example, in a corporate setting, an AI system might adapt its communication style and decision-making approach based on the perceived power dynamics among team members. AI systems with theory of mind handle situations where agents have hidden desires by analysing behavioural cues, communication patterns, and contextual information to infer underlying motivations and goals. They use probabilistic reasoning and predictive modelling to generate hypotheses about hidden desires and adjust their responses accordingly to facilitate effective communication and interaction. For example, in a marketing context, an AI system might infer consumers' hidden desires based on their browsing history, purchase patterns, and demographic information to personalise product recommendations and marketing strategies. AI systems with theory of mind recognise and respond to changes in an agent's level of vulnerability by monitoring behavioural cues, communication styles, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in vulnerability to provide appropriate support, empathy, and assistance. For example, in a mental health support context, an AI system might recognise signs of increased vulnerability in a user's speech or behaviour and offer empathetic responses and resources to provide emotional support. Philosophy informs the development of theory of mind in AI by providing insights into the nature of consciousness, intentionality, and mental representation. Researchers draw on philosophical theories and concepts to design computational models and algorithms that simulate theory of mind capabilities, such as intention attribution, belief reasoning, and moral judgment. For example, philosophical inquiries into the nature of free will and moral responsibility might inform the design of AI systems that can reason about agents' intentions and ethical considerations in decision-making scenarios. AI systems with theory of mind interpret the social roles and responsibilities of different individuals by analysing patterns of behaviour, communication styles, and interaction dynamics within social contexts. They recognise social cues, such as role titles, duties, and expectations, to infer individuals' roles and responsibilities within organisations or communities. For example, in a team project setting, an AI system might analyse team members' contributions and communication patterns to identify leadership roles and distribute tasks accordingly. AI systems with theory of mind adapt their behaviour based on changes in an agent's level of autonomy by recognising cues indicating increased independence, self-determination, or decision-making authority. They adjust their communication style, decision-making processes, and interaction strategies to accommodate changes in autonomy and promote effective collaboration and engagement. For example, in a collaborative work environment, an AI system might empower autonomous decision-making among team members and provide support and guidance as needed to foster productivity and innovation. Literature plays a role in informing the development of theory of mind in AI by providing insights into human psychology, social dynamics, and interpersonal relationships. Researchers draw on literary works and narrative structures to design computational models and algorithms that simulate theory of mind capabilities, such as empathy, perspective taking, and narrative comprehension. For example, literary analyses might identify narrative techniques and character interactions that inform theory of mind development, guiding the design of AI systems that mimic similar narrative understanding and social reasoning. AI systems with theory of mind interpret social hierarchies by analysing behavioural cues, communication patterns, and interaction dynamics to infer power dynamics, authority relationships, and social status within human societies. They recognise signs of dominance, submission, and deference to understand individuals' positions within hierarchies and adjust their behaviour accordingly. For example, in a workplace setting, an AI system might recognise cues indicating leadership roles, such as assertive communication and decision-making authority, and tailor its interactions with different individuals accordingly. AI systems with theory of mind can adapt their behaviour based on changes in an agent's level of cooperation by monitoring behavioural cues, communication styles, and interaction dynamics. They adjust their strategies and responses to encourage or facilitate cooperation, collaboration, and teamwork. For example, in a team project setting, an AI system might recognise signs of increased cooperation, such as active participation and mutual support, and reinforce positive behaviours through acknowledgement and encouragement. Theory of mind has implications for AI systems' understanding of empathy and compassion by enabling them to recognise, anticipate, and respond to others' emotional states, needs, and experiences. They analyse emotional cues, contextual information, and interaction dynamics to infer emotional states and adjust their responses accordingly to provide empathetic support and understanding. AI systems with theory of mind handle situations where agents have conflicting priorities by analysing behavioural cues, communication patterns, and interaction dynamics to understand individuals' goals, preferences, and decision-making processes. They use probabilistic reasoning and predictive modelling to generate hypotheses about conflicting priorities and adjust their responses accordingly to facilitate conflict resolution or negotiation. For example, in a project management context, an AI system might identify conflicting priorities among team members and propose compromise solutions to reconcile differences and achieve consensus. AI systems with theory of mind recognize and respond to changes in an agent's level of satisfaction by monitoring behavioral cues, communication styles, and interaction dynamics. They adjust their strategies and responses based on perceived shifts in satisfaction to maintain positive relationships and interactions. For example, in a customer feedback scenario, an AI system might recognize signs of dissatisfaction in a user's tone or language and offer proactive solutions or assistance to address concerns and improve satisfaction. AI systems with theory of mind can use various strategies to handle situations where agents have conflicting values, such as facilitating open communication, promoting compromise, or mediating discussions to find common ground. They analyze behavioral cues, communication patterns, and interaction dynamics to understand individuals' underlying values and beliefs and negotiate solutions that align with shared interests or principles. For example, in a team decision-making scenario, an AI system might encourage constructive dialogue and information sharing to bridge differences and reach consensus. AI systems with theory of mind interpret the social norms and conventions of different cultures by analyzing cultural practices, customs, and communication styles to understand individuals' beliefs, values, and expectations within cultural contexts. They recognize cultural cues such as language, gestures, and social rituals to adapt their behavior and communication strategies accordingly. For example, in a multicultural workplace, an AI system might tailor its interactions and decision-making processes to accommodate diverse cultural perspectives and promote inclusivity and mutual understanding. AI systems with theory of mind can adapt their behavior based on changes in an agent's emotional state by recognizing emotional cues such as facial expressions, tone of voice, and body language to infer individuals' emotional states and adjust their responses accordingly. They use empathetic responses, active listening, and supportive gestures to provide emotional support and understanding. For example, in a mental health support context, an AI system might detect signs of distress or anxiety in a user's speech and offer calming responses and coping strategies to alleviate emotional distress. Theory of mind has implications for AI systems' understanding of cooperation and collaboration by enabling them to recognize, anticipate, and respond to others' intentions, goals, and perspectives within social contexts. They analyze social cues, communication patterns, and interaction dynamics to infer individuals' mental states and adjust their behavior accordingly to facilitate effective collaboration and teamwork. For example, in a collaborative project setting, an AI system might recognize signs of cooperation, such as active participation and mutual support, and reinforce positive behaviors through acknowledgement and encouragement. AI systems with theory of mind recognize and respond to changes in an agent's level of engagement by monitoring behavioral cues, communication styles, and interaction dynamics. They adapt their strategies and responses based on perceived shifts in engagement to maintain effective communication and collaboration. For example, in an educational context, an AI tutoring system might adjust its instructional approach based on the student's level of engagement to maintain interest and motivation. Developmental psychology informs the development of theory of mind in AI by providing insights into the cognitive processes, social behaviours, and developmental milestones associated with theory of mind development in humans. Researchers draw on developmental psychology theories and findings to design computational models and algorithms that simulate theory of mind capabilities, such as perspective taking, intention attribution, and belief reasoning. For example, developmental psychology research might identify key milestones in theory of mind development, such as the ability to understand false beliefs, guiding the design of AI systems that mimic similar developmental trajectories and social cognitive abilities. AI systems with theory of mind interpret the intentions behind an agent's social interactions by analyzing behavioral cues, communication patterns, and interaction dynamics to infer individuals' goals, motivations, and desires. They recognize social cues such as facial expressions, gestures, and verbal cues to infer intentions and adjust their behavior accordingly to facilitate effective communication and interaction. For example, in a social conversation, an AI system might recognize cues indicating the speaker's intention to share information or seek clarification and respond appropriately to support the interaction. AI systems with theory of mind can adapt their behavior based on changes in an agent's level of trustworthiness by monitoring behavioral cues, communication styles, and interaction dynamics. They adjust their strategies and responses based on perceived shifts in trustworthiness to maintain positive relationships and interactions. For example, in a collaborative project setting, an AI system might recognize signs of increased trustworthiness, such as open communication and reliability, and adjust its interactions with different individuals accordingly to foster trust and cooperation. Theory of mind has implications for AI systems' understanding of reciprocity and fairness. By enabling them to recognize, anticipate, and respond to others' expectations, preferences, and norms within social interactions. They analyze social cues, communication patterns, and interaction dynamics to infer individuals' reciprocity preferences and adjust their behavior accordingly to promote fairness and cooperation. For example, in a negotiation scenario, an AI system might recognize cues indicating expectations of reciprocity and fairness and adjust its negotiation strategy to accommodate shared interests and principles. As we conclude today's exploration into the theory of mind, we hope you've gained valuable insights into the intricate mechanisms that shape human interactions and understanding. Remember to like, share, and subscribe to our channel, Minds Unraveled, for more thought-provoking content. Let's continue to foster empathy, understanding, and connection in our ever-evolving world. Until next time, keep pondering, keep questioning, and keep unraveling the mysteries of the mind. Thank you for joining us on this enlightening journey.